Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Recording by Michelle. Lesson 1. Geology defined. Form of the earth. Its surface. Internal heat. Mineralogy defined. Definition of the term rock. Formations. Strata. The origin of strata. Vegetable earth. Alluvium. Division of the formations. Plutonic formations. Neptunian or stratified rocks. Order of strata. Temple of Jupiter Serapis. Subsidence and elevation of coasts. Geology. From the Greek, ge, the earth, and logos, discourse, or science of the earth, is that branch of natural history which treats of the physical constitution of our globe. The earth, as is generally known, is in the form of a ball, or spheroid, slightly flattened at the poles, floating freely in space. Its diameter is about 8,000 miles, and its surface is irregular. Here it is studded with long chains of mountains, there hollowed by deep depressions. But these inequalities, however gigantic they may appear, when compared with objects surrounding us, are in reality very trifling. In comparison with the mass of the globe, they are proportionally much less than those we see on the skin of the smoothest orange, and if represented on a ball 3 feet in diameter, the highest mountains would still be so small as almost to require a microscope to perceive them. The deepest excavations of the surfaces of the globe are covered by great masses of water, which conceal them and prevent their examination, but there is reason to believe that the most profound depressions do not much exceed 3 miles in depth below the surface of the sea, and we know by exact measurement that the summit of the loftiest mountains is not 6 miles above the same level. The surface of the earth has not always possessed the same configuration that it now presents. It has been frequently upturned, and there is even reason to believe that the entire globe was a liquid mass melted by heat, and that it gradually became solid as it cooled. Except at comparatively shallow depths, we cannot examine the nature of the materials constituting our globe, not even by descending into mines excavated for the purpose of extracting the wealth they contain, for the deepest of these excavations do not exceed 500 yards. But by calculations it has been inferred that the centre of the earth cannot be occupied, either by water or by vapour, but by matter as heavy as our heaviest metals, and so hot that it is probably in a state of constant fusion. A great number of facts concur in proving that the earth possesses an internal heat, the remnant of the original heat, independent of that which it receives from the sun. Its temperature increases in proportion as we descend to considerable depths. There are some very deep mines in which the workman can only labour when naked, and whenever the water of a spring rises from a great depth, its temperature is always very high. This increase of temperature has even been measured, and it has been ascertained that the heat of the earth increases about 2° Fahrenheit for every 70 to 100 feet. In very deep cellars, where the influence of the seasons is not felt, and where the temperature is always the same, the thermometer at Paris stands at about 51°, and at a depth of 200 feet below these cellars the heat is about 55°. At a league below the surface the temperature must be above that of boiling water, and at a depth of less than 2 leagues it must be sufficient to melt tin. It appears to be demonstrated that the globe at some remote period was in a state of incandescence, or liquefaction from heat, and that it cooled by degrees, but we must not conclude that this cooling process has continued to the present time, and is still going forward. It has almost, if not entirely, ceased. From the earliest records of history to the present moment, the temperature of the globe has not sensibly changed, and by the calculations of the learned, it is proved that the surface of the earth receives from the sun during the year a quantity of heat equivalent to that which it loses in the same space of time. The internal heat of the earth no longer influences the temperature of its surface, except in an insensible degree. and to diminish this influence, which is almost none at all, one half, would require the lapse of 30,000 years. Our knowledge of the central portion of the globe is limited to what we have just said of its weight and temperature, but the solid crust constituting its surface has been better studied. This crust is not formed of a single piece, but is composed of a great number of various materials. The study of these various substances particularly belongs to mineralogy. The study of their mutual relations, and the more or less important part they play in the constitution of the globe, is a province of geology. In general, we give the name of rocks to mineral substances which are united in great masses, and apply the term formations to diverse assemblages of rocks which appear to have been formed under the same circumstances. The word rock, as used by geologists, is applicable to all mineral masses, whether hard or soft, and therefore includes in its meaning sand, marble, clay, granite, etc. When we examine the sides of mountains, artificial excavations, and various other localities favourable to geological studies, we very soon perceive that there are a great many different formations, and these formations are in layers or stories reposing one above the other, constituting strata, the plural of stratum, a Latin word meaning a bench, couch, or layer, anything spread out or strewed over a surface. We can be convinced of this by examining the cuts made through hills for the passage of railroads and canals in various parts of the United States. By comparing the different materials composing the earth's crust, the geologist will soon be satisfied that these different rocks, in a majority of instances, are not placed one alongside the other, but cover each other and form a series of layers of more or less thickness, comparable to the courses or layers in a mass or wall of mason work. Gypsum or plaster of Paris, for example, rests upon a stratum of coarse limestone, for in digging wells in the neighbourhood of Paris, at different points, the coarse limestone is always found below the plaster. This coarse limestone in its turn covers a stratum of plastic clay. In many places where the coarse limestone is not very thick, it has been pierced through, and the plastic clay is found beneath it. But it is not necessary to dig wells in order to be certain of the superposition of different layers formed by these rocks. It is distinctly seen by examination of the declivities of certain hills, or cuts made through them for the passage of roads, etc. For when the point of contact of two layers is exposed at one of these localities, we may frequently distinguish without difficulty the manner in which one of these layers is continued beneath the other. In other places nothing similar is seen. The rocks show no trace of stratification, but constitute compact masses, such as granite. To form an idea of the manner in which nature has produced these immense earthy layers, we must study the phenomena which are now taking place at different places on the surface of the earth. The action of rain, of the sun, of frost, and many other causes, are constantly tending to change the surface of rocks, even those which are most compact, and to detach fragments from them. These fragments, more or less divided, are spread out over the surface of the soil, mixed with the detritus of plants and animals, and constitute a kind of movable bed, more or less thin, which covers the whole surface of the globe, and bears commonly the name of vegetable earth, because it is in this bed that almost all vegetables grow. The mineral substances which enter into its composition are ordinarily sand, clay, or the debris or the remains of calcareous rocks. Detritus is a geological term applied to deposits composed of various substances which have been comminuted by attrition. The larger fragments are usually termed debris. Those which are pulverized, as it were, constitute detritus. Sand is the detritus of siliceous rocks. When currents of water pass over movable formations, such as we have just mentioned, they take up a portion and convey to a distance the detritus and debris of which they are composed. In this way, when the heaped up snows on the tops of mountains melt under the influence of the summer sun, or when abundant rains fall on the same places, impetuous torrents descend towards the plain, and carry with them earthen fragments of stones found in their route, or which they tear up from their resting places. The result is that the water of these torrents is often turbid, and loaded with mud, sand, flints, or even blocks of stone, but when they reach a flat country, or fall into a large basin, their course is much less rapid. and the foreign materials they held in suspension are gradually deposited. The heaviest sink first, and at length these materials line the bottom of the river in an earthy bed whose thickness is continually increasing. The river Po, which is precipitated from a lofty chain of the Alps, and traverses Lombardy, is a remarkable example of this curious phenomenon. This river and its principal tributaries have transported in this way so much earthy matter from the mountains to the plain, that since the Roman era several large lakes and extensive marshes situated near Parma, Paysance, Cremona, etc., have been filled up and become dry. The bed of these rivers is also gradually filled up, so that they have several times changed their course, and poured over the neighbouring plains. It has been necessary to restrain them artificially by building up a long dyke on each bank. This has put an end to these disastrous inundations, but has not prevented the bottom of the river from continuing to rise up. Every year it is therefore necessary also to raise up the dykes, so that now these rivers flow in a sort of immense aqueduct, and at certain places the surface of their waters is higher than the roofs of the surrounding houses, as in Ferrara, for example. The river Rhone descends on the northern side of the Alps, and passes the Valais too impetuously to deposit the mud and flints with which it is abundantly freighted. But when it empties into the lake of Geneva, its course becomes so slow as to be almost imperceptible, and its waters, which were at first turbid and muddy, are limpid and transparent when they escape from the opposite side of the basin to pass through the town of Geneva. The result is that the Rhone deposits in this basin all the materials which it carried, and gradually raises up its bottom, constituting what is termed lacustrine formation. This progressive elevation of the soil is so marked at the eastern extremity of the lake, that an ancient town called Port Valais, formerly situated on its margin, is now found about a half a league from it. About 8 centuries have been sufficient for the formation of the great earthy bank which now separates this town from the lake, and the deposit which gave rise to it continues to be made at the bottom of that portion of the lake in its vicinity, and continually tends to raise it up more and more, so that in time it may fill the whole of this basin, and transform the lake into a plain which the Rhone will pass through without spreading itself. In passing through Geneva, this beautiful river, as we have already said, is clear and limpid, but a little beyond the town it receives new tributaries, such as the Arve, which pour into it their muddy waters, and little by little it is again loaded with sand and mud, which rolls on impetuously to the sea. But at its mouth, its course being slow, these foreign materials, the debris of Mont Blanc, of the Alps, the Dauphiné, and the central regions of France, are in their turn deposited, and gradually elevate the soil they cover. The result is new land, which advances more and more on the sea. We give the name alluvion from the Latin alluvio, an inundation, or alluo, I wash, to formations caused in this way by the deposit of materials carried by waters. And as these alluvial formations, when deposited at the mouth of a river, often assume the form of the Greek letter delta, we designate the new made land, which in a manner encroaches on the domain of the sea, under the name of delta. The delta of the Rhone, to which we alluded above, and that which is found at the mouth of the Po, are very inconsiderable, but in certain parts of the globe several are found of very much greater geological importance. One of the most celebrated is the delta of the Nile, which, according to the calculations of some authors, must have grown nearly half a league since the time of Herodotus, and according to the commonly received opinion, its formation began at the foot of the rocks upon which were built the pyramids of Memphis. But the deltas at the mouth of the Mississippi and the mouth of the Ganges increase more rapidly, and possess greater interest for the naturalist. Other formations are also produced, so to speak, under our eyes by the deposit of materials which the waters of certain springs hold in solution, and throw down when they can reach the surface of the earth. In different parts of France, near a spring situated at the north of Clermont-Ferrand, for instance, we see examples on a small scale, and in many parts of Italy enormous masses of calcareous stone, known under the name of travertin, from the Italian travertino, are formed. We often behold issuing from the craters of volcanoes a burning semi liquid matter, which spreads over the surface of the neighbouring country, and on cooling is converted into a hard compact rock called lava. Etna has furnished a great number of eruptions of lava, one of which is 6 leagues in length, and in 1783 Helka, a volcano of Iceland, gave origin to a similar current, which extends 20 leagues in length and 12 in breadth. These different phenomena partly explain to us the manner in which the production of the different formations disseminated on the surface of the globe must have been effected, formations whose origin date back from an epoch long anterior to that of the creation of man. In fact, the various formations constituting the common portion of the globe differ, as we have already seen, very widely in their nature, in their constitution, and in their mode of arrangement. Now these differences remind us of those which exist in the modern formations above mentioned, and seem to indicate that in the ancient formations some were produced in the midst of the waters, by the deposit of solid materials held in suspension or solution by this liquid, and others by the action of heat on earthy materials susceptible of being melted and of being afterwards hardened by cooling. Guided by these considerations, geologists have divided the formations into 2 great classes, namely, the sedimentary or stratified formations, and the massive or igneous formations. On account of the presumed method of their production, they are also designated under the names of aqueous or Neptunian formations and igneous or Platonic formations. The Platonic formations have received this name because they appear to be the product of the action of fire. They are generally of a dense crystalline structure, and ordinarily form very immense masses. They are not arranged in regularly superposed beds, nor do they contain the remains of organized bodies. Some of them are formed, as we see, by the action of volcanoes, and others are very analogous to the latter. They contain not only minerals peculiar to volcanic ejections, but sometimes also matters that are produced by the furnaces of our laboratories and workshops. They seem to have formed the primitive crust of the globe, for we find them beneath the Neptunian formations, but they are also sometimes spread over the surface of the latter, or betwixt the different beds or strata of which they are composed. The aqueous or Neptunian formations appear to have been deposited by the waters. In general, their texture is coarse or compact, rarely crystalline, and they are often composed of grains of sand, separate or agglutinated of heterogeneous fragments or material having the aspect of a kind of indurated mud. They are also frequently called stratified formations, and most of them are also termed sedimentary formations. It is in the midst of these formations that we find the remains of the different organized bodies by which the earth has been successively peopled. These stratified formations are not all produced at once, but successively, and under the influence of different circumstances. They constitute, as we have said before, distinct beds or strata, and these strata lie one on top of the other, so that those of a more ancient are found beneath those of a more recent formation. By studying them carefully, we shall also perceive that different points on the surface of the earth have been successively and at intervals left dry and covered by the waters of the sea, or by fresh water, the sediment from which constitutes these banks. And we see that these banks themselves differ, not only in the nature and disposition of their constituting elements, but also in the nature of the remains of the organic bodies buried in their substance. We distinguish a great number of these stratified formations, and, as might be anticipated from their mode of production, they are everywhere found in the same order of superposition. The formation which, in one locality, covers another formation, can never be found in another place beneath the latter. It may be entirely wanting, so as to leave the latter uncovered, or in contact with the stratum, which in another place it covered, but wherever it exists, it must be on top of or superior to all formations, the production of which dates back to a more remote epoch. For example, we have stated that in the vicinity of Paris the gypsum rests on the coarse limestone, this upon the plastic clay, and this plastic clay upon the chalk. In other localities we may find new strata interposed between these various formations, or we may find one of them entirely wanting, for example, the plastic clay being absent, The coarse limestone would be found resting directly upon the chalk. But this coarse limestone, for the reason alone that it is everywhere found resting upon the chalk, must have been deposited after the chalk was formed, and consequently can never be found below it. It is also evident that when these solid beds are slowly deposited at the bottom of waters, they must have a nearly horizontal position, and that they must occupy the steepest parts of the surface upon which they are formed, so that if the surface presents considerable elevations, these may remain uncovered, and show themselves above the level occupied by the new formation. Thus, when we go from low plains towards mountainous chains, and ascend to their summits, we meet successively formations more and more ancient as we rise. Sometimes these stratified rocks preserve the horizontal position they had at the beginning, but at other times they become more or less oblique, in consequence of their partial depression, or sinking, or their unequal elevation. Frequently we see beds which are abruptly raised up, so as to be almost perpendicular, and on the edge of the elevation produced by this overturning of nature, we find other beds which are perfectly horizontal, and we may conclude that the latter were formed subsequently to the elevation of the former. By studying these relations of position, we are enabled to determine the geological age of the mountains. These great movements of strata sometimes take place suddenly, and are accompanied by earthquakes, but at other times they are effected gradually and without any shock. It appears to be well ascertained that since the time of the Romans, a portion of the coast of Naples sank below the level of the sea, and was subsequently raised up again above this level, without overturning the monuments built on this movable soil. One may be satisfied of this fact by visiting an ancient temple situated near Pozzuoli, called the Temple of Jupiter Serapis. This monument, of which 3 columns remain standing erect, appears to have been built in the 3rd century, and was then very much frequented, on account of its warm baths. But at a subsequent epoch, supposed to be about 1488, the ground sank down, and the temple was covered by the sea to a height of about 16 feet above the pavement. Marine animals then established themselves on a portion of the submerged columns, and mollusks of the genus Pholas excavated innumerable holes in the same way as they do in rocks now covered by the sea. But in the present day the state of things is not the same. The pavement of the temple is again dry, and the traces of the foliage we have just mentioned are at a considerable height above the level of the sea. Now these changes in the relative levels of the coast of Pozzuoli and the neighbouring sea cannot be attributed to an alternate sinking and rise of the waters, because movements of this sort must have been accompanied by fearful inundations along the shores of the Mediterranean, but we cannot explain this phenomenon except by supposing that the coast itself, after sinking, was again gradually raised up. At the present time Scandinavia and Chile exhibit an analogous phenomenon. On the coast of Sweden, for example, we see certain rocks which were formerly submerged now above water, and that the steep shores gradually rising more and more above the level of the sea. For a long time it was observed that the sea abandoned certain parts of the coast, and that the depth of the water decreased in several ports of this region. But these changes of level have been ascertained in a more exact manner. More than a century since, marks were made on different rocks on a line with the surface of the water, to serve as points of comparison, and on examining them from year to year it was found that these marks were successively higher and higher above the level of the sea. In the Gulf of Bothnia this rise appears to be 4 feet in a century, but at other places less, and at some points on the coasts of the Baltic it was nothing, which proves that the change of level does not depend on the subsidence of the sea. We shall recur to the subject of stratification and the various causes which influence it, after we have studied the characters of the various formations. End of Lesson 1.
Lesson 2 of Elements of Geology by W.S.W. Ruschenberger. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Barbara Jade Siranen. Elements of Geology by W.S.W. Ruschenberger. Lesson 2. Organic Remains. Fossils, how produced. First geological epoch, primitive rocks, granite, gneiss, mica schist, argillaceous schist. Second geological epoch, transition formation, Cambrian system, Silurian system, trilobites and other animal remains. Devonian system, fossil fishes, fossils, limits of the transition formation, strata changed in position by geological convulsions. We find entombed in the different strata of the crust of the globe a great quantity of the remains of organic bodies, which at different epochs have lived on its surface. Those which exist in the present formations, and which have been deposited since the last great revolutions of the earth, generally preserve their primitive composition. But those which have been found in the more ancient strata have been altered in their nature and passed into the fossil state. The gelatinous, fleshy, or ligneous portions, which concurred in their formation, have in part disappeared and have been more or less replaced by stony particles. By the term fossil, formed from the Latin fodio, I dig, is meant any organic body, or the traces of any organic body, whether animal or vegetable, which has been buried in the earth by natural causes. In general, it is the hard parts, those that are capable of long-resisting decomposition, which alone undergo this kind of alteration, such as bones, shells, and scales, for example. We never find flesh, nor nails, nor soft fruits, nor other analogous bodies in a fossil state. Sometimes even these hard bodies disappear and leave merely traces of their existence in an impression or print in the rock that envelop them. The organic remains which are found in the most superficial and most recent strata of the crust of the earth belong in part to species which still exist. But most fossils are derived from animals or plants which have not existed since a period anterior to historic times, and the species of which are now totally extinct. In general, they differ from species now living more and more in proportion to the antiquity of the strata in which they are found, and in most of the strata of the earth's crust we find certain species which are not met with either in more ancient or more recent formations. It is by comparing the fossils with each other, and by combining this study with that of the order of superposition in which the different strata are found, and with their mode of formation, that we have arrived at a knowledge of the earth at periods long anterior to the creation of man, and are enabled to trace the history of the great revolutions which have successively disturbed and changed its surface. We learn by this study that the physical condition of the surface of the earth, as well as that of the organized beings by which this surface is inhabited, has undergone great and numerous changes. Entire creations of animals and of plants have succeeded each other, after having peopled the waters and inhabited the land for ages. Each in its turn has been destroyed by some great catastrophe of nature and given place to a new creation. But the appearance of a new flora or a new fauna, the destruction of living beings, and the deposit of enormous beds of rocks are not the only phenomena which characterize the great revolutions of the earth. At different epochs, total overthrows, of which the most fearful earthquakes and volcanic eruptions of our times can give but a very feeble idea, have raised up the solid crust of the globe and produced lofty chains of mountains whose elevation, immense as it appears to us, was even still greater before the valleys and basins that separate them were gradually filled by new deposits. The great revolutions of the earth appear to have been separated by long periods of tranquility, during which animals and plants multiplied on different parts of the globe's surface, and deposits of solid materials, borne by the waters or drawn from the bosom of the earth, were heaped up, constituting beds of rocks of greater or less thickness, and varying in their nature, in the substance of which were entombed the remains of contemporaneous animals and plants. The natural history of the globe is written in the very rocks of which our planet is composed, and the study of these ancient monuments of the power of the Creator teaches us what transpired long before the existence of man on the earth. These fossils are truly the metals of creation, metals which are more important and incomparably more ancient than all those of Greece and Rome, or the hieroglyphics of Egypt. Of the natural revolutions of the globe. The history of the globe, like that of nations, is divided into a certain number of distinct periods, during each of which the state of things changed but little, yet it resembles neither that which preceded nor that which followed after it. Geologists designate under the term formation the assemblage of rocks which were produced during each one of these periods, comprised in the interval between two of these revolutionary disturbances of the globe. For example, they give the name of Cretaceous formation, from the Latin creta, chalk, to the assemblage of rocks which were deposited or derived from the interior of the earth during a geological epoch in a part of which chalk was deposited. And Jurassic formation is the name given to the assemblage of contemporaneous sedimentary rocks composing the most remarkable strata of the mountains of Jura, etc. Beginning with the most ancient, we will examine these several formations in succession. First geological epoch. Primitive, primary, primordial, or unstratified rocks. Note: Mr. Lyell proposes to designate this system of rocks by the term hypogene, from the Greek upo, under, and genomi, I beget, because they are found under other rocks. He objects to the words primary and primitive because these terms convey a notion as to the time and age of the formation, and might lead to the error of supposing that they were formed before any other rocks were formed. But the term hypogene refers exclusively to position. Under the name of primitive or primary rocks, from the Latin primus, first, before, we ordinarily designate the different rocks which appear to have been formed before the creation of plants and animals, the remains of which are found in less ancient strata and seem to be a foundation for rocks subsequently produced. As already stated, at its origin our globe must have been a mass kept in a state of fusion by the action of heat, and its surface became solid by slowly cooling. This first crust must have remained for a long time in a soft or pasty condition, and at first its temperature must have been too high to permit water to remain on its surface without evaporating. It must have been split in different directions by the contraction produced by cooling, and then resembled the masses of ice which in our day cover the surface of the polar seas. That is, it presented a very unequal surface, studded with immense fragments heaped up in all directions. In this first geological epoch were formed the massive rocks, such as granite, which serves as the base of all other rocks, and is the result of the solidification of mineral substances previously melted by heat. The cooling of this first crust must have also caused the precipitation of the least volatile matters diffused in the atmosphere, just in the same manner as a cold body placed in a warm, moist air is quickly covered by a layer of condensed vapor. And from this cause came new changes in the configuration of the surface of the globe and the formation of new beds of a crystalline texture. The most ancient portion of the crust of the earth known to geologists is composed chiefly of granite and some other unstratified rocks, which appear to be also of igneous origin. We give the name of granite to a rock which is extremely hard, having a rough fracture which is composed of a confused agglomeration of crystals formed of three distinct materials. Some of these crystals have a glassy appearance and are ordinarily of a grayish color. They are quartz, the same material of which rock crystal is composed. Others, often large, opaque, and sometimes rose-colored, sometimes green, sometimes white or yellow, are formed of a mineral called feldspar. And the third variety of crystals, which are composed of mica, resemble small, brilliant spangles, sometimes black and sometimes silvery white. Granite, then, consists of quartz, feldspar, and mica. Certain varieties of granite remain for centuries exposed to the inclemencies of the weather without undergoing any alteration, but other varieties are speedily disintegrated by the action of the atmosphere and are thus reduced to a kind of grit or argillaceous earth. It presents no trace of stratification and possesses all the characters of a rock of igneous origin. Granite, which seems to form the first basis, the foundation stone of the great geological edifice, remains uncovered at various points on the surface of the earth, while in other places it is covered by more or less numerous beds of more recent formations. But all the granitic rocks now scattered over the surface of the globe do not date from an antiquity so remote, for, in different recent epochs, mineral materials in a state of fusion have escaped from the bosom of the earth, which spread over formations then existing, and, on cooling, constituted immense masses of granite similar to that first formed. This rock is met with in different places in all parts of the world, and is employed in the construction of edifices of various description. The beds which are deposited on the first massive crust of the globe are crystalline in structure, and this character is more decided the more ancient they are. They seem to have been exposed to the action of a great heat without possessing the characters of rocks of igneous origin. They consist principally of gneiss, mica schist, and argillaceous schist. Gneiss is a rock very analogous to granite as respects its elementary constituents, but its structure is foliated and presents a stratified arrangement. It appears to have been formed under water and seems to be the most ancient of the sedimentary formations because in certain places on the surface of the globe we find it covered by all the other formations. We often see it naked. It forms vast systems of rocks in which it is often alternated with mica schist and other ancient rocks. It is used in building and flagging. Mica schist is a lamellar rock composed of quartz, ordinarily grayish, and a great quantity of brilliant lamellae of mica arranged in extended leaves or scales. It commonly accompanies granite and gneiss. Argillaceous schist is in appearance an earthy rock, which is easily divided into large laminae, more or less thin, and was evidently formed under water by the deposit of sediment. Schist, from the Greek schistos, slaty, easily split. We also find in these primitive strata compact limestone of great hardness and other rocks which more or less resemble the preceding. These different rocks, the origin of which dates from the earliest period of geological history, constitute a great part of the present surface of the globe and are often found at great depths beneath less ancient formations. They present evident traces of great overthrows, and the beds or layers which they form no longer occupy the horizontal position they must have had in the beginning, but are more or less inclined, twisted, and fractured, as if at various times they had been broken, and their immense fragments irregularly raised up. Those countries in which the primitive rocks constitute the surface are knotted and mountainous, and we find these same rocks in the most elevated points of the globe, where they form the mass of most great mountain chains. The central plain of France, comprising Auvergne, Limousin, Vivarais, and Valais, is formed almost entirely of primitive rocks, most of which are granitic. The same is true of a great part of Brittany and Corsica, Scandinavia and Finland, etc. These ancient rocks also constitute a large part of the Great Alps, of which Mont Blanc is the highest point, the Eastern Alps from San Goda to Hungary, the Pyrenees, the chain of Jetzgeberge in Saxony, the Grampian Hills of Scotland, the Ural Mountains in Russia, the Alleghenies in the United States, and the Andes in South America. As we have already stated, we find no fossils in the sedimentary formations of this geological period, and it is therefore inferred that in this epoch no living beings existed on the surface of the globe, but it may have been otherwise, and the absence of fossils in these strata depends on some cause, such as their destruction by heat, resulting from their vicinity to enormous masses of igneous rocks, effused near to, or even over and above, these non-fossiliferous strata. Second geological epoch, Transition Formation. The stratified formations which rest on the primitive strata just mentioned present us with the first traces of the existence of living beings on the surface of the globe, and constitute a particular division generally named the Transition Formation, but designated by Mr. Lyell as the primary fossiliferous formation. The most recent name given, however, to these formations is Paleozoic, formed from the Greek polluios, ancient, and zoon, an animal, because they contain ancient animal remains. These formations closely resemble the preceding, and it is often difficult to distinguish them, but they do not appear to have begun to form until the first had been disturbed by some great geological convulsion. For the strata of which they are composed are not parallel to those of the rocks on which they rest, and they differ from them by having fossils entombed in their substance. They appear to have been formed by a slow and continuous deposit of sand, mud, and other materials suspended in water, and they consist chiefly of schists and calcareous rocks. The sea seems, then, to have covered the greatest part of the known surface of the globe, for we scarcely find a trace of terrestrial plants, and immense depots of these strata, almost identical in character, are met with in the most distant parts of the earth, as in Germany, England, and America. To judge by the fossils concealed in these formations, the globe was then inhabited by a small number of plants belonging for the most part to the family of Fucus, and by a multitude of marine animals, the forms of which differed widely from those now existing. It is also remarked that most of these animals belonged to the inferior classes of the animal kingdom, and, until lately, it was believed no vertebrate animal then existed. But within a short time it has been ascertained there were marine fishes, for remains of them have been discovered in certain rocks whose formation dates back to this remote epoch. The most ancient beds of the Transition Formation contain very few fossils, while other rocks of the same formation are rich in these remains. These differences, which correspond with other peculiarities of stratification, have led geologists to divide this period into three divisions, called the Cambrian, Silurian, and Devonian systems of rocks. The Cambrian, from Cambria in Wales, or schistose system. The Cambrian rocks are the lowest sedimentary deposits known. They are composed essentially of schistose grauwackes, which pass through all shades of solidity, luster, and color. On one side they unite with the mica schists and gneiss, and on the other with the coarse grauwackes with which they are found intercalated. These rocks contain slate rocks, conglomerates, dark limestone, and fine-grained slates of various shades of purple, blue, and green. In the Cambrian rocks, the organic remains consist of a few fossil brachiopods, polyparia, or coral animals, etc. The Silurian system, from the Silures or Siluri, the ancient Britons who inhabited the region where these strata are most distinctly developed, is next above the Cambrian. It is subdivided into the upper and lower Silurian strata. In its mineral composition, it so closely resembles that of the Cambrian that it is often difficult to distinguish them. These strata are entirely of marine origin, and many of the beds, as the well-known Dudley limestone, are composed of shells, corals, crinoidea, and those peculiar crustaceans termed trilobites, held together by a calcareous cement. The presence of these fossil animals is characteristic of the Silurian and Devonian systems of strata because they are rarely met with in other situations. They are found entombed in slate and dark limestone. Trilobites, from their extraordinary form and appearance, have, for more than 150 years, been objects of great interest to the naturalist and of wonder to the general observer, and have long been provincially termed Dudley insects or locusts. The most common examples consist of a convex oblong body divided transversely into 3 principal parts and longitudinally into 3 lobes by 2 deep parallel furrows. From this last character, by which the family is recognized among naturalists, the name trilobite, from the Latin trace, 3, and lobus, lobe, has been derived. These fossils are the carapaces or shells of crustaceans belonging to an extinct family which comprises many genera and numerous species. The class of crustaceans consists of 2 groups, namely, those with eyes supported on movable peduncles, as the crab and lobster, and those with eyes fixed. The extinct order of trilobites belongs to the last. The Calimene blumenbachii is named after the celebrated German naturalist Blumenbach. The generic name Calimene, formed from the Greek kakeliumen, concealed, was devised to express the obscure nature of this genus of trilobites. It is found expanded with its under surface attached to and blended with the limestone, or coiled up. The head is large, convex, rounded in front, with a broad border, and divided into 3 lobes by 2 longitudinal depressions. It has 2 compound eyes with numerous facets, situated at the back of the head remote from each other. This species is from 1 to 4 inches in length. It is a curious fact, says Mr. T. A. Conrad, paleontologist, State of New York, 1838, that whilst the Calimene blumenbachii ceased to exist in New York after the final deposition of the Trenton series, it escaped into remote seas and lived in the era of the Dudley limestone. In another genus, Esophus, from the Greek ossophes, obscure, the carapace is wide and much depressed, the middle lobe distinct, the cephalic portion rounded in front and terminating posteriorly in a sharp process on each side. The eyes are compound and each contains 400 spherical lenses. Some kinds of Esophus have remarkably long, pointed caudal appendages or tails. Some American species of this group are 18 inches in length. Besides the trilobites, the remains of other animals are found in the Cambrian and Silurian systems. They mostly belong to the division of brachiopod mollusks. Among those which are regarded as characteristic of the Silurian system are the Orthis orbicularis, Orthis testudinaria, The orthus is a circular shell with a striated surface and long, narrow hinge. The orthoceras, from the Greek orthos, straight, and kyros, horn. The lithoides, of large dimensions. The productus, Latin, drawn out, dilated, or leptina, from the Greek leptos, slender. The genus Productus has received its name from a peculiarity observed in several species where the dorsal valve, after having attained a certain magnitude, bends suddenly at right angles to its former direction and is then continued irregularly, sometimes being produced, extended, to a considerable length. The whole shell is usually covered with striae and spines, which in some species are numerous and very long, and which appear to have been movable, doubtless serving a purpose in the animal economy. The spirifer, from the Latin spira, a wreath or twisting, and fero, I bear, is a brachiopod closely resembling the terebratula in many important characters, but differing from it in the singular spire of calcareous matter passing across the interior of the shell, and from which the name of the genus is derived. The species are very numerous and, next to terebratula, are the most abundant of all brachiopod fossils. The genus Terebratula, from the Latin terebro, I bore, board, alluding to the perforated beak. Throughout the whole of the Paleozoic formation, certain species of terebratulae are found. This remarkable genus, which has in the present day some representatives in the existing seas, appears to have been created among the very first of the inhabitants of the first formed ocean, and to have retained its place longer than any other. From the incalculable antiquity of their lineage, the terebratulae have been humorously styled the fossil aristocracy. The genus Pentamerus, from the Greek pente, 5, and merus, parts or cells, contains 4 known species, all of which belong to the Silurian rocks. In this genus, the lesser valve is divided internally by 2 parallel walls or septa running close together lengthwise along the shell, forming 3 cells. The other valve also has a septum or wall, which is forked towards the beak of the shell and divides it into 2 cells, thus forming the 5 cells to which it is indebted for its generic name. The casts of these shells often have fissures produced by the decomposition of the septa, and occasionally these cavities are occupied by calcareous spar. Of the polyparia, or corals, which existed when the Silurian rocks were formed, representations of 2 genera are given. The Cyatophyllum, from the Greek quathos, a cup, and phyllon, a flower. The abundance of corals of this genus in the Silurian system proves that the seas of that epoch must have teemed with these zoophytes. The Catinopora, from the Latin catina, a chain, and porus, a pore. The oval form of the cells when united laterally, and the flexuous disposition of the lamellae, give rise in transverse sections to the elegant catenated markings, from which appearance the fossil has received the name of chain coral. The species figured is common in Silurian limestone and sometimes forms hemispherical masses more than a foot in diameter. The organic remains of the Cambrian system differ from those of the Silurian system in being less developed. The genera and species of mollusks and corals found in both are alike. The Devonian system, so called because it is largely developed in Devonshire, England, forms the superior part of the preceding formation. It appears to be composed at first of pudding stone, with which it commences, and to pass to sandstone, with which it alternates at different places. Then come sandstone schists, more or less fine, different species of schist, limestones, alternating with each other, in the midst of which are found beds of anthracite. These various materials are differently developed in different countries. In England, the sandstones predominate. They form the old red sandstone, comprising strata of clay and marl of different colors. In other places, the limestones prevail with different clay slates or chloritic schists, sometimes intercalated with schistose quartz, as in Devonshire, and sometimes almost alone, as in Cornwall. This system presents us with depots of the oldest combustible materials known, and we find in it ferns, calamites, diverse species of plants differing but little from the plants found in the coal formation which immediately follows. We here find also a great many polyps, more or less analogous to the Caryophylla, amplexus, by some regarded as polyps and by others as chambered shells, which are found nowhere beside. The calceola, so nearly resembling certain productus, appears to be characteristic of the Devonian rocks, and perhaps also the Clymenia linearis, a chambered shell with aventral siphon. Certain peculiar bivalves are also found, some brachiopods, and among others the Terebratula porrecta. Slates, so extensively used for roofs, are furnished from this group of ancient rocks, and on many we find impressions of trilobites. The upper part of the transition strata often contains carboniferous materials, sometimes disseminated among the schists, and at others constituting more or less extensive masses, which are generally composed of anthracite, though sometimes of bituminous coal. These three systems of rocks, namely the Cambrian, Silurian, and Devonian, which are not easily distinguished from each other, are found in most countries of Europe, where their assemblage constitutes the greater part of what is named the transition or Paleozoic formation. They abound in Brittany. There the anthracitiferous mass forms a stripe along the Loire, extending from Maine to Morbihan, as well as other depots in Sardes and Mayenne. These rocks are found through the whole chain of the Pyrenees, in the southern part of Cévennes, in the mountains of Forez and Beaujolais, and in some parts of Vosges. They form all the Hunsrück, Eifel, and Ardennes, and the southern part of Belgium. They are met with in Harz, in Saxony, and different parts of Germany, Sweden, and Norway, and they abound in England as well as in the United States. They everywhere offer a matrix for anthracite. Geologists are not agreed as to the natural limit between these strata and those of a more recent order, generally designated under the name of secondary formation. But most authors consider the period of transition to cease beneath the Carboniferous rocks and the coal measures. While the different stratified rocks we have spoken of were in progress of formation, there were effusions of granite and other igneous rocks on their surface, and these geological convulsions have produced in the strata elevations and changes of direction, so that many of them are raised up and are very much inclined, and in some instances almost vertical. It was during one of these revolutions that the mountains of Westmoreland and Cornwall in England were suddenly elevated. A part of those of Brittany and Bigorre, etc., in France, of the Hunsrück, Eifel, and Harz in Germany, and many other mountain chains. The superior transition strata, which were formed subsequently to this convulsion and rested on the edge of strata thus upheaved, were in turn dislocated and raised up, and according to the observations of a French geologist, Élie de Beaumont, this elevation appears to have been anterior to the formation of more recent rocks than those we have yet mentioned, and to correspond with the eruption of masses of igneous rocks of the mountains of Vosges, known under the name of Buttons of Alsace and Comte. The elevation of the hills of Bocage in Calvados and several mountain chains in England, Germany, and Poland appears to have occurred about the same time. The following diagram represents the several strata we have described in a horizontal position, one lying above the other, and embraces the granite or plutonic rocks below. Next, the aqueous or metamorphic rocks, and above the whole, the transition formation consisting of the Cambrian, Silurian, and Devonian systems of strata. If we suppose the strata to have been in this position at the time of a geological convulsion, such as we have alluded to above, and that the granite should force its way upwards at A or B, we should find perhaps all the relations of the strata changed, presenting something like the arrangement represented in the following figure. The above figure represents the effect of the sudden rising up of a mass of granite, bursting and breaking through all the strata that were lying above it. Instead of a horizontal level surface, as in figure 27, we have a mountain of granite from the lowest stratum overtopping all the more recent formations, and the ends of the several strata, where they were broken to give passage to the granite, are brought up towards the Earth's surface, represented by the dotted line. In such a case as we here suppose, it would be very difficult for one who had not studied the subject to determine which stratum was first formed. It might seem to him that inasmuch as he finds the granite occupying the highest point and the transition rocks the lowest, that the granite is of the last or most modern formation. End of Lesson 2. Recording by Barbara Jade Siranen in the
Lesson 3, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Lesson 3, Part 1. Third geological epoch. Secondary formation, Carboniferous formation, Old Red Stone, fossils, Coal formation, fossils, extent of coal measures. Third geological epoch, secondary formation, Carboniferous formation. After the great revolutions which seem to have terminated the ancient period commonly designated as the transition epoch, the earth appears to have remained in a state of repose for a long time, which permitted new generations of organized beings to multiply on its surface, and mineral substances carried by the waters to be deposited in great layers, and to entomb in their substance the solid remains of the exuvia of contemporaneous animals and plants. The first deposits which took place during this geological epoch constituted the strata of sandstone conglomerate, an assemblage of fragments of rocks and pebbles cemented together by other mineral matter, clay, calcareous rocks, etc., and from their union resulted the formation called by geologists the Old Red Sandstone, on account of its antiquity and prevailing colour. But this state of things was soon changed, and there was formed, slowly and gradually, at the bottom of the waters, an immense stratum of calcareous rocks, 700 or 800 feet in thickness. Then the sandy sediment alternated with these limestones, and above this great formation, designated under the name of Carboniferous limestone, coal-bearing, numerous strata of sandstone, schistose clay, and coal were accumulated. The fossils of the Old Red Stone are somewhat numerous, and belong for the most part to marine animals, among which was a fish of strange form called Cephalaspis, from the Greek cephala, head, and aspis, shield or buckler, because its head resembles a kind of buckler. The remains of the genus Cephalapsus are found chiefly in the upper beds of the old red sandstone of Scotland, but also in Herefordshire and Wales. In this genus the head is very large in proportion to the body, and occupies nearly 1/3 of the entire length of the animal. Its outline is rounded and crescent-shaped, and the lateral horns slightly inclined towards each other, their points being nearer to one another than they are to the round part of the snout. The middle of the head is elevated and the sides dilated so as to overlap the body and extend considerably behind it. But perhaps the head only appears to extend so far, owing to accidents of displacement since the death of the animal. The eyes are placed in the middle of the shield, near to each other, and are directed straight upwards. It is imagined that the pointed horns of the crescent may have been useful as defences when the fish was attacked by the powerful cephalopods which inhabited the ocean at the period of its existence. The head and body are covered with scales of peculiar and varied shapes. Ansted. The Carboniferous limestone, also called mountain limestone and metalliferous limestone, affords several varieties of black, bluish grey, and variegated marbles, as well as ores of lead, copper, zinc, etc. It contains a great number of organic remains, such as divers, Polyperia, Cyathophila, Madrepora, etc., encrinites, which belong to the division of Crinoidea. It also contains the remains of a number of molluscs, as the Orthoceras lateralis, Goniotites, which resemble the nautilus, Bellerophons, which, with analogous forms, are not chambered, Euomphalus, Spiriphers, and Productus in great variety especially. The Crinoidea, from the Greek krinon, a lily, and eidos, resemblance, a family belonging to the class of radiate animals, are remarkable for the simplicity of their organisation and the peculiarly complicated structure of their skeleton. The animal resembled a true polyp or coral animalcule. The body consisted of a gelatinous tube, contracted at one extremity by which it was attached, and furnished at the opposite end with a variable number of delicate contractile filaments placed around the opening which represents the mouth. The calcareous skeleton was formed within the tube, and consisted of thousands of regularly shaped pieces kept together by the tough membrane which enclosed them during the life of the animal. The family is divided into genera according to the form of the stems, or according to its general shape. When the arms or stems are round, it is an encrinite. The Cyathocrinites, taken for its name from the Greek, kaiathos, a cup, and krinon, a lily. Many limestones are composed almost exclusively of the remains of species of Crinoidea, as at Lockport, New York, and various genera of this family are found in Alabama, near Huntsville. The Orthoceras, or orthoceratite, from the Greek orthos, straight, and keras, horn, is straight or slightly bent, cylindrical, slightly conical, many-chambered cell. The chambers are separated by plain septa, which are concave towards the larger end and pierced with siphuncle. Goniotites, from the Greek gonia, an angle, is a genus of extinct cephalopods which inhabited a chambered shell resembling that of the ammonites. Bellerophon, from the Greek Bellerophontes, the name of a fabulous hero, a genus of cephalopods which inhabited chambered shells similar to those of the Argonaut and Nautilus. The Euomphalus, from the Greek eu properly and omphalos the navel, was a gastropod mollusk. The shell is often exceedingly thick and is divided irregularly into a number of compartments or chambers, provided with a solid tube running through them, entirely shutting off that part of the shell in which the animal dwelt from the smaller and uninhabited portion. These empty spaces served, no doubt, as floats, rendering the whole mass of the shell and animal sufficiently light to move easily in the water and stead. At the period of the coal formation, the earth appears to have been occupied in a great part by a deep sea studded with islands covered by an abundant and luxuriant vegetation. The then existing plants differed very much from those now living. Hundreds of different species are known, but almost the whole of them belong to the class of vascular cryptogamia. They are principally ferns, equistaceae, lycopodiaceae, that is, plants of a very simple structure, but of gigantic size. The tree ferns, of which existing species do not exceed 20 or 25 feet in height, even in the torrent zone, and generally not more than 8 or 10 feet, then grew in localities far beyond the tropics, from 40 to 50 feet high, and other plants whose representatives of the present time are mere herbs, then rose to 60 feet in height. In that period there were also insects resembling weevils and neuroptera of the present day, scorpions, which differed from existing species in the number of their eyes, freshwater mollusks, and very remarkable fishes, which in certain respects resembled reptiles, and had their bodies covered by thick solid plates. The debris of the plants of that period, accumulated in immense masses and altered by time and other causes, were transformed into the combustible material which is so immensely valuable, known under the name of coal. The deposits of coal begin in France ordinarily with pudding stones formed of the debris of different rocks from the surrounding country, often comprising gigantic blocks scarcely rounded. Sometimes finer pudding stones alternate with sandstone, which always constitutes a chief part of the deposit. Very numerous varieties of these sandstones, arising from the size of the grains of quartz and the quantity of argillaceous matter entering into their composition, are found. They are frequently micaceous and schistose. They contain beds of clay slate and bituminous schist, which are sometimes very thick, but rarely calcareous strata. The masses of coal are scattered throughout, but are always separated from the sandstone by beds of slate. These are at first nearly pure, then mixed with the combustible, and finally are represented alone above the deposit. Besides the coal formed by the accumulation of the debris of the decomposed plants, the coal measures contain a great number of the remains of plants which retain their organic characters. The stems and trunks of trees are found in the sandstone. The leaves have left their imprints perfectly preserved in the schists and clays which accompany the coal. The impressions of ferns are extremely numerous. Among them is the Pocopterus, of which the leaflets, but little detached from the pedicle, are joined in a single leaf, deeply incised, in which we recognize a principal nervure from which the secondary nervures arise perpendicularly. The Spheronopterus, analogous to the preceding, but in which the leaflets are more distinct, deeply lobed, and have the nervures radiate almost from the base. The Neuropterus, which also has the leaflets detached, but entire and rounded, and the nervures arise very obliquely from the middle nervure, and afterwards frequently divide, and a great number of other genera founded on the form of their leaflets and the arrangement of their nervures. We also find various other plants, the families of which are uncertain, such as the Sphenophyllates, the Annularia, etc., which are very abundant in certain localities. True Equiseta appear to have existed in the coal measures, but we are also led to place in the same family certain stems, grooved lengthwise with joints at intervals from which branches sometimes spring. These stems, called calamites, are often found, like all the rest of those of which we speak, converted into argillaceous matter, which has become hard, or into carbonates of iron, but rarely into silicious matter. The external vegetable tissue is frequently found to have passed into a carbonous state. The Lycopodiaceae embrace various species of lepidodendrons, of which entire trees have been sometimes found upwards of 60 feet in height. Their trunks present rhomboidal projections, spirally arranged, which clearly exhibit near the top cicatrices of leaves. The Sigillariae seem to range themselves next to the Cicadiae. Their stems, flattened by pressure, are channelled lengthwise but not articulated, and the cicatrices are arranged in a longitudinal series. The stems, called stigmaria, are, according to Adolf Brongniart, probably only the roots of plants, the body of which is traversed by a ligneous axis surrounded by soft fleshy parts. The conifers, which, from the consistence of their wood, seem to have participated largely in the formation of carbonaceous matter in different strata, present us in the different coal measures, especially in the upper beds, species approximating to the Araucaria in their spirally arranged sessile leaves. M. Adolf Brongniart refers the whole of them to the genus Valkia of M. Sternberg. Animal remains are not very common in coal measures. Still, some are found, and even in great numbers in some localities. From the calcareous beds subordinate to these sandstones in the environs of Edinburgh, Dr. Hibbert has collected the remains of enormous sauroid fishes, the strong and longitudinally striated teeth of which, as well as the whole osseous system, remind us of the largest sized reptiles. The limestone in which they are found also contains particular concretions, which are considered to be the excrement of these animals, and on this account are called coprolites, from the Greek kopros, dung, and lithos, stone. The family of squalae was then represented by the division of cestrations, characterized by teeth adapted for grinding, and by that of the hybodons, with conoidal but not trenchant teeth, the enamel of which is plaited on both surfaces. The true sharks, with teeth flattened and trenchant on the edges, did not then exist, and did not appear until very much later in the Cretaceous formation. Other fishes are found in the coal basins of the continent of Europe, either in the bituminous schists, as at Saarbrück and Antun, or in kidney-shaped masses of carbonate of iron, as at Saint-Étienne. They belong to neighbouring genera of sturgeons, named by M. Agassiz Paleoniscus and Amblypterus, and seem to have lived in fresh water. Marine shells are rare in coal strata and are only found in the subordinate limestone of Belgium and England. But at the same time there were some species of Unio and some small entomostracans which indicate at least an afflux of fresh water to the sea at the points where these particular deposits were made. The extent of the coal measures. It is evident that the coal formation cannot be found except above the Cambrian, Silurian, and Devonian strata, which were formed anteriorly to or about the time of these deposits. If it existed before that period, it must be necessarily concealed by all the strata subsequently formed, and searches have been extended below them at great expense for this combustible. The consequence is that the coal formation occupies a small portion of the uncovered surface of the earth. All the deposits known in France do not occupy more than 1/200th part of the superficies of the territory. England and Belgium are comparatively richer, for in the first the surface of the coal formations is equal to 1/20th of the whole kingdom, and in the second to 1/24th. All the other states of Europe are much poorer, and some, Sweden, Norway, Russia, Italy, and Greece, are almost entirely without this valuable formation. Bohemia is the richest part of Germany in coal, though it does not produce largely. The northern part of the Spanish peninsula seems to contain considerable deposits of coal, and to participate in this respect in the wealth of Western Europe. The coal fields of the United States are numerous and extensive. Coal is found in Massachusetts, Rhode Island, Pennsylvania, Maryland, Virginia, Ohio, Kentucky, Tennessee, Illinois, Alabama, Mississippi, and Indiana. In a word, the coal formation in the United States is greater than in any country or kingdom on the face of the earth, and embraces every variety hitherto discovered. The different layers constituting the coal measures were deposited horizontally at the bottom of the basins they occupy, but they have not remained in this position. At certain places they were raised up, and at others lowered down, so that they became more or less oblique, and often seemed to be, as it were, folded on themselves. It is also remarked that frequently a certain extent of the mass formed by these layers has been separated from neighbouring parts by a sort of split or cleft, and elevated or depressed to a different level. Consequently, the beds of coal are suddenly interrupted at these points, and are found further on at a different height. These geological accidents are designated by miners under the name of faults. Speaking of the origin and nature of coal, Dr. Buckland remarks, "The most early stage to which we can carry back its origin was among the swamps and forests of the primeval earth, where it flourished in the form of gigantic calamites and stately lepidodendra and sigillaria. From their native bed these plants were transported into some adjacent lake or estuary or sea. Here they floated on the waters until they sank saturated to the bottom, and being buried in the detritus of adjacent lands became transferred to a new estate among the members of the mineral kingdom. A long interment followed, during which a course of chemical changes and new combinations of their vegetable elements converted them to the mineral condition of coal. By the elevating force of subterranean agency, these beds of coal have been uplifted from beneath the waters to a new position in the hills and mountains, where they are accessible to the industry of man. From this fourth stage, coal has been removed by the labours of the miner, assisted by the arts and sciences that have co-operated to produce the steam engine and the safety lamp. Returned once more to the light of day, and a second time committed to the waters, it has, by the aid of navigation, been conveyed to the scene of its next and most considerable change by fire, a change during which it becomes subservient to the most important wants and conveniences of man. In this seventh stage of its long and eventful history, it seems to the vulgar eye to undergo annihilation. Its elements are indeed released from the mineral combinations which they have maintained for ages, but their apparent destruction is only the commencement of a new succession of change and of activity. Set free from their long imprisonment, they return to their native atmosphere, from which they were absorbed by the primeval vegetation of the earth. Tomorrow they may contribute to the substance of timber in the trees of our existing forests, and having for a while resumed their place in the living vegetable kingdom, may ere long be applied a second time to the use and benefit of man. And when decay or fire shall once more consign them to the earth or to the atmosphere, the same elements will enter on some further department to their perpetual ministration in the economy of the material world. A part of this grand upturning of the coal formation has not disturbed the more recent strata by which it may be covered, and consequently it must have been effected at the close.
Lesson 3, Part 2 of Elements of Geology by W.S. W. Ruschenberger. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Barbara Jade Siranen. Lesson 3, Part 2. Fourth Geological Epoch. Secondary Formation continued. Saliferous Formation. New Red Sandstone. Poikilotic Variegated Group. The rich vegetation which adorned the surface of the earth during the coal period seems to have been entirely destroyed or converted into coal by the geological convulsion which separated this epoch from the succeeding period. This convulsion was followed by the formation of extensive deposits of more ancient rocks and sandy matters, as well as by the effusion of different rocks of igneous origin, such as porphyries. These deposits, which are indicative of great movements in the waters, constitute the formation designated by geologists under the names of red conglomerate, new red sandstone, Rotatote liegende, etc. Note: Rotatote liegende, German, red, dead, liar, so named because it is of a red color, underlies the metalliferous strata, and is dead or worthless as far as any metallic produce is concerned. End note. They frequently form layers 600 feet in thickness and contain scarcely any remains of organized beings. This lower new red sandstone, or Pennine Formation of the French, is very abundant in Thuringia. It contains very few organic remains. Above this red sandstone we find in some places bituminous schists, which are very remarkable, especially in Thuringia, for the ores of copper they contain, which circumstance has gained for them the name of Kupferschiefer, that is, copper slate. They contain plants which appear to belong to the family of algae, and a very small number of terrestrial plants, such as the conifers. Higher in the series come the compact limestones, the Zechstein, Mindstone of the Germans, separated into several layers by marls, then cellular and magnesian limestones, which are more or less friable, and again compact limestone and argillaceous matter. Such is the assemblage of strata in Thuringia and in different parts of Germany. But in England the whole series is replaced by the magnesian limestone. It was about this geological period that animals belonging to the class of reptiles were created. In this formation we find for the first time the remains of saurians in the bituminous schist and in the Zechstein, and subsequently in the magnesian limestone of England. These reptiles resemble the living genera of the iguana and monitor. We also find fishes of the genera Paleoniscus, from the Greek paleos, ancient, and oniskos, a kind of fish, and Amblypterus, from the Greek amblus, obtuse, and pteron, wing, similar to those of the coal measures, but they are not found in any formation subsequent to that we are now considering. The Paleoniscus is found in the magnesian limestone of England and the Kupferschiefer of Germany. The head is of a somewhat singular form, especially with regard to the anterior portion of the face, which forms a rounded projection above and before the upper jaw, occasioned by the swelling out and prolongation of some of the bones of the skull. The orbit of the eye is surrounded by a series of small, narrow bones, and the mouth is usually large, but the teeth so exceedingly small that it is rarely possible to distinguish them. The jaws, however, are powerful, and more especially the lower one, which is larger than the upper. The genus Platysomus, from the Greek platus, flat, and soma, body, which is found in the same strata, differs considerably from the Paleoniscus, as the body is of a trapezoidal form, is much raised, and nearly as high as it is long, while from the position of the scales on the edge of the back and on the belly, it appears to have been flattened. The head is large in proportion to the size of the body. The extremity of the snout forms a slightly rounded projection. The mouth is small and narrow. The jaws are armed with small but very pointed teeth. The lower jaw is shorter than the upper and broader in proportion, and the operculum, or bony scale covering the gills, is narrow and much elevated. The whole body is covered with large scales. One of the most remarkable peculiarities in the structure of this fish is that although the body is flat, short, and elevated like that of the recent flatfish, the tail, instead of being as in the latter, much forked and equally lobed, arrangements which appear in the present state of things to be indispensable, retains in the Platysomus the heterocircle character, the upper portion having the vertebral column continued into it, and being much longer and more powerful than the lower portion, which rather resembles a small accessory fin. M. Agassiz classifies fishes according to the form of their scales. All those fishes with angular scales, regularly arranged, and entirely covering the skin, constitute the order of Ganoidians, from the Greek ganos, splendor. The order of Placoidians, from the Greek plax, a broad plate, contains fishes whose skin is covered irregularly with plates of enamel, often of considerable dimensions, but sometimes reduced to small points, like the shagreen on the skin of the shark and the prickly tubercles of the ray. The order of ctenoideans, from the Greek dis, in the genitive stenos, a comb, is characterized by horny or bony scales, jagged like the teeth of a comb on the outer edge. The perch and many other existing genera are of this order, which contains but few fossil forms. The order of cyclodians, from the Greek kuklos, a circle, is characterized by having scales which are smooth and simple at the margin, as in the herring, salmon, etc. When the vertebral column is prolonged into the caudal fin, the tail is heterocercal. When the vertebral column terminates where the tail is given off, we have the homocercal tail, as in most of the recent fishes. In this same formation, we also find spirifers and productus, and especially the Productus aculeatus, which, under the name of Graphites aculeatus, has been regarded as characteristic of it in Germany, and sometimes in consequence the Zechstein is called Greifitenkopf, which on this account has been confounded with the lias. Other mollusks, as well as the remains of encrinites, which seem to be the same as those of the Carboniferous limestone, are also found. Next in order is a layer known as the sandstone of Vosges, which lies either on the red sandstone or magnesian limestone, or, when these strata are wanting, on some other more ancient rock. After the formation of the several portions of the crust of the globe just mentioned, geological convulsions again occurred, and, as it appears, the mountains of Vosges, the Black Forest, etc., were elevated about the same time. After this movement, new deposits were formed around the base of the hills, constituting the Trias system of French and German geologists, so named because it is composed of three kinds of rocks. The Trias or Triassic system, or Upper New Red Sandstone of the English, consists of 1. Bunter Sandstein, Grèce-Bigar of the French, a quartzose sandy deposit, which usually forms the base of the system both in France and Germany. 2. Muschelkalk, shell chalk, a well-marked and highly fossiliferous limestone, rarely absent in the continental series, but never found in England. 3. Keuper, a singular group of sandy marls of variegated colors, frequently containing salt and gypsum, and remarkable for numerous fossil vegetable remains. The Bunter Sandstein, or Grèce-Bigar, is a fine-grained, solid sandstone, sometimes white, but more frequently of a red, blue, or greenish tint. The structure of the lower part is tolerably close-grained and sufficiently compact to form a good building stone, but the uppermost strata are fissile and incoherent and pass into an earthy clay containing gypsum, plaster of Paris. The intermediate portion is compact, like the lower, but its structure is that of a conglomerate and is used for making millstones. In many districts, the Bunter Sandstein contains numerous remains of fossil plants and marine shells, but the latter are rare and confined to particular localities. In this series are found footprints, some of which evidently belonged to birds, and others, according to the opinion of certain naturalists, belonged to marsupial mammals or gigantic batrachian reptiles. The sandstones and marls of this part of the series are spread over an extensive tract of land in Western Europe, more particularly in France, and in southwestern and central Germany. On the right bank of the Rhine in Swabia, there are some districts in which the Bunter Sandstein rests immediately on the Rotatote Liegende, the lower new red sandstone, Vosges sandstone, being absent, and no other representative of the magnesian limestone taking its place. The Muschelkalk, also called Conchilian limestone, shell limestone, is a compact limestone of a gray or greenish-gray color and commonly contains in great abundance the remains of shells and fragments of radiated animals and fishes. Sometimes the Muschelkalk is a bituminous rock and emits a fetid, disagreeable odor when rubbed or struck with a hammer. Among the characteristic shells are the Ammonites nodosus, Avicula socialis, Posidonia minuta. In this stratum, the Trigonia is first met with, and species of it are found extending through various subsequently formed strata to the chalk. A great many Engranites are also found, especially the species Maniliformis. The Ammonites, or Cornua ammonis, so called from a supposed resemblance to the horns engraven on the heads of Jupiter Ammon, are among the most common and well-known fossils. Local legends ascribing their origin to swarms of snakes turned into stone by the prayers of some patron saint are still extant in certain parts of England, and perpetuated by the name of snake stones, by which these fossils are provincially known. Several hundred species have been described. They are divided into genera, which are characterized by essential modifications in the direction of the spire and the inflections of the septa. The shell of the ammonite is generally thinner and more delicate than that of the nautilus, to which it bears considerable resemblance, and in some species it resembles the flexible covering of the argonaut. Possibly, in these species, the animal, like the recent paper nautilus, may have possessed a pair of arms terminating in broad membranous expansions, which secreted the shell and generally remained in contact with it. Otherwise, it is difficult to explain how such delicate fabrics should have been uninjured. The living and extinct species of testaceous cephalopods, are all connected by one plan of organization, each forming a link in the common chain which unites the existing species with those that prevailed among the earliest conditions of life upon our globe, and all attesting the identity of the design that has effected so many similar ends through such a variety of instruments, the principle of whose construction is, in every species, fundamentally the same. Throughout the various living and extinct genera of these beings, the use of the air chambers and siphon of their shells to adjust the specific gravity of the animals in rising and sinking appears to have been identical. The addition of a new transverse plate within the coiled shell added a new air chamber, larger than the preceding one, to counterbalance the increase of weight that attended the growth of the shell and body of these animals." Buckland. The occurrence of the nautilus and its congeners among the earliest traces of the animal kingdom, and their continuance throughout the immense periods during which the family of ammonites was created, flourished and became extinct, and the existence of species of the same genus at the present time, are facts too remarkable to have escaped notice. To these facts Mrs. Howitt alludes in the following lines to the nautilus. "Thou didst laugh at sun and breeze in the new created seas. Thou wast with the reptile broods in the old sea solitudes, sailing in the new made light with the curled up ammonite. Thou survivest the awful shock which turned the ocean bed to rock, and changed its myriad living swarms to the marble's veined forms." See Mantell's Metals of Creation. The genus Avicula belongs to the division of bivalve shells, and the fossil species, a great many of which are known, resemble the pearl oyster, Avicula margaritifera. The genus Posidonia, from the Greek Poseidon, Neptune, also belongs to the bivalves, and is found in the lower part of the Carboniferous series. The genus Trigonia, from the Greek trigonos, three-cornered, belongs to the family of Ostracea. The only living species known inhabits the seas of New Holland. The Encrinites, from the Greek krinon, a lily, belong to the family of echinoderms. The skeleton of this animal is said to consist of not less than 26,000 separate pieces. The body of the lily encrinite was supported on a long and nearly cylindrical column attached to a rock or some hard substance at the bottom of the sea by an enlargement of its base. This column was made up of a vast number of joints, through which was an aperture descending from the stomach of the animal to the base of the column. The Cupa, a German word, is the name given to the uppermost division of the Triassic system and is often applied to the upper part of the New Red Sandstone Formation. This group usually consists of a numerous series of mottled marls of a red, greenish-gray, or blue color, which pass into green marls, black slaty clays, and fine-grained sandstones. Throughout the series, common rock salt and gypsum are abundant, but the organic remains of animals are extremely rare. Of plants, however, a considerable number are preserved in some localities, and these indicate a wide departure from the Carboniferous period, and, as well as the shells, seem to possess more analogies with the forms of life determined from the fossils of the Secondary period than with those common in Paleozoic rocks. Besides peculiar species of ferns, the Trias presents us with fossil plants not previously met with. In the sandstone are particular species of conifers which constitute the genus Voltsia, and in the limestone remains of Cycadae of the genus Mantelia. This last family is very abundant in the Cupa, in which are found the genus Nilsonia and the genus Pterophyllum. Several species of large saurian reptiles are also found in the Trias group of rocks. Fifth geological epoch, Lias or Liassic system, Jurassic formation, Oolitic system. Secondary formation continued. Up to this period of its geological history, we have seen the earth was inhabited only by plants, some inferior animals such as zoophytes, mollusks, and fishes, and lastly, by some reptiles. During the period at which we have now arrived, this state of things changed, and there was created a new fauna composed of most remarkable animals, characterized especially by a multitude of reptiles of strange form and gigantic size. The formation of the lias, so called from a barbarous provincial word supposed to be a corruption of layers, and to allude to the riband-like appearance of the rock when seen in section, the lias consists of strata in which an argillaceous character predominates throughout, but which are also remarkable for a quantity of calcareous matter mingled with the clay and forming occasional bands of argillaceous limestone. A few beds of sandstone also alternate with the clay and marl, and are sometimes mixed with the latter, forming a marly sandstone of a white or greenish color. The inferior layers of the Liassic system are characterized, according to M. Lemery, by the presence of the Pecten lugdunensis and different species of Echinidae of the division Diadema. The middle layers, or the lias proper, are distinguished especially by the presence of the Gryphia arcuata and the ammonite named after Dr. Buckland, the spirifer of Walcott, the last of the race, the giant Plagiostoma, and the spinous Plicatula. The superior part of the lias contains a great number of belemnites, the ammonite named after Walcott, and an avicula with unequal valves, etc. We also find in this group various species of trigonia, which appear to have existed in all parts of the deposit, but the species, which perhaps furnish very important characteristics, have not yet been studied sufficiently in relation to the grouping. They extend through the oolitic series to the chalk formation. We find, too, in the lias for the first time, in ascending through the crust of the earth, those singular saurians whose skeleton at the same time reminds us of lizards, crocodiles, fishes, and mammals. Their feet, which are in form of paddles, show they were aquatic in their habits. Such are the ichthyosaurus, some of which were 25 feet in length, the plesiosaurus, some species of which are nearly 15 feet long. The ichthyosaurus, from the Greek ichthus, a fish, and sauros, a lizard, fish-lizard, must have resembled some huge fish having an exceedingly large head and very powerful tail. The spine consisted of 120 vertebrae or joints, besides those of the neck, which were united into a mass of solid bone. The eye was an extremely powerful organ, "capable of adapting itself," says Dr. Buckland, "to great changes of distance and great alterations in the amount of light in which it could be used, giving to its possessor the power of discerning a far distant object as well as one near at hand, and of pursuing its prey in the darkness of night or the dim obscurity of the depths of the ocean, as well as in the daytime or on land." This animal had a wrinkled skin like the whale, without scales. The plesiosaurus, from the Greek plesion, near, and sauros, a lizard or reptile, resembling a reptile, may be described as exhibiting the head of a lizard attached to a neck whose length was 3, or in some species even more than 4 times that of the head. The body appended to this head and neck was comparatively small and fish-like. The extremities were large paddles, and the tail like that of the crocodile. The neck consisted of upwards of 30 vertebrae or joints, and was very long and flexible. We also find, for the first time in the Liasic group, the pterodactylus, from the Greek pteron, wing, and dactylos, finger, a flying saurian, whose head and neck gave it the semblance of a bird, and its tail was like that of a mammal, while its extremities were analogous to those of a bat. It was capable of walking and flying, and perhaps of climbing steep rocks in pursuit of food. With the remains of these singular animals are found, in the lias of Lyme Regis on the coast of Dorset, England, an immense quantity of coprolites, from the Greek kopros, dung, and lithos, stone, which probably belonged to them. Sometimes their intestines are found in their skeletons, and we also find in these the remains of fishes and other reptiles, clearly showing how the aquatic species were nourished. The remains of insects are found with those of the pterodactyli at Zollenhofen in Franconia, also showing what was the food of these animals. Saurians resembling crocodiles were much less abundant in this epoch, although we find in the lias remains which prove their existence. The megalosaurus, from the Greek megas, great, and sauros, reptile, partook of the nature of the crocodile and monitor, and must have been from 50 to 60 feet in length. Ink bags of considerable size, analogous to those of the cuttlefish, are also found. In the lias of Lyme Regis, the dorsal bones of the calmar are also met with other traces of this genus, as well as of belemnites. The ink, or sepia, which may be obtained from these fossils, is as good as that prepared from the recent cuttlefish, and has been used. The Jurassic, or oolitic system. Oolite, from the Greek on, an egg, and lithos, a stone, is a granular variety of carbonate of lime, frequently called rowstone, from its resemblance to a fish roe or egg bag. The frequency of the occurrence of this particular form of limestone in a great series of deposits has caused the name of oolitic to be applied to the whole series. The oolitic or Jurassic deposits, the Jurakalk of German geologists, are divided into several groups which are distinguishable from each other by their relative position in the scale of elevation, but more particularly by the fossils found in them. The remains which are characteristic of the preceding groups are not met with in this. The oolite is divided into the lower, middle, and upper oolites. The lower oolite, the first in the series of oolitic deposits, consists at first of layers of marl intermixed with sand, then layers of ferruginous oolites and strata of compact limestone and clays, more or less pure and fitted for the purposes of the fuller, and hence named Fuller's earth. The first of these marly deposits joins with the marls of the lias, but is characterized by a new species of graphia, which is not found in the preceding layers. Above these deposits are found fissile marls, limestone, with ferruginous oolite, to which succeed earthy deposits, the great oolite, which consists of a variable series of coarse shelly limestone, locally called rag, alternating with beds of fine, soft freestone, devoid of fossils, and admirably adapted for building purposes. Above these again come marls, sands, clays, and limestones, some of which are full of shells. They are known under the names of Bradford clay, forest marble, and cornbrash. In spite of the number of fossils, often broken and in the state of molds, found in this group, it is difficult to designate those which are certainly characteristic of it. To the graphia cymbium, which is characteristic of the first group of the oolitic deposit, and forming, as it were, a new geognostic horizon, we may add the Ostrea acuminata, which is found in the upper marls, or limestones sometimes met with in their place. Different species of terebratula, which seem to belong more particularly to the lower oolite, as well as a small globose species of ammonites. In the limestones proper, different species of ammonites are found, various species of pleurotomaria, which seem to be characteristic, and a great number of shells of diverse kinds are met with. Encrinites, frequently very numerous, which are chiefly referred to the pyriform species, Apiocrinites, are sometimes found on the very spot where they lived, attached to the solid materials forming the bottom of the sea of that epoch, and covered by successive deposits of the earthy matter of which it was constituted. An important fact is connected with the marls and fissile limestones which form the first of the oolite system. The first or most ancient fossil mammals were discovered in Stonefield slates. These small animals, the lower jaw of one of which is represented, belong to the marsupials, that is, one of the most imperfect orders of the class. Bones of large animals, thought to belong to the order of Cetacea, are also found in the oolitic strata. Conifers, which are but rarely found beyond the shell limestones, are abundantly met with in the oolite series of particular genera, with cycadee, ferns of different species differing from all those met in more ancient strata, and finally a true equisetum. Middle oolite. This group, which is less complicated than the preceding, at the lowest part consists of clay called Oxford clay, with layers of calcareous grit and stratoid masses of limestone. Above these are found sands and limestones which are more or less oolitic and often ferruginous. In this group we find deposits of oolitic iron which had already appeared in the preceding series. It is very rich in fossils, particularly ammonites, and the Ananchides bicordatus is very common. Ananchides is a genus of the family of Echinidia or sea urchins, sometimes vulgarly called sea eggs. The family contains 13 genera, which are distinguished from each other by the form and size of the ambulacra, alleys, the narrow longitudinal portions of the shell of the echinus or sea urchin, which are perforated with a number of small orifices, giving passage to tentacular suckers, and alternate with the broad tuberculate spine-bearing portions, and also by the position of the vent and of the mouth. Figure 70 exhibits the ambulacra between the tubercles to which the spines are attached in living species. What especially characterizes the Oxford clays is the presence, often in abundance, of a new species of Graphia, the Austria marshii, which already commenced in the preceding group, a great number of different Terebratula, among which we find in the upper part of the series the Terebratula thermani and the Terebratula impressa. The molds of these shells are frequently siliceous, and we find in the upper layers beds of siliceous balls of loose texture, sometimes enclosing siliceous molds of shells. The upper group of the middle oolite, called coral oolite, consists almost entirely of limestone. It is divided into different thick layers, which are distinguishable from each other by their structure. The first or lowest layers are ordinarily compact, grayish or yellowish, filled with polyparia or corals of a saccharoid structure, or those which have passed to the siliceous state. This constitutes the coral rag of English geologists. Some of the succeeding layers are oolitic, frequently of large irregular grains mingled with fragments of rolled shells. Others are compact, passing into chalk or even marl of greater or less solidity. The numerous polyparia contained in this group present to us Caryophylla, Astrea, Meandrina, madrepores of a great number of species, resembling more or less those of coral reefs, and a great many other genera. Among the shells, ammonites are less common, but above the oolite, where all the organic remains are broken, the lowest layers contain a great quantity of various shells, among which are Nerinia. The superior strata contain a great quantity of Astartes, the most characteristic of which is the Astarte minima. Among other shells, we may cite the Diceras aretina, and among the echinoderms, the Sideris coronata. Upper oolite. This group is divided into Kimmeridge clay and Portland oolite. Kimmeridge clay, so named because it is well exhibited at Kimmeridge Bay and near the village of the same name, in the Isle of Purbeck, is of a blue, slaty, or grayish-yellow color. Above this is the Portland stone, which, with alternations of compact, marly, sandy, or oolitic limestones, terminates the Jurassic or oolitic system. The organic remains which characterize this group are of the genera Austria and Exogyra of particular species, sometimes in great abundance. With a few ammonites, we also find Maya, Phalandomaya, and Terebratula, which are also equally characteristic. Certain beds of this formation contain Paludinae or helices, consequently indicating that streams of fresh water emptied into the seas of that period. The lithographic stone of Zollenhofen in Bavaria is referred to the upper strata of the Jurassic system. In it are found an immense quantity of fossils, reptiles particularly, pterodactyls, fishes, insects, plants, etc. In some parts of Upper Oolite are beds of a highly bituminous shale, locally known as Kimmeridge coal. In the latest calcareous beds of the Portland group are found Cicadiae. The Oolitic or Jurassic system of rocks is met with in England and on the continent of Europe, but is not represented in North America, where the transition from the new red sandstone to the green sand and other rocks of the Cretaceous period is abrupt. No rock answering to the lias has yet been discovered in the United States. End of Lesson 3, Part 2. Reading by Barbara J. Zierman from the Northwoods of Wisconsin.
Lesson 4 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Thomas Bosk. Elements of Geology by William Ruschenberger. Lesson 4. Secondary Formation, 6th Geological Epoch. Cretaceous Formation. Secondary Formation continued. Next in order above the Jurassic system we find, in discordant stratification, immense Cretaceous deposits in a great many localities. These deposits may be divided into several others, according to their discordance of stratification observed in some of their divisions. The Cretaceous Formation, from the Latin creta, chalk, may be divided into the upper and lower chalk. The lower, or inferior Cretaceous system. Neocomian of the French, the Shanklin, or lower green sand of the English. The first deposits formed above the oolite are composed of marls, then a yellowish limestone, characterized by great numbers of genus Spatangus, with a multitude of the remains of shells and polyparia of different genera. This limestone is sometimes in continuous layers of considerable thickness, sometimes only in masses agglutinated to each other by mud and sand. Sometimes it is entirely wanting. Above it are clays which contain, often in great quantity, exogyra and oysters, among which is distinguished the great species named Ostrea leimeri. The Lima elegans is also found. Among these clays are met large calcareous masses, a good deal flattened, filled with the same fossil shells, presenting lumicella or conchilians, which have been confounded with the Portland group, formed by an accumulation of the exogyra virgula. Footnote: Lumicella, an Italian word, formed from limacea, a snail, which is derived from the Latin limax. The word is used to designate a mass formed of the remains of snails, etc., with their nacre, united by gluten. It is also called conchilian marble. End footnote. Next we have, at least in parts of France, sands and clays, sometimes variegated in colors, among which are masses of iron ore, commonly oolitic. The remains of shells seem to give place here to ferruginous masses. These last deposits seem to be wanting in other localities, in which we find, instead, great layers of limestone, more or less compact, sometimes white, sometimes colored, which enclose hipporites, spherulites, and even nummulites, which have been long regarded as belonging to the Tertiary Formation. We also find here a fossil which is very characteristic. It was at first compared to the Diceras, but is now called Chama ammonia. This species of shell, which is often very abundant, is always so embedded in the mass of rock, where it is distinguished by the sinuosities it forms, that it is very difficult to detach it entire. Various species of ammonites, gigantic hamites, several species of crioceratites, from the Greek krios, a ram, and keros, horn, and belemnites. The trigonae, which are still met with and continued to the green sand, present here new species, which seem to be characteristic. In the south of France and in the Pyrenees, The chalk formation possesses peculiar characters, both in relation to the organic remains contained in it, as well as its mineralogical relations. We there find a great many shells, very remarkable for their form and peculiar structure, which are called hippurites and spherulites. Many nummulites, of which some deposits are formed exclusively, are also met with. It is not determined precisely to what part of the lower chalk these deposits should be referred, but they seem to represent a part of the Neocomian or Shanklin formation. In the Pyrenees, the layers are often of a deep color, and separated by argillaceous schists, which seems to make them a part of the transition formation, but on the contrary, in the north part of the basin of the Gironde, they belong to the chalk. The Neocomian, which was not at first distinguished from other parts of the chalk formation, is now recognized in a great part of France, Switzerland, and different parts of Germany, Poland, and even to the Crimea. Here and there deposits of gypsum of greater or less extent are met with, sometimes isolated, and sometimes associated with crystalline rocks. The Weldon deposit. We frequently meet in the first deposits of the chalk formation the remains of organized bodies, which appear to belong to paludinae, clearly showing there is here and there an afflux of fresh water to those seas in which these remains accumulated. We also find in the same situations deposits of combustibles, which have always been known under the name of lignite, from the Latin lignum, wood, probably formed from conifers, as dicotyledons did not then exist, which were doubtlessly carried by rivers. Such are those in the environs of Orthez, in the department of Landes, of Balesta and of Saint-Giron in the department of Ariège, of Irun in Guipuscoa, Spain, etc. But all these local deposits are nothing compared to those which have long been described in England, in parts of the counties of Kent, Surrey, and Sussex, under the name of welds, from which is derived the term Weldon formation. This formation is composed of alternate layers of limestone, sand, more or less ferruginous, and clay, the deposits of which are sometimes extremely thick. There are entire beds of limestone composed of paludinae, constituting what is named Purbeck limestone. The laminae of argillaceous matter are often covered by cyclades and anodontae, and we find disseminated a great number of small cypress. There are many species of fresh-water fishes, the remains of fluviatile tortoises, mingled with marine and terrestrial saurians, among which is the monstrous iguanodon, which must have been 30 feet in length, to judge from the size of its bones. In this formation are found also, in the dirt of the Isle of Portland, the silicified stems of cycadiae, standing erect in the midst of the earth, of which the deposit consists. Various species of conifers, Equisetaceae, and ferns are also met. The remains of birds of the order of Gralliae, waders, also exist, but no mammals, although we have seen them in the marls of the oolite. It is believed that the clays in the environs of Boulogne, which seem to be continuous with those of England on the southern side of the Channel, may be referred to the Weldon deposit, as well as those of Forges and of Savigny in the country of Bray, where paludine limestones like those of Purbeck have been found. It is very certain, according to the observations of M. Lemery, these deposits are connected with those in the department of Aube, and form part of the superior Neocomian clays. If there are indications of freshwater deposits, they prove the connection between the Weldon formations and those of this epoch. According to English geologists, the Weldon formation is below the Neocomian, and is, consequently, older and not precisely contemporaneous with it. Above the Neocomian and Weldon formations, there is a group of deposits generally termed green sand, consisting of two arenaceous beds, with a parting of clay called gault. The green sand formation receives its name from the prevalence of small green particles of silicate of iron distributed through the sand. It is found in New Jersey. In England, it is divided into lower green sand, gault, and upper green sand. This group consists of white and yellowish sands, which are frequently ferruginous, containing masses of limestone, clays, and sandstones of more or less compactness. It also comprises the quadersandstein and planer kalk of German geologists. Gault is a stiff clay of a blue color, and the inferior portion of it in England abounds in iron pyrites, while the upper part contains green particles of the silicate of iron. Various nodules and concretions are found throughout, which are sometimes fossiliferous, but more frequently obscure and of doubtful origin. Gault is a provincial term, used originally in the middle of England to designate the brick clay, which there belongs to the Cretaceous system. Above the green sand formation, the calcareous part becomes more abundant. At first it is mixed with sandstone, and then, little by little, becomes isolated, and now contains only green particles of silicate of iron, which from being at first very abundant, gradually disappear. This is the chloritic chalk, which is sometimes friable, and at others solid. The green particles having totally disappeared, the limestone is found alone, sometimes in form of pure chalk, of more or less solidity, and occasionally becomes very compact. Here we have argillaceous or arenaceous limestone, and finally sands, or nearly pure sandstone. From these result the chalk marl, or representatives of it. Organic remains are very abundant in these deposits, and in species, and even in genera, are very distinct from those of the preceding formations. Immediately above the Wealden is a marly bed, characterized by the presence of a species of Exagera, 5 or 6 inches in diameter, not known in the Neocomian. According to M. Leymarie, the nucula pectinata is a characteristic shell of the gault or blue marl. Belonging to the green sand formation, generally the characteristic shells are the Inoceramus concentricus, the Plicatula placunea, several species of ammonites, and particularly the ammonites monilae, which are quite characteristic. We find in the chalk marl the baculites and turrilites, different species of the first of which are found in the highest part of the chalk formation. To these may be added the scaphites, some particular species of ammonites, the Exagera columba, the Ostrea carinata, the Terebratula octoplicata, which continue in the chalk. Nucula, from the Latin nux, a nut, is an inequilateral bivalve shell. The hinge is narrow, and has many teeth like those of a comb. Several species are known. Scaphites, from the Greek scaphe, a boat, is an elliptical, many-chambered shell, somewhat resembling the ammonites. Baculites, from the Latin baculum, a stick, is a multilocular, straight or slightly bent, and slightly conical shell. The chambers are separated by septa, pierced by a marginal siphuncle. Turrilites is a spiral, turriculated, multilocular shell. The chambers are separated by winding septa, which have the siphuncle in their discs. The aperture is round. This fossil must not be confounded with the turritella, which is a univalve, found both recent and fossil. The upper chalk formation. In this we find chalk with and without flints. The layers of flint are frequently almost the only indications of stratification afforded by the mass. It is frequently soft and susceptible of solution or suspension, as in Spanish whiting, which contains an immense quantity of microscopic shells, belonging to the group of foraminifera. In some cases it is arenaceous and sometimes very compact. Although often white, we find it in some places colored gray, yellow, red, etc. Sometimes it is oolitic in character, and becomes almost crystalline, even magnesian, and in localities remote from crystalline materials which might affect it. The inferior part of this formation is frequently soiled with clays, chalk marl. Above it is more pure, and contains a great many nodules of flint or silex. Though this character is very common, it is wanting in a great many places. At its upper part, the chalk formation becomes very sandy, as in the neighborhood of Maastricht. Excepting the baculites found at Maastricht, the remains of cephalopods are not found in the Upper Cretaceous formation, but belemnites, from the Greek belemnon, a dart, of particular species, and many other organic remains not met within the chalk marl are found. Among them are the Plagiostroma spinosum, the Ostrea vesicularis, the Catulus cuvieri, the structure of which is fibrous, the Terebracula defranci, the Ananchitis ovatus, the Spatangus corynguinum. In the upper part of these deposits we find, among many other fossils, an enormous saurian, called the Mosasaurus, from the name of the river, Moose, and the Greek saurus, lizard. Originally found on the banks of the Moose, in the celebrated quarries of St. Peter's Mount, near Maastricht. Organic remains of a Mosasaurus have been found in New Jersey. The Mosasaurus is a genus determined from a fossil discovered upwards of 60 years ago, and which at that time was extremely puzzling to naturalists. Its true place in the animal kingdom is now known to be among the Lacertian saurians, but the animal appears to have been perfectly marine in its habits. The head, the only part at first discovered, measured 4 feet in length, and is preserved in the museum at Paris. Other parts have also been found from time to time in the Maastricht quarries, and some fragments in the chalk of the south of England, Ansted. The whole length of the animal was probably not less than 24 feet, a magnitude which must be compared with that of the lizards of the present day, and not with the crocodilians, whose structure is totally different. We also find in the chalk formation Cretaceous mammals, which are classed among the lamantins and dolphins. The Cretaceous group prevails extensively in England and on the continent of Europe. True white chalk exists not only in England, but also in France, in Denmark, in Poland, in central Russia, and in the Caucasus. Semi-crystalline rocks of the Cretaceous epoch also exist in the central plains of Asia Minor. Beds of the Cretaceous period are found in New Jersey and other parts of the United States, but they rest on the oldest secondary rocks, without the intervention of the oolite. The formation is extremely calcareous, in places chiefly arenaceous, but no true chalk has yet been discovered in America, nor has oolite been found. Fossils, apparently Cretaceous, have been recently obtained from southeastern India. This brings us up to the close of the secondary formation. As far as we have studied our subject, we find the earth's crust to consist of a series of formations, as represented in the following diagram. The study of Cretaceous rocks brings us, as it were, to the termination of that period in the history of the earth's structure to which the character of antiquity belongs. In the succeeding period,
Lesson 5, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Lesson 5, Part 1. Seventh Geological Epoch. Tertiary Formation. Ordinarily, geologists designate under the collective name of secondary formation the long series of systems of rocks commencing above the transition formation with old red sandstone and coal and terminating above with the chalk, and they give the name of tertiary formation to those strata which are more recent than the chalk, and consequently superior to it, but still more ancient than the strata of the present or modern epoch. During that period, the seas were very much less extensive than they were in the more remote geological ages, and consequently the sedimentary deposits formed in those waters are of less extent and more isolated. Moreover, their formation was effected at different points of the globe and at different periods, and to follow their history in chronological order, it is necessary to subdivide them into three groups. At that period, contemporaneous with the deposit of each one of these series of formations, there existed particular species of organized creatures, mingled with other species like the preceding or succeeding periods. But the fauna of all the divisions of this period possess certain common characters, and among the most remarkable of these is the existence of a great number of mammals. The Tertiary formation is divided into the older, middle, and newer Tertiary groups, which have been conveniently designated by Mr. Lyell under the names of Eocene, Miocene, and Pliocene. The first, Eocene, from the Greek eos, dawn, and kainos, recent, designates the older Tertiary strata in which there appears, as it were, the first dawn of existing species. The second, Miocene, from the Greek maion, less, and kainos, recent, is applied to the middle Tertiary strata because in them we find more recent species than in the preceding group, but still fewer recent than extinct species. The third, Pliocene, from the Greek plion, more, and kainos, recent, is given to the newer Tertiary beds because there is always a greater number of recent than of extinct species found in them. The Eocene or older Tertiaries. The beds thus designated are a very variable series, consisting in England and Belgium of stiff clays alternating with sand, and resting on coarse sand and gravel, and in Paris of a number of limestones and marls, alternating with gypsum and silicious strata. They are deposited in basin-shaped depressions in the older rocks, and in England some portion of them has been so greatly disturbed that the beds are actually vertical. The older Tertiaries of England are chiefly confined to three masses, contained in trough-shaped basins, called respectively the London, the Hampshire, and Isle of Wight basins. A stiff clay predominates in them, and from being very abundant near London is known as the London clay. The London clay often, but not always, rests on a series of sandy and gravelly beds, enclosing bands of potter's clay, to which the name of plastic clay has been given. The greatest development of Eocene strata in the United States occurs in Virginia, North and South Carolina, Georgia, and Alabama. In Virginia, these beds consist of greenish sands, nearly identical in appearance with a portion of the Cretaceous series, and of the same mineral composition. And a little further to the south, a continuous formation of white limestone, Santee limestone, occurs, which is of no great thickness, and which varies in hardness, and is composed of comminuted shells, but so closely resembling certain Cretaceous beds of the Secondary period in New Jersey as to have been frequently mistaken for them. But this resemblance does not extend to the fossil contents of the beds, which are in many instances analogous, or the same as those of the Eocene formations in other parts of the world. The geological position of the city of Paris resembles that of London, each being situated upon an extensive and important group of Tertiary strata, which occupies a depression or basin in the underlying chalk. The nature of the two deposits is, however, totally different, the deposit being characterized in England by great accumulations of argillaceous matter, which form the London clay, while in the neighborhood of Paris there is a varied series of limestones and marls, alternating with important beds of gypsum and silicious matter. The depression in the chalk forming the celebrated Paris basin, so frequently named by geologists, which is filled up by these strata, is nearly 180 miles in its greatest length, and about half that in breadth. The surface of the chalk is usually covered by broken and rolled flints, often cemented by a silicious sand into a kind of breccia, and these flints seem to mark the action of the sea upon reefs of chalk before the commencement of the Tertiary epoch. The order of stratification of the Paris basin is represented in the following table. At the bottom, chalk. Above the chalk, plastic clay. Above the plastic clay, calcaire grossier or marine limestone and calcaire siliceux or freshwater limestone. Above this, gypsum and green marls, and at the top, upper freshwater sands and upper marine sands. Above the chalk we find first deposits of plastic clay, so called because varieties of it are well suited for the manufacture of pottery. In the neighborhood of Montereau on one side, between Udine and Dreux on the other, it is remarkable for its whiteness and purity, and is used in the fabrication of the finest porcelain. Around Paris it is colored and impure, and suitable only for coarse pottery. These clays contain lignite, in which we see, perhaps for the first time, mingled with numerous conifers, phanerogamous monocotyledons, true palms, and some dicotyledons. Marine as well as freshwater shells are found in its upper part. Above the plastic clay we find thick deposits of marine limestones, more or less arenaceous in structure, the different beds of which may be easily distinguished by their characters. These limestones contain a prodigious quantity of meliolites, extremely small shells, the most of which do not attain 0.03937 of an inch in size, and yet they constitute a great number of genera. These serve, in a manner, as paste to an immense number of shells of different genera, which are more analogous to creatures now living than any we have hitherto mentioned. 3% of them are even identical with species now existing in the neighboring seas. The Cerithia are here so abundant that the formation is sometimes known by the name of Cerithia limestone, although these same fossils are found in many other deposits. There are certain species which are characteristic. That is, they are always found wherever these deposits exist. Such, for example, is the Cerithium giganteum, sometimes 27 inches in length, the extremity of which is almost always worn or broken by the friction and knocks occasioned by the movement of the animal. Among other shells, of which there are a great many species, it is difficult to name any which are absolutely characteristic. Among the most common are the Turritella imbricateria, the Ampullaria acuta, the Terebellum fusiforme, the Mitra scabra, the Crassatella sulcata, the Cardium porulosum. With these species are found a great many others, which have been described and figured in a great many books on the environs of Paris. There are species which are much more common than those named, but some of them are not found everywhere, and others are seen first in the superior formations. Above the marine limestone, or rather parallel with it, we find what is named freshwater or silicious limestone, so called because there is mingled in it a considerable quantity of silex, sometimes uniformly disseminated, and at others forming here and there more or less voluminous masses, which constitute the millstone without shells, which is wrought into millstones. Fluviatile shells are found in the lower parts of this bed, such as Limnia and Planorbis. The next group in the general series of Paris Basin rocks consists of white and green marls, with a considerable quantity of gypsum, the latter being chiefly developed in the center of the basin. The upper parts both of the marine and freshwater limestone alternate occasionally with marls, but the latter form, on the whole, a distinct overlying group of freshwater origin, and contain land and fluviatile shells, fragments of wood, and great numbers of the bones of freshwater fishes, of crocodiles and other reptiles, of birds, and even of quadrupeds, the latter being usually isolated and often entire. The gypsum beds, having been extensively quarried for the manufacture of plaster of Paris, obtained by burning the gypsum. They have yielded a multitude of these mammalian remains, which form the base of the great discoveries of Cuvier, so that the investigation of them by that anatomist may even be considered to have laid the foundation of the science of paleontology, so far as it is dependent on sound principles of analogy. It is chiefly in the lower parts of the gypsum that these extinct quadrupeds are found. Such, for example, are the Anoplotherium and Paleotherium, pachydermatous animals, more or less approaching to the rhinoceros and tapir, of which there were several species. The common Anoplotherium, from the Greek alpha without, oplon, arm, and therion, animal, was of the size of an ass, of a heavy form, and with thick short legs and a long tail. Some species had slender legs, and must have been swift and active, and others of the size of a hare and even of a guinea pig, which were nevertheless adult. The Paleotherium, from the Greek paleos, ancient, and therion, a beast, was of the size of a horse, and form of a tapir. Species of various size, both large and small, existed. Above the gypsum we find another more modern group, consisting of two formations, one marine and the other fresh water. They are composed of marls, micaceous and quartzose sands, and layers of flint. These beds of sand are often of great thickness, and are at first colored by oxide of iron, and then white and pure. They frequently form masses of sandstone, sometimes without organic remains, or only rolled shells of the marine limestone. Sometimes, on the contrary, they contain the casts or impressions of shells. On these sandstones repose new lacustrine deposits, forming sometimes shell millstone, filled with limnea planorbis and seeds of chara or gyrogonates. The Miocene or Middle Tertiary Period. During this second part of the Tertiary period, both terrestrial and aquatic animals became more numerous, and more like those of our own times. Then there existed a great number of mollusks, belonging to species which still inhabit the seas of the present epoch. In England, the Miocene Tertiary is represented by a thin and variable heap of gravelly strata, called the crag formation, which is divided into three parts. The lowest is called coralline crag, because a great many coral remains are found in it. The next is the red crag, distinguished by its deep ferruginous stain. The uppermost is named Norwich, or mammaliferous crag, which is of more recent origin than the red crag, and contains bones of large mammals, and occasionally freshwater shells. An extensive series of Miocene beds occupies the whole surface of both shores of the Chesapeake Bay, 100 miles north and south and 50 miles wide. A similar series occurs in Virginia. The lowest beds of the Chesapeake series are argillaceous, and the uppermost are sandy. Both series abound in fossils, and when met on the side of a river, they are sometimes found to consist of little else than shells and the remains of zoophytes, often in a high state of preservation. The Miocene tertiaries prevail extensively on the continent of Europe in various river basins. They occupy a considerable portion of the west of France, filling up the basins of the Loire and Garonne. They fill up also a great part of the valley of the Middle Rhine, and the whole of the great valley of Switzerland between the Alps and the Jura chain, and from Switzerland they extend towards the northeast, following the course and partly filling up the valley of the Danube. From point to point they may here be traced, spreading out into extensive series near Vienna and in Styria, and occurring again in the plains of Hungary. They are also found in Poland and Russia. They appear both in northern and southern Italy, and on the shores and islands of the Mediterranean. The Miocene beds of the basin of the Loire are chiefly developed near the city of Tours, and in the Touraine district, where they consist for the most part of broken shells. These beds, however, sometimes afford a building stone, the comminuted shells being mixed with sand and gravel and cemented by calcareous matter. In Switzerland there is a series of tertiary sandstones of the Miocene period, and between the lakes of Geneva and Lucerne these beds consist of a coarse conglomerate called nagelfluh, passing into a finer sandstone, the molasse of French geologists, which is usually soft and incoherent, but sometimes sufficiently hard to be used as a building stone. Various beds of lignite and marl are irregularly distributed through the molasse, which are evidently of freshwater origin. The marine deposits of the Miocene strata, although abounding in shells, do not contain as great a number of species as the marine limestone of the Paris basin, yet 18% of these species are identical with those now living in the neighboring seas. There is often the strongest analogy between these new deposits and the lower limestones with which they have been confounded, yet if we do frequently observe a common aspect, and often find the same shells in both, there is, nevertheless, essential differences between them. In one case, we no longer find species characteristic of the lower deposits. There is no Cerithium giganteum, no Cardium porulosum, etc. In the other we find new remains which we did not meet with before, such as the Balanus crassus, the Rostellaria pespelicini, the Pecten pluronectes, etc., which are never found in the Paris Basin, but exist in the Subapennine Formation. The strata belonging to this period of the Tertiary Formation contain diverse species of Paleotherium, but differing from those found in the Paris gypsum. Here we also find several other species of animals, which constitute genera, no trace of which is met with in the preceding formation, and which totally disappear in the succeeding epoch. Here we find the remains of mastodons, from the Greek mastos, a nipple, and odos, tooth, animals analogous to the elephant, but whose teeth have crowns studded with conical or nipple-like points instead of being flat. On the Miocene beds we also find the gigantic Dinotherium, from the Greek dinos, circular, and therion, a beast, an animal resembling the tapir, which is remarkable by having the tusks turned downwards. It was first found in Hesse, afterwards near Auch, by M. Latte, who subsequently found in the same place the bones of monkeys. Remains of the rhinoceros, of the hippopotamus, and of the castor are also found in these deposits. Quote, "The Dinotherium is the largest of the terrestrial mammalia of whose existence we have any positive knowledge, but as it is not a matter of absolute certainty at present of what nature its extremities may have been, we are hardly in a condition to speak very decidedly of its general appearance or habits. It is chiefly known by the fragments of the head and teeth, which exhibit a near approach, the former to the cetacean tribe and the latter to the tapir, but there is a remarkable and very striking anomaly in the existence of two large and heavy tusks, placed at the extremity of the lower jaw and curved downwards like the tusks in the upper jaw of the walrus. It is probable, from the size and position of these tusks, as well as from the structure of the bones of the head, that the animal was aquatic in its habits, living almost entirely in the water and feeding on such succulent plants as it could there obtain. The length of the Dinotherium is calculated to have been at least as much as 18 feet, and its proportions were, probably, very much the same as those of the great American tapir. It was provided with a trunk which seems to have been short, but extremely large and powerful, and capable of being employed to tear up the food which the tusks, acting like pickaxes, may have loosened." Unquote. Ansted. The Miocene is very rich in combustible material. To it belong the lignites of Languedoc, of Provence, Switzerland, and most of those of Germany, as well as the masses of earthy combustible in the neighborhood of Cologne. All these lignites appear to have been formed chiefly from conifers, the structure of which may be recognized in the mass of combustible itself, or in the wood disseminated through various deposits. But the tertiary sandstones of the Miocene period, the molasse, also contain a great quantity of dicotyledonous plants, the wood of which is here and there found disseminated, sometimes in a siliceous state, and clearly exhibiting the proper tissue or structure of this class of plants, particularly characterized by the presence of large longitudinal vessels. We also find leaves, often in great numbers, in the clays which accompany the lignites, in the characters of which we distinctly recognize existing dicotyledons, such as walnuts, maples, elms, birches, etc. Even fruits are found, which are distinguished, often with difficulty, from those now growing. We also find in this formation, either in the midst of deposits of combustible, as in those of Liblar near Cologne, or in the argillaceous or sandy matter of the formation, the remains of monocotyledonous plants. There is wood presenting the structure of the palms, that is, an assemblage of woody fasciculi, bundles, longitudinally arranged, without regard to regularity, in the middle of cellular tissue. Leaves like the representation are also met with. We find, too, in the Miocene, gypsum of the same nature as that of the Paris Basin, which has led to the supposition that they were of the same epoch, but besides this section of country being formed of the molasse, The organic remains are not of the same species. Towards the close of the Miocene or second epoch of the Tertiary period, a new upheaval appears to have taken place in the region of the Alps. A part of this complicated chain of mountains had then long existed. Thus the Alps of Provence and of Dauphiny, which belong to a system of which Mont Viso is the most remarkable point, date from the interval elapsed between the deposit of the inferior and upper layers of the Cretaceous system. Other portions of the Alpine region were raised up at the same time as the Pyrenees, that is, after the Cretaceous period, for example, the neighborhood of Castel Gambert, and in the mountains which connect the Alps to the Jura, we perceive traces of an upheaval contemporaneous with that of Corsica, which occurred after the deposit of the Eocene, or first period of the Tertiary formation. But the greater part of this majestic barrier between Italy and the north seems to have acquired its present configuration and to have attained the immense height we now observe in more recent times. The chain of the Western Alps appears to have been upheaved after the deposit of the Miocene, or second series of the Tertiary, and the chain extending from Valais towards Austria appears to be of still more recent origin. Dating from the geological convulsion which gave to the Western Alps their existing prominence, and at different points produced the elevation of the molasse and other tertiary strata of the Miocene period, as well as those of more ancient epochs, Europe presented a great continental space, and during the period of tranquility which followed this catastrophe, marine deposits did not take place except on the shores or in gulfs not far from the center of this region, as in the sub-Apennine hills, in some parts of Sicily, and on a portion of the coast of England. But sedimentary deposits occurred in the basins or valleys of still existing rivers, and in Lesson 5, Part 2 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Lesson 5, Part 2. The Pliocene or Newer Tertiary. In Europe, the Pliocene is chiefly represented in South Italy, in the Morea, and in the islands of the eastern archipelago. And important contemporaneous beds exist in the valley of the Lower Rhine, near Bonn, and a portion of central France, as well as in southern Russia. The Pliocene beds are not all, however, of the same age, and the beds so called must have been in the course of formation for a very long period. Those of Italy admit of being subdivided into two groups, the older of which is called the sub-Apennine, and attains a great thickness near Parma, exhibiting a considerable number and variety of fossils. These beds consist for the most part of grayish, brown, or blue marls, containing calcareous matter, and overlaid by thick, sandy beds. The Sicilian beds are distinctly newer than these, and are equally extensive. Marls with occasional limestone form the great mass of the materials of these strata. Like the sub-Apennines, they are richly fossiliferous, but are chiefly characterized by their shells. A freshwater bed of the newer period is found at Uningen on the Lake of Constance, and contains numerous remains of fishes and some fragments of land animals. From the Eocene, or deposits of the Paris Basin, there is a progressive increase in the number or proportion of recent species found. In the Paris Basin, 3% of the fossil shells are analogous to the shells now existing. In the Miocene, 18%, and in the Pliocene, 50% of the fossil shells resemble existing species. There is scarcely any analogy between the shells of the Paris Basin limestone and those of the sub-Apennine hills. Besides the Balanus crassus and the Rostellaria pespelicani, we may cite the Pleurotoma rotata, the Buccinum prismaticum, the Voluta limberti, and almost all the shells of the Mediterranean. The deposits alluded to also contain masses of lignites, which are advantageously worked in different localities. Some offer regular layers of a sort of compact coal, brown coal, accompanied by freshwater shells, indicating a tranquil deposit in lakes. But the greatest number contain only irregular masses of wood, some of which present the texture of the conifers. A great number of leaves, analogous to those of existing dicotyledons, are also found. The Pliocene beds of the United States seem to belong chiefly to a very modern period. They exist to a great extent in several localities. At the mouth of the Potomac, in Maryland, is a series of clay beds alternating occasionally with sand. All the fossils found in these beds are identical with those species found living on the neighboring seacoast, a positive indication of the newness of these beds. Similar beds exist at Niagara and in Kentucky, and in other parts of North America. In all cases the recent deposits are very striking. While these lacustrine deposits were tranquilly forming beneath the waters, the then uncovered surface of the earth was inhabited by hyenas, cavern bears, hairy elephants, mastodons, rhinoceroses, hippopotami, and other animals belonging to genera still in existence, but the species of which are now lost. They appear to have been destroyed in the geological revolution which raised up the principal chain of the Alps and gave to these mountains their present configuration and its present shape to the European continent. It is probable, too, that the same revolution destroyed the multitude of animals whose bones are found at the bottom of certain caverns or fissures in the rocks, where they are buried by a sort of calcareous cement, ordinarily of a reddish color. Bone caverns. The most ancient caverns, celebrated for the remains of mammals which they contain, are those of Hartz and of Franconia, but since Dr. Buckland has shown the propriety of removing the mud, sands, rolled flints, stalagmites, etc., which often cover the bone collections, these remains have been found everywhere, even in places where they had not been previously supposed to exist. Most of these caverns appear to have had one or more lateral openings, affording easy entrance to the animals that frequented them as places of refuge, to devour their prey, and finally they came to them to die. Here their bones accumulated through a great many generations, and we now find them buried in a dark earth, in or on which we recognize their dejections. Often we find among the bones of a certain genus of animals other bones, having upon them the print of teeth, showing they had been the prey of the first. The greater number of these bones belong to the bear tribe, two species of which were larger than any now existing, or to the hyena tribe, also larger than those now known. Sometimes one and sometimes the other of these genera predominates. A species of wolf abounds in the bear caverns of Gallenruth in Franconia. Other carnivora of the genus dog and those of the genus cat, including species of cougars, are everywhere in small numbers. The remains of rodents, of ruminants, also of large pachyderms and of birds, which have been dragged as prey to these resorts, are also found. Superficial deposits. Quote, "The regularly stratified deposits of whatever geological period they may be are in most parts of the world covered up, more or less, by a considerable mass of heterogeneous material derived from the degradation of the more ancient rocks. This mass is generally unstratified and deposited in irregular heaps, partially filling up valleys, covering low tracts of level country, and sometimes even capping low hills, but almost always bearing marks of having been transported from a distance over ranges of high land, although not without some reference to the present physical features of the country over which it has traveled. Occasionally the fragments which have been thus conveyed are of large size and angular, and in this case they are called boulders or erratic blocks, but such masses have not generally traveled to any very considerable distance from the parent rock. The transported fragments are much more commonly of small size and rounded, as if by mutual attrition, at the bottom of the sea, and in this state they have been often carried to very great distances, and are found many 100 miles from the place whence they seem to have been derived. They are then called gravel, and are not unfrequently mingled with bones and fragments of bones of large quadrupeds." Unquote. Ansted. These superficial deposits are termed drift, and comprise deposits of water-worn, transported materials consisting of gravel, boulders, sand and clay, etc. Drift is divided into diluvium, or ancient drift, and alluvium, from the Latin alluo, I wash upon, or modern drift. The diluvium, formed from the Latin dilio, I wash away, covers up the tertiary deposits and contains fossils whose origin dates back to a period not very long antecedent to the present. In fact, the diluvium, to a certain extent, unites the tertiary with the recent period. It contains the bones of large mammals, both of extinct and recent genera and species. Among them we may perhaps place the enormous megatherium, from the Greek megas, great, therion, beast, which was not less than 18 feet long and 9 feet high. The skeleton is analogous to that of animals of the order Edentata. The thigh bone in the megatherium is nearly 3 times as great as the largest known elephant. The bones of the instep and those of the foot are of corresponding size. The heel bone projects back nearly 18 inches, and the small bones of the foot advanced as much forwards. The third toe is provided with a socket to receive a claw, the sheath of which measures 13 inches in circumference, and the core on which the nail was attached is 10 inches in length. The forelimbs were well adapted for grasping the trunk or larger branches of a tree. This animal was slow in its movements, and probably fed on roots, which its teeth were admirably adapted for grinding. To the diluvial drift are also referred the great collections of bones of the icy ocean, on the coast of Siberia and on the neighboring islands. There a number of enormous animals, their flesh preserved through thousands of years, lie buried in sands consolidated by perpetual ice. In the same situations have been found stags and horses, the elephant and rhinoceros, covered with hair, seemingly indicating that the species which then lived in northern climates were enabled to bear, from being clothed in fur, lower temperatures than those with naked skins which now inhabit southern Asia and Africa. The tusks of these elephants of the ancient world are sought for the ivory they afford, and compete in commerce with those of modern elephants. It is perhaps to the diluvium we must refer these immense masses of rolled debris which contain gold, platina, and the diamond in Brazil, in Africa, in India, and in the Ural Mountains, as well as in the arenaceous veins of tin in Cornwall and Mexico. The boulder formation, or erratic block formation, also is regarded as part of the diluvial drift. A great part of the plain of Switzerland is covered at intervals by fragments of rock measuring about a cubic yard, which strew the plain and dot the sides of the alpine ravines, and rise on the opposite side of the Jura range, even to an elevation of several thousand feet above the sea. The most concentrated distribution of these blocks seems to be near the town of Neuchâtel, but similar masses are also found on the summit of the Mont Salève, behind Geneva. It is very remarkable that a belt of fragmentary masses, not a few or small, but countless and gigantic, differing entirely in character from the formation on which they rest, should be found lying on a steep, almost precipitous slope of nearly bare or thinly covered rock. One of the blocks behind Neuchâtel, 850 feet above the lake, is of granite and measures between 50 and 60 feet in length by 20 feet broad and 40 feet high, while between the Jura and the Alps blocks still larger are in many places to be found, one out of a great number together in the canton of Bern, measuring 61,000 cubic feet. Erratic blocks and gravel cover the plain of Central Europe and the steppes of Russia. Almost the whole surface of North America, as far as it has been examined, has been found covered with gravel, pebbles, and boulders, varying greatly in thickness, and obviously of the same origin as similar deposits in Europe. In a region which has been called the Great Atlantic Plain, extending between the Alleghany Mountains and the Atlantic Ocean, together with the lower part of the great valley of the Mississippi, appear to be the districts where it conceals the underlying deposits to the greatest depth. On the borders of Lakes Erie and Ontario there are very decided marks of the great drift which has elsewhere overspread North America, and the boulder formation, containing marine shells, extends into the valley of the St. Lawrence as far down as Quebec, and at a height of at least 300 feet above the sea level. Below Quebec there are large and far transported boulders in beds, both above and below these marine shells, and wherever the contact of the drift with hard subadjacent rocks is seen, these rocks are smoothed and furrowed on the surface, as they are in similar positions in northern Europe. Alluvium, or modern drift. In many parts of North America the valleys are filled up to a depth of 20 or 30 feet with unconsolidated beds of earth of various kinds, and the heterogeneous mass contains in it abundant remains of large pachydermatous animals now not living in the country, but associated with and overlaid by other and similar beds in which occur the bones of buffaloes that have within a few years been driven westward by the advancing steps of civilized man. These beds all belong to the same geological period, or nearly so, and a description of one will be sufficient to give an accurate notion of a multitude of similar bogs and soft meadows in many of the western states. The most remarkable is that known as the Big Bone Lick in Kentucky. The Big Bone Lick occupies the bottom of a boggy valley, kept wet by a number of salt springs, which rise over a surface of several acres, and the substratum of the country is a fossiliferous limestone. At the lick the valley is filled up to the depth of not less than 30 feet with beds of earth, the uppermost of which is a yellow clay, apparently the soil brought down from the high grounds by rains and land floods. In this yellow earth, along the watercourses at various depths, the bones of buffaloes and other modern animals are often found quite entire. Beneath the clay is another layer of a different soil, bearing the appearance of having been formerly the bottom of a marsh. It is more gravelly, darker colored, and softer than the other, and in it, or sometimes in a stratum of compact blue clay alternating with it, there are found innumerable bones of large mammals, chiefly mastodons, but including also elephants and extinct species of animals of the ox and deer tribe. In other localities the mastodon bones are found immediately below the surface in reclaimed marshes, and they are sometimes extremely perfect, sometimes broken and water-worn. The Big Bone Lick would appear to have been resorted to not only in modern times by the living races, but more anciently by animals now extinct, for the salt, and perhaps the food produced by the marsh. The buffalo and bison are frequently known to perish entrapped in these licks and swamps, and it seems evident that the mastodon and elephant of former times must, from their huge size and unwieldy forms, have been at least equally exposed to the same fate. Anstead, Rogers, etc. Up to the present time, all geologists agree in saying that in the formations of this period, as well as in the most ancient rocks, neither human bones nor any vestige indicative of the existence of man on the face of the earth has been found, and it is for this reason probable that man had not yet been created at the time of the destruction of these animals. Eighth geological epoch. Modern formation. New formations are now being made, either by the effusion of igneous matter from the bowels of the earth, or by sediment from waters, and these formations, which are contemporaneous with man, constitute the modern formation. Since the last great catastrophe alluded to, the upheaval of the Alps, there has been a general repose, which perhaps will be disturbed one day by some new geological revolution, by the upheaval of some great mountain chain, for example, and by the great rush of waters which must follow such a convulsion. New lands will rise from the bosom of the ocean, and probably enclose remains of the bony frame of man and of animals now existing, just as the ancient formations conceal the solid remains of creatures which preceded us on the earth. Even now we have proof that things must pass in the present time very nearly as they did in ages long gone by, for in certain modern formations, which continue to be formed under our eyes, we find human skeletons embedded in the substance of the rock, and already presenting the characters of fossils of the Tertiary period. One of the most remarkable examples of this kind has been discovered in the island of Guadeloupe. Thus far we have presented a sketch of the earth's structure as revealed to us by an examination of its crust, only in reference, however, to the order of superposition of its formations, resulting from great geological convulsions, and characterized by the remains of animals found entombed in it. When we reflect on the inconceivable length of time it has evidently required to effect all these changes, and elevate one above another gigantic stories of various rocks, the imagination is startled. When we see entire creations of plants and animals covering the surface of the earth and inhabiting the waters disappear after a time, leaving a few mutilated remains as the only trace of their existence, and give place to a new flora and a new population of animated creatures destined to undergo in turn a similar fate, we are struck with astonishment, and overcome by admiration of
Lesson 6, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Abai in May 2016. Elements of Geology by William Ruschenberger. Lesson 6, Part 1. Influence of internal agents on the surface of the earth. Earthquakes. Description, effects of, changes of level produced by, upheaval and subsidence, constant level of seas, slow and progressive subsidence, general conclusions. Volcanic phenomena. Explosion, eruption, Island of St. George, Monte Nuovo, Jorullo, Vesuvius. Definition of a volcano. Submarine eruptions. Volcan of Unalaska. Crater of elevation. Formation of craters. Effects of upheaval. Form of volcanic islands. Periods in the formation of a volcano. Interior of craters. Kirauea. Sulfuratas. Volcanic ashes. Lava currents. Characters of lavas. Dikes. Gaseous volcanic products. Eruption of mud. Solid products of volcanoes. Trachyte. Obsidian. Compact lavas. Porous lavas, etc. We have spoken of formations and of their relative order of superposition, and occasionally alluded to the various causes which affect them. From what we have said, it might be inferred that the several formations are so many concentric spheres enveloping a mass of fire, and such in fact might have been the case had it not been for certain disturbing forces which have fashioned the mountains and valleys, and caused the dry land to be lifted up above the waters. Had it not been for these disturbing forces, phenomena analogous to volcanoes and earthquakes, the whole globe would have remained under water, and man would not have been called into existence. But having seen the general structure of the interior of the earth, we will study the phenomena, the disturbing forces which modify its surface, more particularly than we have yet done. These disturbing forces are either internal or external. First, of the influence of internal agents on the surface of the earth. It has been already stated that the center of our earth is a mass of fire, to the influence of which many phenomena may be referred. Earthquakes. Description of earthquakes. Everyone has heard of the terrible scourge which in a moment reduces the most flourishing cities to a heap of ruins, and sometimes upturns the neighboring country. An earthquake is often preceded by rumbling, subterraneous sounds, which are frequently heard some time before the catastrophe. Tremblings more or less violent are perceived during a few minutes or seconds only, which in many instances are often repeated with more or less rapidity and force. In certain cases they even continue with irregular intervals during several days or months or even entire years. These movements of the earth are of different kinds. Sometimes they consist of jerking horizontal oscillations, occurring at irregular intervals, sometimes of vertical shocks, that is, in rapid and successive rising and falling of the soil, at other times of various twisting movements. Frequently all the various motions take place almost at the same moment, and then nothing can escape destruction. Sometimes an earthquake is circumscribed in narrow limits. That which happened on the 2nd of February 1828 in the island of Ischia was not felt either in the neighboring islands or on the continent. Frequently, too, it shakes an immense surface. For example, the earthquake of the 17th of June 1826 in New Grenada was felt over many thousand square leagues. Sometimes it extends enormous distances, as in the case of the famous earthquake of Lisbon, which was felt in Lapland in one direction and Martinique in another, and transversely from Greenland to Africa, where Morocco, Fez, and Mekines were destroyed. All Europe experienced its effects at the same moment. From the different histories of earthquakes, many examples of this kind of propagation might be adduced, extending more or less widely. It may be even concluded, from statements of facts, that the shock extends according to a great circle, more or less inclined to the equator, and perhaps over an entire hemisphere. Effects of earthquakes. Earthquakes, when violent, not only overturn entire cities and the most solidly built edifices, but they cause important modifications in the ground itself. Those of Calabria in 1783 furnish examples which are the more important because the facts were observed by the most distinguished men of the times, such as Vicenzio, physician to the King of Naples, Grimaldi, Hamilton, Dolomieu, etc., and also by a commission appointed by the Royal Academy of Naples. All was overturned in this unhappy country. The course of rivers was interrupted and changed. Houses were raised above the level of the country, while others, frequently at no great distance, were sunk down more or less. Edifices of great solidity were split from top to bottom. Certain parts were raised above others, and their foundations pushed up out of the ground. Everywhere the surface of the earth partly opened, often in long crevices, some of which were 150 yards in breadth. Some of these were isolated, sometimes bifurcated, frequently exhibiting other fissures perpendicular to their direction, Fig. 179. Some were in form of rays diverging from a center like a broken glass, Fig. 180. Some opened at the moment of the shock, and immediately closed again, grinding betwixt their parietes the inhabitations they swallowed up. Others invariably remained gaping after the commotion, or, commenced by a first shock, were widened by the succeeding shocks. In both cases it was sometimes observed that the borders of the split were on the same plane, or showed a more or less projecting swelling up, Fig. 181. Sometimes one of the parts is elevated much higher than the other, Figures 182, 183, showing that one must have been raised while the other was sunk. Again, it happens that a more or less considerable extent of surface is suddenly sunk, carrying down plantations and habitations, leaving yawning chasms with vertical sides 80 or 100 yards in depth. In certain cases an immense quantity of water springs from the bottom of these cavities, forming more or less extensive lakes, sometimes without apparent current, and sometimes giving origin to impetuous torrents. In some instances, on the contrary, rivulets were absorbed by the fissures in the earth, or swallowed for a time, or forever. But, besides the numerous cracks and diverse chasms which intercept the waters, furnishing new springs and giving them a new channel, it also happens that masses of rocks, falling across valleys, arrest the waters and soon form lakes in the upper part. Now, these accumulated waters make new passages, either by breaking through the sides of the valley or by enlarging some fissure in the mountain, or they degrade, cut down the obstacle which retained them, and soon overturn it entirely or in part. Hence arise those fearful outbreaks, those impetuous torrents rolling down enormous masses of rock, the ravages of which are as disastrous as the earthquake itself, and which, excavating new channels or widening and deepening those that waters before pursued, mark their course by the debris which they roll down and successively deposit. When the principal effects of earthquakes took place on the continent between Oppido and Soriano, the phenomena extended as far as Messina, across the straits. More than half the city was destroyed, and 29 hamlets or villages were swallowed up. The bottom of the sea was sunk and disturbed at various points. The shore was rent, and the whole ground along the port of Messina was inclined towards the sea, suddenly sinking several yards. The whole promontory which formed its entrance was swallowed in a moment. Upheaval and subsidence. The earthquakes which occurred in the coast of Chile in 1822, 1835, and 1837 have produced effects not less remarkable. Different parts of the coast, from Valdivia to Valparaiso, that is, an extent of more than 200 leagues, were evidently elevated above the waters, as well as many neighboring islands as far as those of Juan Fernandez. The bottom of the sea to a considerable extent participated in this phenomena. On the coast, rocks which had been previously under water were raised 2 or 3 yards above its level, with the mollusks which lived on their surface. Rivers emptying on the coast became fordable where they had been navigable by small vessels. Well-known anchorages were diminished in depth to a corresponding extent, and at different points shoals now opposed the passage of vessels of large draught where they readily floated before. Analogous circumstances occurred in India in 1819. A hill 50 miles long and 16 broad was raised up in the midst of a flat country, barring the course of the Indus. Further to the south, on the contrary, but parallel to the same direction, the country sank, carrying down the village and fort of Sindre, which nevertheless remains standing, half submerged. The eastern mouth of the river became more shallow in many places, and portions of its bed which had been fordable suddenly ceased to be so. The history of all times and of all places furnishes us with facts of exactly the same nature. Everywhere we are told of fissures in the earth, of profound chasms in which cities and even entire countries are swallowed, from which flow mephitic gases, enormous masses of water, sometimes cold, sometimes hot, sometimes even flaming. Also of plains suddenly transformed into mountains, of shoals raised in the midst of the ocean, of mountains rent and overturned, of mountainous regions, of hundreds of leagues of rocks, all at once levelled and replaced by lakes, of water-courses changed, swallowed in chasms of the earth, of lakes which dry up by breaking through their bounds, or suddenly lost in subterraneous conduits, instantaneously formed. In opposition, we also learn of enormous springs producing new streams, suddenly rising through a fissure of a rock, without any knowledge whence the waters come, of thermal springs which have become instantaneously cold, of others, on the contrary, appearing where they did not exist before. All these phenomena are so many indications of fissures in the earth which afford new channels to waters which might have circulated there before. Relatively to the sea-coasts, these phenomena are often mentioned by authors in a peculiar manner. Rarely do we see it explicitly announced. There is an elevation, but the event is stated in other terms, referring the effect to the most movable element. In this way authors speak of the sea having retired more or less, leaving its bed dry, either permanently or only for an instant. Sometimes, on the contrary, they mention that the sea suddenly overflowed more or less elevated coasts. Geologists translate these indications by the term oscillation, if the phenomenon be momentary, and by the terms upheaval or subsidence of coasts, if it be permanent, because they refer these effects to the solid parts of the globe, and not to the sea, the level of which does not vary. Nevertheless, it must be borne in mind that, if these transitory phenomena may sometimes be attributed to oscillations of the earth, they may also arise from a real impulse communicated to the waters of the sea, and possibly partake of both causes. We know, in fact, that during earthquakes the sea is sometimes violently agitated, that its waters, elevated to considerable heights, occasionally make fearful eruptions on the land, advancing and retiring again, carrying devastation over a greater or less extent. These impetuous movements of advance and retreat, accompanied by sudden dislocations caused by subterraneous commotions in the solid crust of the globe, may occasion frightful havoc. The history of the Grecian archipelago, or the islands of Japan, and of a multitude of places, is full of disasters produced by these catastrophes. The various effects produced by earthquakes under our eyes, and those cited in the most authentic narrations, tend to confirm what is transmitted to us from the most remote times, although we might state the facts in other terms. Who dares formally to contradict Pliny, relating, according to the historians, that Sicily was separated from Italy by an earthquake, that the island Cyprus was separated from Syria by the same means, and that of Euboea, Negropont, from Boeotia, etc. We would not even positively deny the existence of the Atlantis, swallowed by the waters, according to Egyptian tradition, in a day and a night. Let us rather declare that the assemblage of observations we have evidently shows that immense upheavals and subsidences have for a long time formed part of the mechanism of nature, in bringing the surface of the earth to the configuration we now observe. Constant level of seas. We have just admitted the subsidence and upheaval of coasts, and laid down the principle that the level of seas is invariable. But this last assertion being contrary to opinions commonly received by the world, it is necessary to support it by demonstration. The laws of hydrostatics teach us that a mass of liquid cannot be permanently elevated or depressed at one point of its surface, but that a level must be established after oscillation, great or small, ceases. Hence it follows that the level of the sea cannot be stationary at one point without its being so throughout, and that the waters cannot be elevated or depressed in one spot without similar changes being experienced at all points of the same basin. Now we know thousands of localities where the surface of the sea has not undergone the least variation since the most remote historic times. Therefore the level has not changed, and its constancy is the most positive fact we are aware of, because it has been subject to the proof of all ages. On the other hand, if we could be led to suppose, like the inhabitants of Chile, seeing the manifest change on their coast, that the sea has subsided there, we must also conclude, with the inhabitants of California, Peru, Brazil, etc., that in those places it underwent no variation. It must also be admitted that the sea has risen at the bottom of the Gulf of Arabia, as it has done, in different epochs, on the coast of Portugal, in the Straits of Messina, etc. All these circumstances are incompatible with each other and opposed to the laws of hydrostatics, and hence we conclude that instead of the immutability of the ground, which an error, analogous to the idea of immobility of the globe, has created, we must admit immutability of the seas, by acknowledging that the solid surface of our planet is susceptible of elevations, depressions, and all kinds of disturbances. The slow upheaval of Sweden has already been noticed. slow and progressive subsidence. There is no doubt that, for 4 centuries past, the western coast of Greenland is continually sinking, through an extent of 200 leagues north and south. Ancient buildings, both on the low islands and on the continent, have been gradually submerged, and it has been frequently necessary to move various establishments built near the shore farther inland. Subsidence of certain islands in the South Seas has been indicated, but in those places, so rarely visited by geologists, the facts are not yet clearly established. General conclusion. It must now appear to be well established that earthquakes are capable of producing great modifications of the earth's surface, since, within our times, vast tracts of country have been elevated sensibly above the level of the sea. It is not less evident that there is a slow power in operation, in virtue of which different parts of our continents may also be successively raised, and that it also produces gradual sinkings as well as sudden subsidences, which are doubtless correlative phenomena. All these circumstances, however remarkable, are, nevertheless, not very astonishing, when we reflect on the enormous disproportion which exists between the thickness of the solid crust of the globe and the mass of melted matter it envelops. It is surprising that such a crust, a mere rind, relatively almost as thin as a coating of gold leaf on an orange, should be disturbed in every manner by the least movement of the subadjacent mass, particularly if we bear in mind that similar movements doubtlessly have been taking place ever since the first pellicle was consolidated on the surface, and all the successive crusts must have been rent in every direction. Lesson 6, Part 2 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in October 2016. Elements of Geology by William Ruschenberger. Lesson 6, Part 2. Volcanic phenomena. General notion: explosion, eruption. Volcanic phenomena are closely connected with earthquakes. They are, in a manner, the final results of them. When, by the shaking and elevation of the ground, the terrestrial crust is deeply broken, a temporary or permanent communication is established between the interior and exterior of the globe, through which various kinds of matter are disengaged from the bosom of the earth. Through the crevices escape gases of different kinds. Waters hot or cold, simple or sulphurous, and loaded with mud are the most simple transitory results. But frequently there are also, through the upheaved and broken ground, amidst violent detonations, explosions which eject, to a great distance, all the debris of the formation, as happened at Saint-Michel in the Azores in 1522, where the debris of 2 hills covered the whole city of Villafranca. It most frequently happens at the same time that more or less considerable eruptions of incandescent matters take place, consisting of scoriae, pumice, etc., in a melted state, which are either projected to a distance, or run on the slopes, or accumulate on the spot to a greater or less height. This has occurred in a great many localities. Eruption of the island of St. George. In the month of May 1808, in the island of St. George, one of the Azores, the soil in the midst of cultivated fields, after being upheaved, opened at many points with a fearful noise. It first formed a vast cavity, or crater, of 100,000 square yards, then a smaller one at the distance of a league, and finally 12 or 15 little craters on the broken surface. An enormous quantity of scoriae and pumice was projected to a distance, and the ground was covered 1.5 yards deep over an extent 1 league wide and 4 leagues long. For more than 3 weeks afterwards, currents of melted matter flowed from the principal crater to the sea. Monte Nuovo. Monte Nuovo, formed in 1538 at the bottom of the Bay of Baia on the coast of Naples, is another example of a similar eruption. Violent earthquakes had continued during 2 years. On the 27th and 28th September they did not cease either day or night. The plain found between Lake Averne, Monte Barbaro, and the sea was then upheaved, and various cracks were evident, etc. Pietro Giacomo di Toledo. Then a great extent of ground was elevated, and suddenly assumed the form of a growing mountain. In the night of the same day this little mountain of earth opened with a great noise, and vomited flames, as well as pumice, stones, and cinders. Porzio. The pumice came from the upheaval of the soil, which consists of this material throughout Campania, and the stones and cinders came from the eruption which occurred at the moment. We still see on the south side of the mountain a ridge of scoriae, and on its summit the crater which produced them. The eruption lasted 7 days, and the matters projected and ejected partly filled Lake Luerin. From that time the most perfect tranquillity has prevailed. Jorullo. There was something analogous, but under peculiar circumstances, in what happened in Mechoacan, near the town of Ario, on the 29th September 1759, after an earthquake of 2 months' duration. In the midst of a plain covered with sugar-cane and indigo, and traversed by 2 rivulets, there formed in a single night, says Mr. Humboldt, a gibbosity bunching up 160 yards high near the center, covered by thousands of small smoking cones, in the midst of which were raised up 6 great hillocks, arranged in one line, in the direction of the volcanoes of Colima and of Popocatépetl. The highest of these hillocks, called Jorullo, was more than 500 yards in height above the plain. From its sides escaped a great quantity of lavas. Vesuvius. Something similar must have occurred in Vesuvius, for Strabo describes the mountain so called by the ancients without in any way alluding to the remarkable cone which now exists, and which he would not have failed to mention. It is evident this cone did not then exist, but the crests which rise in semicircles on the north, forming what is now called the Somma, probably constituted part of a complete circle. The south half, which was much more arched and separated from the other by a diametrical split, only offers now a trace at the east, and an indication at the west by the pumice tufa of Salvatore. The mountain, which is probably represented in figure 186, was, says Strabo, very fertile on its slopes. Its summit was truncated, in a great part united, entirely sterile, of a burnt aspect, exhibiting cavities filled with cracks and calcined stones, from which it may be conjectured that these places were formerly burning craters. All leads to the belief that the cone, which alone bears the name of Vesuvius now, all the products of which differ from the rocks of the Somma, was not formed till long afterwards, and probably at the same time of the famous eruption in the year 97, which cost the life of the Roman naturalist. It then, without doubt, formed a permanent conduit in the midst of the matters which are raised in form of a dome, and which has been enveloped by subsequent scoriae. This catastrophe seems to have produced but little lava, but a horrible upheaval, which precipitated a great part of the mountain into the sea, Pliny the Younger, and buried Herculaneum and Pompeii, not under torrents of melted matter, as commonly said, but under avalanches of pumice which previously existed on the slope of the mountain, for Vesuvius itself has never produced an atom. If the whole south slope turned towards the sea is now occupied by lava, it is evident that before the formation of the permanent volcan it was covered with pumice tufa, traces of which are still seen at different points, the same as now on the external slope of the Somma and in all Campania. Definition of a volcan. In those events, it often happens that the rent which has given rise to observed effects is obstructed or closed at a considerable depth, and tranquillity is entirely restored, as at Monte Nuevo. Under other circumstances, on the contrary, the rent forms a permanent conduit at once, or after several shocks in the same place. In this case, there is sometimes established a continuously active furnace, from which gaseous matter in abundance is disengaged, or from which lava continuously boils, and from which there is an incessant projection of scoriae. This has been the case at Stromboli from the remotest antiquity. At other times the conduit is temporarily obstructed at its upper part, but the least effort is sufficient to remove the obstruction, or to produce a new opening in the vicinity through some fissure which communicates with the principal conduit. In all cases the result is a centre of easy communication between the interior and exterior of the earth, and it is this which is called a volcan or volcano. This facility of communication is probably a preservative against the violence of earthquakes. Indeed, it has been observed that, from the moment an eruption takes place anywhere, the shocks which had been felt up to that time become fewer and weaker, and even cease altogether. The earthquake of Caracas in 1812 terminated by the eruption of the volcan of St. Vincent in the Antilles. The eruption of Jorullo and that of Monte Nuevo terminated the earthquakes which desolated the surrounding countries. On the contrary, when a volcano becomes inactive, it seems to announce earthquakes. In 1797, when the volcan of Puraque, near Popayan, had ceased to emit flame and smoke, the valley of Quito was agitated by violent shocks. Volcans, therefore, seem to be natural vents, designated by Providence to prevent a complete destruction of the globe, and its inevitable rupture into fragments, which, launched into space, might there describe new orbits. Submarine eruptions. It is not only on land that volcanic phenomena occur, they also take place under the sea, as might be naturally anticipated. In our own times we have had formed in this manner the island of Julia in 1831, on the southwest of Sicily, Bogoslav in 1814, in the Aleutian archipelago, Sabrina and another one not named in 1811 in the Azores, where, previously, at different epochs, others were formed, according to the most authentic histories. The same thing occurred at different times around Iceland, and various accounts indicate that in the islands of Sunda, the Philippines, and Moluccas throughout the Pacific, in the Kurils, Kamchatka, etc., similar phenomena took place. Volcan of Unalaska. One of the most striking examples is furnished by the island which arose in 1796, about 10 leagues from the northern point of Unalaska, one of the Aleutian Islands. At first a column of smoke rose above the surface of the sea. Then a black point appeared, the summit of which launched forth sheets of fire and stones with violence. This phenomenon continued for several months, during which the island grew successively in extent and height. Later, smoke only issued, which ceased altogether 4 years afterwards. Still the island continued to enlarge and to rise without any apparent ejection, and in 1806 it formed a cone which might be seen from Unalaska, and upon it were 4 other smaller ones, on the northwest side. Santorin. The Mediterranean also furnishes a fine example of submarine eruptions in the midst of the space comprised between the islands of Santorin, Teresia, and Aspronisi, which, according to the ancients, appeared above the water several centuries before the Christian era in consequence of violent earthquakes. In this circuit, Hira arose first, 186 years before our era, which subsequently grew by little islets rising on its borders in the year 726, 1427. Then, in the same way, Mikra Kameni in 1573 and Nea Kameni in 1707 were formed, and successively growing in 1709, 1711, 1712, etc. No crater was formed in either of these islands, and we only have there the appearance of volcanic matter in form of a dome, which seems to have covered the orifice through which it escaped. There was no volcan there, according to the terms of our definition, but a tendency to form one at some future time. The islands of Milo, Argentiera, Polino, Policandro, Poros, etc., are formed of the same materials and probably had the same origin. What passes in these phenomena? These submarine phenomena are announced by incandescent matters ejected above water, by scoriae and pumice which float on the surface, by burning rocks which appear in the midst of waves of vapor, and by the boiling of the sea, the temperature of which becomes very much increased. All these things occurred in our own times, at Julia, at Sabrina, etc., and are such as authors mention in detail in all their accounts. Father Gore has given us a history of the upheaval of Nea Kameni of Santorin in 1707, and all the circumstances he relates agree with what Strabo, Pliny, Plutarch, and Justin tell us of the appearance of Hiera in the midst of flames and a violent ebullition of the sea. But the circumstances we have just spoken of are not always all present at the same time. Sometimes no solid rock appears above water. This was the case at Kamchatka in 1737, where jets of vapor, great ebullition of the sea, and pumice stones floating on the surface were all that was perceived. But when the spot could be approached, there was found a chain of submarine mountains, where there had been previously a depth of more than 100 fathoms. In certain cases there is not even a jet of vapor, and the phenomenon is manifested by the heat of the water only. This happened in 1820 at the island of Banda, among the Moluccas, where the bay, which was upwards of 50 fathoms deep, was filled by the tranquil elevation of compact basaltic matter, probably pre-existing, which formed an elevated promontory composed of large blocks piled one on the other, and its appearance was manifested by the heat of the water only. It also seems that after eruptions there is often a peaceful and slow upheaval, as in the island formed before Unalaska and at Santorin, according to the observations of Mr. Verlet. Indeed, between Mikra Kameni and the port of Fira, where there is an abrupt submarine mountain, there was, at the beginning of the present century, 15 fathoms of water above the highest part, but there were only 4 fathoms in 1830, and little more than 2 in 1834. It is presumed a new island, that is, the summit of a new cone, will appear in the Gulf, and the appearance will, probably, be accompanied by such phenomena as we mention. Let us add that islands which rise to the surface of seas do not always remain. Many of them disappear after a longer or shorter period, either by being washed down by the waves, as is supposed to have been the case with the island of Julia, or by their mass sinking into an abyss formed beneath them. The last circumstance doubtlessly happened to an island which was elevated in 1719 near St. Michael, Azores, and disappeared in 1723, leaving in its place a depth of 70 fathoms. In the same region there was an island in 1638, where there is now a bottomless abyss. Crater of upheaval or elevation. The first effect of an eruption is to burst, by its violence, the crust of the earth in the direction which matters pent up in the interior have taken to escape. The ground, no matter of what nature, is at first raised to a more or less considerable extent, or arched like a bell, and often cracked in every direction, at once the explosion occurring as if by the action of a formidable power blast. An opening is made in the form of a funnel, through which often escape gaseous and other matters which caused the event. It is to these initiatory openings, which may be made anywhere, to which the name of crater of elevation has been given, from the necessity of distinguishing them from all that may subsequently occur in the series of volcanic phenomena. The hillock itself, which is produced on the soil by the first effect, is called the cone of elevation, to distinguish it from analogous hillocks, which are often formed also by the accumulation of incoherent materials ejected from the volcano. Character of these openings. What characterizes craters of elevation and enables us to recognize them in places where there is no account of an eruption is the disposition or arrangement of the upheaved strata, being very different from what is everywhere else observed. These beds are here found inclined all round the axis of the cone, as in the section in Figure 188, rising more and more from the base to the summit, and presenting their abrupt escarpments towards the interior of the cavity. Monte Nuovo is an example in miniature. The mountain was formed by elevation, hollowed at its summit by ejecting gases and incandescent matters, and the cavity, which can be examined now, has around it, at an inclination of 30 degrees, strata of different formations, which in all the rest of Campania are horizontal. The semicircle of the Somma presents the same character as in the inclined tables of amphigenic porphyries, and analogous circumstances exist in many other localities. Another character, not less important, and especially useful when the upheaved matters are not divided into beds, is furnished us in great craters of elevation by the crevices or cracks which extend from the margin of the escarpment to the external base of the mountain, forming what are named barrancos in the Canary Islands, where they are so remarkable. One of these barrancos, or ravines, much deeper than the others, extends from the foot of the mountain to the bottom of the crater, as is shown in the following view. This last character is seen almost always in the different localities produced by similar events, as well as in most islands which have been upheaved in our times in the midst of the ocean. Frequently there are many valleys of the same kind. Remarks on the formation of craters. We have mentioned explosion as determining, definitely, the formation of the crateriform cavity at the summit of the upheaved mass. However, it is not probable that this circumstance, which is applicable to Monte Nuovo, the island of St. George, etc., is constantly seen in all cases. It seems to be even totally inadmissible in certain craters of vast extent known to exist in a number of places. But this explosion is not even necessary. In fact, it is easy to conceive that after a fracture, as in Figure 190, which is a correlative result of elevation, it may happen that all the erect, column-like masses, and all the elongated points between the rents, might be tumbled down at the same moment, or by a subsequent action. Hence results an open cavity, the margin of which is formed by all the debris, and the depth is in proportion to the sum of the voids or spaces formed by the fractures. On the other hand, it is clear that elevation is produced by some matter, liquid or gaseous, which pushes the crust of the earth and forces it to swell upwards. Now, if it happen that this matter should find exit at some other point, or retire again into the bowels of the earth, the upheaved part being left without support may sink into the abyss left beneath it, and consequently cause an immense vacuity in the midst of the gibbosity or hillock, then merely forming a mass hollow in the centre and cracked on the margin. This must have taken place in many cases, and notably in the mass of Etna, the eastern slope of which presents a vast excavation, called Val de Bove, which is bounded by high ridges, cracked at various points. This comment need not be regarded as a simple theoretic speculation. There are many examples of similar excavations, independent of the effects produced by earthquakes. At the summit of Mount Etna there is one of 1,300 feet in depth, which dates from 1832, and many others which were produced at the end of the last or beginning of the present century. Frequently lakes are formed on a sudden, sometimes of boiling water, by the sinking of the land consequent on volcanic eruptions, as in 1835, near the ancient Caesarea in Cappadocia, in 1820 in St. Michael's, Azores, etc. It has also happened that high volcanic mountains have at once sunk, their place being at once filled by deep lakes, as the volcano of Parbadayan in Java in 1772, which carried away with it 40 villages built on its sides, as also in 1638 the peak of the Moluccas, which could be perceived 12 leagues at sea. We know that the summit of Carguaraizo, which rivaled Chimborazo in height, crumbled in 1698, and the same occurred to Capaurcu, also situated on the plain of Quito, a short time before the arrival of the Spaniards in America. Many other facts of a similar kind could be adduced in support of the theory advanced. Effects subsequent to elevation. The crateriform cavities we have spoken of sometimes remain the same as when first produced. Often, however, various volcanic phenomena subsequently occur at different times and in various ways. In this manner it was that the cone of Vesuvius was formed in 79 in the ancient crater of the Somma, that the peak of Teneriffe is found in a circle, the vertical walls of which rise from 600 to 1,200 feet, that the volcan of Taal in Luzon, one of the Philippine Islands, is in the center of a basin filled with water and surrounded by elevated rocks, having a single opening only for entrance, etc. Islands which have been elevated in the midst of the sea frequently exhibit phenomena of the same kind. Thus the islands of Santorin, Teresia, Aspronisi, which were elevated long before the Christian era, present the appearance of a vast crater of elevation. Their slopes are gentle, externally, but abrupt, on the contrary, towards the center of the circle of which they form the margin. The ground is composed of various strata, inclined outwardly, among which are limestone and argillaceous schist. In the middle of the circle, the depth of which is considerable on the borders, all the subsequent volcanic phenomena were produced, and here the 3 summits of cones successively appeared, which constitute 3 modern islands, and are still preparing new eruptions. Something similar is seen in the Gulf of Bengal, on the island of Barren, discovered in 1787. It is a vast circle formed of high mountains, into which the sea penetrates by a single opening, and has a Lesson 6, Part 3 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in November 2016. Elements of Geology by William Ruschenberger. Lesson 6, Part 3. Similarity of configuration in volcanic islands. Different volcanic islands, which have been formed under our eyes, as it were, in the midst of the ocean, are entirely analogous to those we have mentioned. The island of Sabrina, at the moment of its appearance, presented a crater which opened to the south, and terminated by an opening through which issued a current of boiling water. According to the accounts, the island of Julia must have been somewhat analogous, and the history given by Captain Tyre, reported by Pöppig, shows such to have been the case. On the 6th September 1835, to the north of New Zealand, this navigator almost witnessed a submarine eruption, which presented an annular rock, almost on a level with the surface of the sea, in the midst of which was a lagoon having a single outlet, and in which the water was burning. Now, these islands appear to be nothing more than points of domes upheaved, like those in the Gulf of Santorin, either instantaneously or slowly, and having the summit broken like Monte Nuovo. These are true craters of elevation or of explosion, as we would call them, and as such they may consist of solid rocks or of various tufas, or even of scoriae accumulated on their borders. The archipelago of the Azores, which have so often witnessed rising from the sea similar islands, which time has destroyed, presents us one which seems to have escaped destruction, to exhibit to us how all those were formed which have disappeared. This is the rock of Porto de Ileo, which presents a vast circle into which vessels enter for shelter. Its sides rise 400 feet and are composed of volcanic tufa. These phenomena explain to us the origin of a great many islands found in the ocean, both by the analogy of their form to those we have named and their nature. Some are in the form of a horseshoe, having a more or less expanded opening which gives access to the middle of the deep basin they enclose, and in the center of which isolated volcanic hillocks are occasionally found. Others are entirely circular, having some of the points of the circle more or less broken, or groups of small islands arranged in a circle, which are more or less prominent above the water. Different periods of the formation of a volcan. We may often distinguish in the mass of a volcanic mountain several different parts, each of which corresponds to a particular mode of formation. The first gibbosity or hill is, in general, the effect of elevation of the pre-existing soil, which may be of any kind or nature. Afterwards, sooner or later, a fissure is formed, which produces either a crater of elevation or a dome of pasty matter, as at Jorullo, clearly detached from the first hillock, and, as a last result, in the midst of one or the other a permanent chimney is formed. Often the formation of the terminal cone then commences by the scoriaceous matters raised by the melted lava filling the primitive conduit, which overflows the margin of the aperture, or it is ejected into the air, from which it falls again around the center of eruption, accumulating in cones with a maximum slope of from 30 to 35 degrees. These loose scoriae melt on the side towards the interior of the chimney, which they narrow more and more by the successive cornice-like projections they form, and in this way conceal the true diameter of the crater. It is rare that these three kinds of formations are all found in the same volcano, but we always find the gibbosity produced by elevation and one or the other of the secondary domes. At Tenerife there is a broken dome which was upheaved in the middle of a crater of elevation. At Vesuvius, from the constant solidity of the base and other circumstances, we may infer the existence of a central nucleus, produced in the same way as a dome in the year 79, afterwards enveloped in loose materials and bearing on its summit a true cone of scoriae. At Etna we clearly distinguish the primitive hill or gibbosity, showing sheets or coats of ancient upheaved lavas on the middle of the slightly arched surface, which all this part of the island presents. It is terminated by an almost level surface, the Piano del Lago, in the midst of which rises the terminal cone of scoriae, regularly circumscribed on all sides, and clearly separated from the base on which it was formed. On the slopes are small cones of eruption formed here and there at different times, which have since contributed to the swelling up of the whole of the surrounding land. It is clear that the cones of scoriae constructed in the manner just mentioned, at the bottom of volcanic gulfs, cannot be very solid. They often change their form at every eruption. Sometimes the edifice rises more and more. Sometimes, on the contrary, it crumbles into more or less considerable shreds, and hence cones are deeply broken in all manners of shape. Sometimes the whole mass is swallowed at once in the abyss it covered, and is reconstructed by subsequent eruptions. This took place in the terminal cone of Etna, which has several times disappeared entirely, leaving an immense aperture, without parapet, in the midst of a little plain which crowned the original gibbosity or hill. At Vesuvius only the upper part of the cone has ever been modified. Interior of craters. Contrary to the expectation of all those who visit volcanoes, the interior of craters seldom possesses much that is worthy of observation. After great eruptions, during which they cannot be approached, these cavities, which are of conical form and have a more or less extensive diameter of the top, with a bottom apparently formed of a sheet of consolidated lava which covers the principal chimney, ordinarily present for observation merely jets of sulphurous vapors, escaping here and there from fissures in the soil, from interstices in blocks of crumbled scoriae, or a greater or less number of small cones raised up in different places. Occasionally we see one or more gulfs, sometimes filled with vapors which escape continually, and sometimes revealing the incandescent lava in the depth, sometimes silent and dark, inspiring with terror, but without possessing the least interest for observation. In long intervals of crisis, traces of volcanic action often entirely disappear. In certain instances even the sides of the crater become covered by vegetation, as is related of Vesuvius before the eruption of 1631. There are, however, some observations worthy attention. The crater of Stromboli, which has been in continuous activity from the most ancient times, still presents phenomena identical with those recorded by Spallanzani in 1788. It is constantly full of melted lava, which alternately rises and sinks in the cavity. Having reached to 25 or 30 feet of the edge, this lava swells, is covered with large vesicles or blisters, which speedily burst with a noise, permitting the escape of an enormous quantity of gas, and projecting scoriaceous matters on all sides. It immediately sinks after an explosion, then rises again to produce the same effects, which are in this way repeated at regular intervals of some minutes. If the lava of Stromboli were less fluid, it is conceived that, having reached to its highest point, it would there stop, assume an arched form, and become consolidated into a more or less elevated cone. And then, if an explosion occurred at a certain instant, a new conical crater would be found in the middle of the old one. This explains what frequently takes place in volcanoes, and, for example, at Vesuvius, where domes have been raised which remained for a long time, and were subsequently broken, giving passage to lavas, and finally sank into abysses left beneath them. Certain craters, having a widely extended bottom, often contain hills of considerable height, which have had an origin such as we have described. Either the lava is arrested at a certain height, in form of a cap, or swelled up at different points, or elevations took place in different matters which had filled the cavity. Sometimes, in place of lava, there is found at the bottom of craters boiling sulphur, as was seen at Volcano, and, on a larger scale, at the volcan of Taal, in the island of Luzon, and at that of Azufral, to the north of Quito, in the Andes. Hills and even domes of sulphur are also mentioned, as M. Bousingot observed at the volcan of Pasto. A crater now often mentioned by voyagers is that of Kilauea on the island of Hawaii, one of the Sandwich Group. This vast cavity is 3½ miles long and 2½ wide, and over 1,000 feet deep. Captain Wilkes, in his narrative of the United States Exploring Expedition, states that the city of New York might be placed within it, and when at its bottom would be hardly noticed. A black ledge surrounds it at the depth of 660 feet, and thence to the bottom is 384 feet. The bottom looks in the daytime like a heap of smoldering ruins. The descent to the ledge appears to the sight a short and easy task, but it takes an hour to accomplish. All the usual ideas of volcanic craters are dissipated upon seeing this. There is no elevated cone, nor igneous matter or rocks ejected beyond the rim. The banks appear as if built of massive blocks, which are in places clothed with ferns, nourished by the issuing vapors. What is wonderful in the day becomes 10 times more so at night. The immense pool of cherry-red liquid lava in a state of violent ebullition illuminates the whole expanse, and flows in all directions like water, while an illuminated cloud hangs over it like a vast canopy. Solfataras. There are a great many craters which for a long time have not given exit to any lava, and are reduced to disengaging, in greater or less abundance, sulphurous gas, which escapes by a multitude of fissures in the soil, and often accompanied by aqueous vapor. Hence the name of solfatara has been given to those places where these phenomena are more or less developed. There are some craters which seem to have been always in this state. Such, for example, is the solfatara of Pusuli in the kingdom of Naples, which is a vast crater of elevation, at the bottom of which are found broken volcanic rocks, daily decomposed by the vapors. This solfatara is of the highest antiquity, and appears never to have presented other phenomena than those now observed. When in repose, volcanic craters become more or less active solfataras. It is not uncommon to find one or more lakes, frequently of great depth, at the bottom of craters and solfataras. The waters they contain are sometimes quite pure, but they are often charged with various salts, or sulphurous or sulphuric acid, as was seen in the volcan of Teshem in the islands of Java prior to 1817, the year when this mountain was entirely destroyed by the action of gas. Commencement of eruptions. Continuous emissions of gas or scoriaceous matter from certain volcans must not be confounded with eruptions, which are sudden events, fortunately transitory, often bringing desolation over an entire country. When an eruption is about to take place, it is ordinarily preceded by earthquakes, after which it suddenly occurs with more or less noise. If a volcan already exists in the country, an eruption begins by pouring out abundant fumes, composed of various gases and aqueous vapor, then pulverulent matter called volcanic ashes, the quantity of which is sometimes immense. Then follow directly, when they do not appear from the beginning, fragments of red-hot porous stones called rapilli or lapilli and puzzolani, more or less considerable blocks of solid matter, which are sometimes ejected to great distances. And lastly, portions of melted matter torn from the lava filling the crater, and becoming rounded by their motion through the air, form what are called volcanic bombs. From all this we have, amidst violent detonations, immense bundles or masses of various matters projected to great heights, lighted by reflection from the melted lava, part of which fall at greater or less distances, according to their weight and the force with which they are impelled. Ashes, rapilli or pumice then produce in the vicinity of the volcan, sometimes even at a distance, considerable deposits, which becoming solid by their weight and by water, form what is termed volcanic tufa, pumice tufa, and various conglomerates. The vapors and ashes ejected from volcanoes sometimes form enormous clouds, frequently dense enough to intercept the light of day, and shroud the whole neighborhood in darkness. These clouds, driven by the wind, are sometimes carried to the distance of 20, 50, and even 200 leagues. This happened in 1812, when the ashes of St. Vincent in the Antilles were carried to Barbados, and so darkened the air that persons could not see their way. The ashes of Vesuvius were carried in 1794 to the end of Calabria, and it was found even in Procopus that during the eruption of 452 they were conveyed as far as Constantinople. What occurs at the bottom of seas during eruptions is not seen, but it is clear that the ejection of earthy matters, rapilli and pumice, are not less abundant, because we find at these times on the surface enormous quantities of them, and in land upheaved there are seen distinctly deposits of volcanic tufa, pumice tufa, and conglomerates, precisely like those formed on land. Appearance of melted matters. The phenomena mentioned are sometimes the only effects of an eruption, but most generally they are only the precursors or sequence of the expulsion of melted matter, which soon appears under different forms. Sometimes these matters, most frequently in mass, rise in cones or domes above the very orifice from which they issued, sometimes entire, sometimes vertically perforated in the center, sometimes susceptible of being pushed further out. This happened at Jorullo and again in the Gulf of Santorin, and the same must occur in a great many other localities. Under other circumstances the crater first formed at the summit of a volcan is completely filled with melted matters. These soon break a passage at a greater or less depth, pouring out torrents which furrow the side of the mountain and run to the plain, where they spread more or less. Form of currents. If fissures or cracks of eruption be formed at the foot of a volcano in a flat country, the lava escaping from it at once forms broad horizontal sheets in the middle of the plain. This occurred in Iceland in 1783. Crevices formed in the plain at the foot of Skaptar-Jökull, a high volcanic mountain of the country, and an immense volume of melted matter escaped from them. This immediately spread over the soil, covering 80 square leagues, filling up all depressions, and forming a vast lake of fire of considerable depth. But this is not always the case. The current often forms on more or less inclined slopes, and the lava forms true currents on their surface, of greater or less length, a part of which adheres to the land in consequence of cooling and in evidence of its passage. After its exit from the bosom of the earth, the melted matter soon cools on the outside, solidifies, wrinkling and cracking in every direction, and thus acquires a crust, ordinarily porous, the thickness of which becomes more or less considerable. This crust prevents the liquid or paste it envelops from spreading, and confines the current to a certain thickness. Also, from its slight faculty of conducting heat, it prevents the interior lava from cooling, which, from this cause, goes on very slowly. Lavas have in fact remained liquid or pasty, and preserved a high temperature for a very considerable time. Some are cited as still running on very gentle slopes, 10 years after their ejection, and others which gave off vapor 26 years after their exit from the bosom of the earth. If after the external cooling the volcanic spring continues to furnish melted lava, the current takes place in a kind of consolidated sack which is formed, a sack which then strives, as it were, in all directions, is broken and mended successively. This causes the twisting and various irregularities in the current of lava. When the source is stopped, the matter which escaped from it does not continue to flow the less in the sack enclosing it, but the latter successively flattens, and the middle is effaced, leaving a more or less elevated roll or ridge on the margins. This is first seen at the upper part of the current, then successively to a point where the liquid matter, becoming more and more viscid, has not sufficient force to drag after it the solid parts formed, to break or push them forwards. The lava then stops at the bottom of the sack, terminating in a club-like mass. The form, direction, and extent of these lava currents vary according to circumstances, such as the degree of inclination of the mountain sides and the nature of the lava itself. Some volcanic products are so pasty they cannot run, but remain over the aperture, as occurs with certain trachytes, which then form more or less elevated domes. Others, such as various obsidians, which seem to cool and harden quickly, are sometimes arrested in form of great tears, even on steep slopes, as at Teneriffe. On the contrary, stony lavas, which cool slowly and long remain fluid, are not arrested except on a horizontal plane. Various characters of the same lava. From what has been stated, it is certain that lavas cannot accumulate to a great thickness, or spread in sheets, except on a horizontal plane. The structure of lava depends, in a degree, on its external arrangement. The vein which is behind the current on a very steep slope is, in parts, thin, scoriaceous, corded, and always very porous. On less steep slopes, the surface of pieces is more united, the pores are smaller. On descents at an angle of from 3 to 5 degrees, the dislocated parts are in plates of greater or less thickness, the structure of which presents a certain uniformity, and the center is sometimes a little more compact if the thickness is sufficient. In great flows causing great accumulations on plains, where the depressions are filled up, all the inferior part becomes a compact and, more or less, crystalline mass, which is porphyritic, because then it cools slowly and tranquilly. In this case it is frequently divided, through its whole height, into columnar masses, generally normal on the cooling surfaces, and porous at the upper part only. This is seen at Vesuvius and Etna, where the lava is very thick, and at Iceland in the immense deposit formed by the eruption of 1783. Veins of lava, or dikes. It frequently happens that in volcanic eruptions there is formed, on the sides of the mountain, crevices of greater or less breadth, through which the lava comes to the surface of the soil. These cracks are remarked for a long time after their formation, either from remaining partly open, or from the rapilli with which they are filled, leaving a kind of ditch which may be readily followed. They may be also recognized by the partial and crateriform excavations of these debris, which all have the same line of direction. Sometimes they are distinguished by rolls of scoriae on the edges, which escaped while the lava was boiling in the interior. They also exhibit conduits of lava which unite to each other the different cones of eruption formed on their line of direction. It cannot be doubted that these cracks remain partly filled with the lava to which they gave passage, giving rise to veins or dikes. Sometimes the lava flows above the crack or fissure, forming sheets on the surface. Sometimes a coat or bed of lava is found in evident communication with a dike, which, after having passed up through all the lower deposits, stops in the middle of it. And it is not rare to find several beds of lava lying one above the other, each one corresponding with a particular dike, to which, no doubt, it owes its origin, the most recent of these dikes or veins being the one which has passed up through all the inferior beds or tables to form the upper one. The matter that constitutes dikes is rarely porous, except sometimes on the sides towards the rock encasing it. It is frequently even of a finer grain than the table or bed in which the dike terminates. Its mass is sometimes divided into prisms perpendicular to the sides of the fissure, which were the cooling surfaces. This matter generally resists atmospheric influences, and it frequently happens that the surrounding rock being degraded, carried away by external agents, the dike remains projecting on the side of the escarpment, or even rising out of the earth like a wall. Gaseous volcanic products. Volcanic phenomena are accompanied by the production of great quantities of various gases, some permanent, others condensable or soluble. These products consist for the most part of watery vapor, but they are found to contain also various acids and other matters sublimated from the volcano. Most of these gases are fatal when breathed. Gases, always at a high temperature and mixed with the vapor of water, act powerfully on the solid surrounding matters. They disaggregate and decompose them in all ways, reduce them to powder, to mud, and form new compounds of every kind. This happens in all solfataras, where it is often necessary to be cautioned against falling into masses of muddy matter, which is sometimes very hot. But nothing is comparable in this respect to the volcans of Java. The acid and aqueous vapors, which are there in great abundance, destroy the rocks and form a paste of them, which speedily becomes incapable of resisting the explosive action of the interior. These fearful eruptions take place, not of lava as in ordinary volcanoes, but of enormous masses of boiling water, charged with sulphuric acid and thick mud, which destroy everything in their way, and cover the whole country with a sulphurous slime, the matter of which is called buah. This happened in 1822 on the eruption of Galunggung, which, with earthquakes and horrible noises, was considerably sunk, truncated at the summit, and entirely overturned. Torrents of hot sulphurous water and mud issued from rents in the side of the mountain, and many inhabitants were swept away in the waters or buried under deposits of mud during the 8th and 12th days of October. Muddy eruptions of Quito. The volcans of Peru, which like those of Java have rarely produced lavas, vomit from their sides torrents of mud called moya, sometimes sulphurous like the bua of Java, at others carboniferous. This happened in 1698, when the volcan of Carguaraizo crumbled, covering more than 2,500 square miles with mud, and in 1797, when the village Pelillo, near Riobamba, was buried under a mass of black mud, etc. What especially characterizes the eruptions in Peru, and makes them very strange, is that the muddy waters which spring from the bosom of the earth are filled with small fishes, species of which live in the neighboring lakes, and the quantity of them has been sometimes so great as to excite epidemic diseases by their putrefaction. Gases disengaged from lavas. It can be readily conceived that gases and matters of various kinds may be disengaged from the bowels of the earth, through fissures communicating with its surface. But what is most remarkable, they are also disengaged from lavas, although on leaving the volcano they have no properties in common. As long as the lava is fluid and at a high temperature, nothing escapes from it, but the moment it begins to harden, and consequently to cool, gases are disengaged in more or less quantity. Streams, matters which fill the lowest levels, then constantly emit the vapor of water, hydrochloric acid, sal ammoniac, which are deposited on the surface, to say nothing of realgar, iron, etc., which are sometimes sublimed in the fissures or cracks. Consequently, the lava itself must contain these matters, which remain engaged in it, we know not how, while the mass is fluid or pasty, and which are disengaged just in proportion as it solidifies and cools, and in a manner which leaves no aftertrace. It is supposed that all these matters give to porous lavas the power of preserving their fluidity for a much longer time than similar substances artificially prepared. Solid products of volcanoes. All the solid substances which volcanoes produce in great abundance belong to the group of silicates, generally anhydrous silicates, and particular to that division of those confounded under the name of feldspar. These are generally compound rocks, and substances more or less mixed, the principal base of which it is difficult to separate, and therefore they cannot be accurately classified. We are forced to resort to artificial divisions. First, trachyte, from the Greek trachus, rough, is a rock often rough to the touch, and its name indicates, composed of albite or rhyolite, sometimes compact, of a ceroid or vitreo-resinous and occasionally earthy luster, sometimes crystalline, the mass being finely porous, containing crystals of the same substances, and often also hornblende and black mica. Albite, from the Latin albus, white, a mineral so called from its color, which contains silica, alumina, and soda. A lamellar variety is found at Chesterfield, Massachusetts, called Clevelandite, in honor of Professor Cleveland. Rhyolite, from the Greek ruax, a stream, and lithos, stone, is a glassy mineral of a grayish yellow to white color, or colorless. Besides silica, alumina, and soda, rhyolite contains potash. Hornblende, from the German, a kind of dark or black variety of mineral, belonging to the same group as tremolite, actinolite, asbestos, etc. Mica, from the Latin mico, I shine, is a mineral generally found in thin, elastic laminae, soft, smooth, and of various colors and degrees of transparency. It is one of the constituents of granite and its associate rocks. Second, obsidian, from the Greek opsis, view, or after Obsidius, who first found it in Ethiopia, is a homogeneous, vitreous substance of various colors. By the ancients it was used in place of glass, and is also called volcanic glass. It consists of silica, alumina with a little potash, and oxide of iron. This substance is produced abundantly in the islands of Lipari and Tenerife, the volcans of the Andes, and wherever volcanic apertures open in trachyte. Third, compact lava. A substance with a compact base of a deep color, most frequently formed of labradorite, containing crystals of the same substance, or of the feldspathic group in general, which in the mass presents a more or less distinct porphyritic structure. Crystals of pyroxene or amphibole, black mica, and peridote are also occasionally found. Labradorite, Labrador spar, a beautiful variety of opalescent feldspar from the coast of Labrador. It exhibits brilliant and mutable tints of blue, red, green, and yellow, and is susceptible of a good polish. It is cut into small slabs and employed in ornamental jewelry. It is a silicate of alumina, lime, and soda, with traces of oxide of iron. Pyroxene, from the Greek pour, fire, and xenos, stranger. The augite, supposed to have pre-existed in the volcanic minerals containing it, and not to have been formed by fire. Amphibole, from the Greek amphibolos, equivocal. A name applied by some mineralogists to hornblende because it may be mistaken for augite. Peridote or chrysolite, from the Greek chrysos, gold, and lithos, stone, from its color, the topaz of the ancients. These substances constitute the center of thick currents, the inferior part of the mass formed in excavation or hollows. They are often divided into prismatic columns. Fourth, porous or scoriaceous lava. A substance of the same nature as the preceding, but rarely having crystals embedded in it, and its structure is porous or cellular. These lavas constitute the upper parts of thick layers, and envelope lava currents and streams which rest on the surface of the ground. Fifth, puzzolani, volcanic tufa. Masses of small scoriaceous fragments or rapilli accumulated around volcans, or earthy substances which contain them in a greater or less quantity. Pumice tufas are formed of fragments of pumice, and trachytic conglomerates of fragments of trachyte united by crystalline or earthy cement. Sixth, to these may be added scoriae in tiers, irregular stalactites scattered on the surface of volcanoes, and volcanic bombs, which are sometimes found at considerable distances. Volcanoes furnish annually but a small quantity of materials to the solid crust of the globe, and the upheavals they cause produce very slight change in the elevation of countries where their action is manifest. Nevertheless, if we remember that a great number have been in action since the time of history, and observation shows that a great many more were previously in action, we are led to the conclusion that volcanic substances are important, and their presence must have occasioned great modifications on the surface of our planet.
Lesson 7, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Thomas Bosk. Elements of Geology by William Ruschenberger. Lesson 7. Influence of external agents on the surface of the earth, light, air, and water. Part 1. Atmospheric effects. Variations of temperature, the air, winds, dryness, and moisture act very perceptibly on most mineral substances. There is not a rock on the surface of the earth which does not present an appearance externally totally differing from what is seen internally when it is broken. This is everywhere seen in escarpments formed by making roads, in mountainous countries, where it is necessary to cut through rocks. The exterior is discolored, and more or less extensively disaggregated, compared with the freshly exposed interior. These effects are not solely produced by a great lapse of time. A few years are sufficient for them to be shown, not only on the surface, but to considerable depths. These effects are seen in ancient quarries of marble, or of certain granites, and in dressed stone. The effect is more rapid and perceptible, in proportion to the susceptibility of the substance to imbibe moisture, and to dry again. Alternations which produce a very rapid disaggregation, when frequently repeated, as is generally the case in mountains. The substances which degrade most easily are those of a granular structure, either earthy or crystalline, those of a foliated structure, or compact masses, fractured and split on the surface, such as are often seen in mountains. Frost, when it attacks water absorbed by a body, is also a powerful cause of destruction, because the expansion consequent upon it produces a multitude of cracks in all directions. As long as the cold continues, its parts are held together by ice as by a cement. But when a thaw comes, the whole falls in scales, grains, or dust. Mountains cannot be visited without meeting evident traces of degradation of this kind. In limestone escarpments, we see parts of loose texture more or less hollowed out, and the more solid banks remain. Hence the falling of the latter, which are successively detached in more or less voluminous blocks. In high mountains, often formed of inclined strata, which present their cuts or planes to the slope, we observe the most marked degradations. Parts are constantly detached, particularly at times of most sensible atmospheric variations. At the instant of thaw, enormous avalanches of stones occur, and roll down the sides with astonishing rapidity, sweeping everything in their course. Sometimes great blocks and considerable portions of the mountain fall with tremendous noise. Hence the enormous debris which accumulate at the base, sometimes covering a great extent. Degradations attributable to these effects. The degradation which many rocks present is generally attributed to atmospheric influences, long continued. Almost all rocks, in fact, are more or less deeply changed, and are in a state of much less solid aggregation, much less homogeneous on the surface, than they are internally. In almost all quarries, it is necessary to remove a great mass of matter before obtaining blocks which are homogeneous, solid, free from cracks, and possessed of the bright colors which are ordinarily sought. This is especially the case with marble, and generally also with compact limestone. Certain granites are so deeply disintegrated that the whole surface of the soil presents a mass of gravel in rounded hills, gullied by the rain in all directions. Frequently we find these granites on the surface of the soil, in great rounded blocks, piled up one on the other in the strangest manner, sometimes in unstable equilibrium, and susceptible of oscillating from the slightest effort. These are termed rocking stones in some localities. In mountains where the granite is easily decomposed, we often remark that the mass, more or less cut, is in a sort of horizontal stories, divided by vertical fissures, so as to present a kind of agglomeration of irregular parallelepipeds. It is supposed that, in consequence of atmospheric influences, these angular blocks are altered on their faces and angles, that the disaggregated parts are successively detached, producing round masses, piled on each other like cheeses, as we now see, sometimes isolated on the surface of the soil. Action of winds, dunes. Although winds act but very feebly on solid mineral masses, they exert an important influence on deposits of fine movable sands. We know that in the deserts of Africa and Arabia, the winds raise immense clouds of burning sands, conveying them from place to place, and suddenly producing vast hills, sometimes quite high, which a new gale again destroys. All sandy sea coasts are exposed to similar effects. The least gale sets the sands in motion, and produces, on the previously uniform surface, a multitude of wrinkles or ridges, parallel to each other, separated by a greater or less interval, and each presenting a gentle slope towards the wind, and a more abrupt declivity on the opposite side. The next gust of wind sets all these ridges in motion, and each one is soon found to occupy the space which separated it from the preceding ridge. This phenomenon of dunes or downs is seen in miniature on the sea beaches, and they sometimes invade immense tracts on adjacent plains. These hills, placed one behind the other, in a direction perpendicular to that of the prevailing winds, are constantly in motion, and constantly advance towards the interior of the land. The wind from seaward drives the sand from the foot of the hillock to its summit, whence it falls in the line, forming at this point a falling talus, always more abrupt than the first or rising talus. The result of this is a single hillock, taken separately, which grows behind, if new sands be furnished in front, or it is displaced, if the same sands are continually removed. Now, the wind acting on all these hillocks at the same time, the mass formed by them is found to have moved a certain distance inland, in a short time, while new heaps are formed in front, at the expense of the sands freshly washed up from the sea. It is calculated that dunes advance, in this way, 20 or 30 yards a year, so that it is evident there must have been a time when they were far from the places they have invaded. A great many localities are known, which have been submerged by the seas of sand. Lightning sometimes produces remarkable effects. In a great many places and on various rocks, traces of fusion by thunderbolts in high mountains have been observed. According to the observations of Friedler, when lightning penetrates sand, it often forms narrow, irregular canals to a great depth, the sides of which are consolidated by the fusion of quartz itself, and there are instances where considerable portions of rocks have been turned round, torn from their places, and hurled to great distances by lightning. Effects of water. Water plays a very important part in the changes which are taking place on the surface of the globe, sometimes by its dissolving power, but more frequently by its softening action, its weight, and especially by the motion that may be communicated to it, and by the transporting power resulting from its rapidity. The extent and importance of modifications from this agent ought to be understood. Dissolving power. Water exerts a chemical action on some substances which it dissolves, either directly or by means of the carbonic acid it may contain. It acts directly on some salts which it meets here and there, or on some deposits of sulphate of lime, which it corrodes in various ways. When more or less charged with carbonic acid, it acts on calcareous rocks, either underground or where they crop out on the surface, or in high mountains at the time snows are melting. In this case, the water generally possesses itself of the carbonic acid contained in the air, in greater quantity than at other times, in consequence of its low temperature. And running over calcareous masses, it forms furrows which gradually deepen, and sometimes cause very considerable falls of rock. These slow effects of water are particularly remarked in the Alps and Pyrenees, where the snow remains a part of the year, and melts by degrees in the fine season. Softening power. Water, by penetrating argillaceous beds, sometimes softens them so much that they cannot remain on the slopes they occupied, and fall from their own weight. This is the cause of many falls or slides in sedimentary formations. One of the most remarkable catastrophes of this kind happened in 1806 at Rufeberg or Rossberg in Switzerland, after a very rainy season. The argillaceous matters which cemented the rolled flints forming the mountain becoming softened, a mass of more than 50 million of cubic yards was suddenly detached, and precipitated into the valley, forming it in hills 60 yards high, and burying several villages under masses of mud and flints. We often see, on a small scale, thick beds of rock gently slide to the bottom of valleys, on softened argillaceous beds which supported them, and tranquilly displace plantations and even the inhabitants on them, without the proprietors perceiving it at the first moment. Waters which filter through rocks to argillaceous layers which may arrest them, and on the plane of which they are directed to the surface, sometimes soften these substances also, carrying away parts successively, and especially sands that may rest on them, laying bare in this way underlying beds. This is termed denudation. There results from this, at the point where the water breaks forth from the declivity of hills, more or less extensive voids, which leave the solid superposed masses without support, which are then dislocated in different ways, and soon overthrown. This is frequently seen in certain escarpments, at the base of which are found argillo-arenaceous layers which conduct the springs externally. Erosion. Something analogous happens when waters, which washing the foot of a mountain, meet there with substances that they can easily soften or disaggregate. These substances being destroyed, the upper parts of the soil are soon undermined, and more or less considerable falls occur. This takes place on sea coasts, on the shores of lakes or rivers where more or less elevated escarpments are formed, and more degraded. The same thing happens sometimes at the foot of cascades which fall over rocky peaks, forming alternately calcareous and argillaceous deposits. The latter are disaggregated, and borne away little by little by the waters which exude on the parietes or jet forth after the fall, and other layers being undermined must fall sooner or later from their own weight. In this case the cascade cuts deep into the soil, and the same being successively repeated, necessarily forms a gorge or bed the whole length of the rivulet, which deepens more and more. It is in this way that the Falls of Niagara, by which the waters of Lake Erie are precipitated into those of Lake Ontario, have sensibly receded since the discovery by Europeans, and probably have excavated the deep bed through which they afterwards escape. The waters, after cutting through strata of limestone, about 50 feet thick in the rapids, descend perpendicularly at the Falls of Niagara, over another mass of limestone about 90 feet thick, beneath which lie soft shales of equal thickness, continually undermined by the action of the spray, driven violently by gusts of wind against the base of the precipice. In consequence of this disintegration, portions of the incumbent rock are left unsupported, and tumble down from time to time, so that the cataract is made to recede southwards. The sudden descent of huge rocky fragments of the undermined limestone at the Horseshoe Fall in 1828, and another at the American Fall in 1818, are said to have shaken the adjacent country like an earthquake. According to the statement of our guide in 1841, Samuel Hooker, an indentation of about 40 feet has been produced in the middle ledge of limestone at the Lesser Fall since the year 1815, so that it has begun to assume the shape of a crescent, while within the same period the Horseshoe Fall has been altered so as less to deserve its name. Goat Island has lost several acres in area in the last 4 years, prior to 1841, and I have no doubt that this waste neither is, nor has been, a mere temporary accident, since I found that the same recession was in progress in various other waterfalls which I visited with Mr. Hall in the state of New York. Some of these intersect the same rocks as the Niagara, for example, the Genesee at Rochester. Others are cutting their way through newer formations, Allen's Creek, below Leroy, or the Genesee at its upper falls at Portage. Mr. Bakewell calculated that, in the 40 years preceding 1830, the Niagara had been going back at the rate of about a yard annually. But I conceive that 1 foot per year would be a much more probable conjecture, in which case 35,000 years would have been required for the retreat of the falls from the escarpment of Queenston to their present site, if we could assume that the retrograde movement had been uniform throughout. This, however, could not have been the case, as at every step in the process of excavation, the height of the precipice, the hardness of the materials at its base, and the quantity of fallen matter to be removed, must have varied. At some points it may have receded much faster than at present, at others much slower, and it would be scarcely possible to decide whether its average progress has been more or less rapid than now. Lyell's Travels in North America. Effects of weight. Water, acting by its own weight, like other bodies, evidently often contributes to such landfalls as we mention, and also exerts a powerful action on the dikes and barriers which retain it. We see the unhappy effects of inundations, to which certain countries are subject from their vicinity to rivers, lakes, or seas, retained by natural or artificial dikes. Action of running waters. To the softening action and weight of waters is often added a new power, from the motion they acquire by running over steep descents. This force is sometimes prodigious. The effects are seen after storms which pass over movable substances, in the deep ravines found to have been excavated. These effects are in proportion to the mass of water, and the rapidity of its motion on a particular point. When a hurricane or violent storm bursts on a mountain, the soil is often found, unless it consists of living rock, removed and gullied to great depths. The numerous fissures on the surface of rocks facilitate the action of waters, and a considerable mass of fragments is soon detached, which increase more and more the destructive power of the current. Then blocks of every size are loosened, torn from the mountain, and transported to great distances, multiplying the effects 10 or even 100-fold, in proportion to their mass and rapidity of motion. Hence we have great ravines on slopes that were previously unbroken, and an immense accumulation of debris at the foot of the mountain, and especially where the soil or the swiftness of the stream abated. Torrents swollen by circumstances of this kind, or by the sudden melting of snows, also produce frightful ravages. They sweep everything in their way, even the living rock, which they soon attack forcibly by the fragments and blocks they swiftly urge along. Nothing is more terrible than this kind of watercourse, and to form an exact idea of the effects one must see a gorge through which it has passed, sometimes rolling along rocks measuring 10 or 15 cubic yards. Debacle of lakes. Lakes which sometimes form in valleys, by avalanches or falls of land, constituting a barrier which retains them, are most fearful in their debacle, sudden escape of their waters from breaking of their barrier, in consequence of an enormous mass of water rushing forth in a few seconds. Scarcely does a flow begin through a few rents, before the first opening rapidly enlarges, and in an instant the whole dike is carried away. An enormous volume of water is then precipitated with extreme violence, and nothing can withstand the combined effects of its mass and rapidity. All is overturned, and the most solid rocks, if they project, in the least, across the direction of the current, are instantly torn away, broken, and transported to great distances. The clearing is so complete at the origin of the current, and in the narrow passages where the slope is rapid, that the exposed rock seems to have been cut by the hand of man. Mud torrents, from one cause or another, are also formed, which are not less terrible in their ravages. It sometimes happens, as in Ireland, that turf beds placed on a slight declivity, after being swelled, more or less arched by retaining rain-water beneath them, cannot resist the first heavy shower, and are set in motion. They run then, in spite of the consistence of the mud, and the gentleness of the descent, with prodigious rapidity, and sweep everything they meet. Under other circumstances, the rain-waters soak in loose, argillaceous substances, accumulate in the midst of them, and, at a certain moment, the dikes of the reservoir give way, and a torrent of thick mud, filled with fragments of rock and even blocks, suspended in the viscid mass, is formed and rushes with fearful rapidity, overturning everything, and cutting deep ravines. Slopes of torrents and rivers. The disastrous effects of torrents are in proportion to the descent on which they move, but it does not necessarily follow that their bed must have a very considerable inclination. The most rapid torrents, forming a continuous bed and carrying rocks a half-yard in diameter, have a descent of only 1 or 2 degrees, and many rivers flow very swiftly on a much less slope. A descent of from 3 to 4 minutes, 60 to a degree, is about the limit for navigable rivers. Rolled flints or pebbles. In the ravages produced by water currents, the debris torn from mountains are transported to a greater or less distance, accordingly as the inclination of the soil permits the current to maintain its force for more or less considerable distances. But in proportion as the slopes diminish, the swiftness decreases, and the larger blocks successively remain behind, at the bottom of the valley, and then those of smaller size, and successively the sand and mud, which are often carried enormous distances. In this rolling of different substances, the blocks and fragments sinking during their transportation, rubbing against each other and against the soil, gradually lose their prominences and angles, and in the end become completely rounded, forming what are termed rolled flints, which may be more or less voluminous. All the lower parts of torrents, where the soil is sufficiently flattened, where the enlargement of the valley permits the waters to expand, diminishing their depth, and consequently their rapidity, is generally found covered with these flints, which are sometimes accumulated in immense quantities, and through which, in its ordinary course, the stream meanders in different ways, in a bed it forms and often changes. Rivers and lakes into which torrents empty, and where they consequently lose their swiftness, are often loaded with these flints, and this is the cause of the constant elevation of the bed of the river Po. Gravel and sand, which are merely small flints, the mud which results from their friction, and the earthy particles removed, are always transported far, either immediately into lakes or seas or rivers, which deposit them on their banks, and especially at their mouths, which they more or less obstruct. Rolled flints or pebbles are also formed by the action of the waves on fallen rocks. In this way, on the coasts of France and England, the silex, or flints of the chalk are rounded by being rubbed against each other, and constitute considerable banks of pebbles or shingle. Something similar must have taken place at points now far inland, where we find blocks round and smooth, at a short distance from rocks from which they were evidently detached. Transportation by ice and glaciers. On the shores of northern seas, the ice envelops blocks and masses of rocks, which, at the breaking up, are floated away on ice cakes in all directions, and deposited here and there, wherever they may ground, or fall to the bottom of the sea. In this way, in Canada, Greenland, and on the coasts of Nova Zembla, etc., very voluminous blocks are transported from one place to another, and often to very considerable distances from the point of departure. There is no doubt that many small debris, embedded in the ice, are transported in the same way, and form adventitious deposits of more or less extent. Glaciers, that is, beds of ice occupying the high valleys of lofty mountain chains, are also very remarkable means of transportation. Various circumstances, their great weight chiefly, keep these deposits in constant, though very slow motion, from half an inch to an inch an hour, descending along the slopes on which they rest. Now, the surface of these glaciers is found to be covered with fragments and blocks which have fallen from the surrounding mountains, and the whole is conveyed from the upper to the lower part, and blocks, often of enormous size, are carried without friction to considerable distances from their place of origin. These debris, from several causes, always accumulate on the lateral parts of the glacier, against the side of the valley, and frequently in the middle also, from other valleys emptying laterally into it, from which result long, slender hills, designated under the term moraines. All these debris, having reached the inferior extremity of the glacier, tumble into the valley on its slope, and form at its foot other moraines, often of considerable height. If, after having increased for a certain time in consequence of a series of cold summers, the glacier diminishes again by a succession of warm, prolonged summers, the moraines of different kinds, abandoned by the ice, are left on the soil. Some form dikes, of more or less height, at the bottom and across the valley, and others long lines on the flanks of the valley, at a greater or less elevation. It must be borne in mind that the slopes on which glaciers move are always much greater than those of rivers, and that they never descend at an angle of less than 3 degrees. This must also be the minimum slope of masses of debris resting on the sides of the valley, in consequence of the rapid melting of the glacier. Thus we have a means of distinguishing the remains of lateral moraines from deposits which have been made by water currents, the slopes of which are very much less. Striae, channels, polishing of rocks. Among the effects produced by the motion of a glacier loaded with debris, and moving slowly over the exposed face of a rock, is a rubbing, wearing, and polishing of the surface which it passed over. The angles of the rocks passed over are rounded. Deep undulating grooves, nearly parallel and longitudinal, are cut in the surface, and the polished surface of the rock passed over is scratched with fine striae, even when it is of the hardest Lesson 7, Part 2 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Thomas Bosk. Elements of Geology by William Ruschenberger. Lesson 7. Influence of external agents on the surface of the earth, light, air, and water. Part 2. Action of the waves and of tides. Waves exert an enormous power, particularly where rocks are abrupt and directly exposed to the open sea. The shock is sometimes so great that the earth trembles beneath the feet. Great blocks of stone are torn up and carried far inland, pushed up against the inclination of the shore, sometimes thrown up vertically on projecting points, where they afterwards roll about like small pebbles. Heavy banks of sand and of shingle are often removed, and entire countries have been in a moment destroyed. Chronology and tradition of maritime countries furnish numerous instances of successive changes, of instantaneous disasters which have occurred in a great many localities. Immense ones have taken place, and every day new ones occur on low, sandy coasts bordering the sea in many parts of the world. We have famous examples from the mouths of the Scheldt to the Canal of the Jutland, or the Biesbosch. The Haarlem Sea, the Zuiderzee, the Dollart have been produced in the extraordinary eruptions of the ocean. Where numerous changes have taken place in the islands, from the Texel to the mouths of the Elbe, in the windings of Limfjord, or on the coasts of the Kattegat and of the Baltic. Immense cuts, bays, and deep gulfs are formed during tempests, and these are still daily forming by the ordinary action of the waves, which sometimes carry away banks of sand, and sometimes destroy the dikes they had already formed. The action of waves is not confined to movable soils, but takes place on the most solid rocks, and hence those daily modifications in the enormous precipices found on the coasts of France, England, and almost all parts of the world. The more abrupt the coast, the more it is exposed to the denudation from the waves, because directly breaking them, the shock is felt in all its force. On flat coasts, on the contrary, the waves meeting with no obstacle, advances as long as its force lasts, and until its rapidity is sensibly lost, and it carries up in sand and pebbles much more than it destroys, even on the most movable soils. The natural disposition of solid beds is sometimes opposed, and at others favorable to the action of waves. It is opposed when the beds, being uniform and homogeneous, incline towards the sea, because the return of the wave along the slope or talus diminishes the action of the succeeding wave, the remaining force of which is spent in merely ascending the plane. The waters are spattered only by the crevices and fissures that may exist in the rock. But the same is not the case when the soil presents an escarpment to the action of the waters. The lower parts, continually attacked by reiterated shocks of waves, which nothing contributes to diminish, and degraded and excavated successively, and with a rapidity in proportion to the facility with which the substance is disaggregated, the upper beds being soon undermined, are not long in being precipitated into the sea. In this way considerable portions of coast have been overturned at different times, promontories have disappeared, and others have been cut off and separated from the mainland. These effects are more rapid in places where a deep sea swallows up detached blocks, or in those where the force of the waves is sufficiently powerful to break up the debris, and wear them one against the other, and successively remove them, so that the foot of the escarpment always remains bare. When masses of debris falling from precipices are not immediately removed, a natural rampart is formed against the action of the waves, which break before reaching the foot of the escarpment. Then it is only in a long time that the debris are worn, rounded, and carried away little by little, depending on the solidity of the rocks of which they are formed. These natural ramparts are imitated as much as possible by piling rocks before the talus we wish to preserve on sea coasts or river banks. To the action of waves must be attributed certain excavations frequently found, on a level with the sea, in calcareous precipices, as well, perhaps, as the arches of greater or less height which traverse certain promontories. Nevertheless, this action does not immediately produce great results, except on matters easily disaggregated, such as chalk, clay, and arenaceous substances, and it is infinitely slow on more compact and harder substances. In fact, there are points where no effect whatsoever has been produced within historic times. The erosive power of water does not explain all these facts, nor even the impetus force of waves. The soils on which this power is exerted are cracked in all directions, either by previous action or at the moment of earthquakes, accompanied by violent agitations of the sea, and it is then they yield to the combined forces to which they are exposed. By this means we can account for isolated rocks, for islands in the vicinity of continents, for those great gaps through which the sea finds passage, for those groups of split rocks which form shoals in the midst of the sea, and for all those severings so common and varied on the coasts of France and England, in numerous islands that extend towards the North Sea, and in a great many localities. Deposits of detritus formed by waters. Although waters continually degrade certain parts of the globe, they create in a measure new deposits proportioned to those they remove. Torrents, after having torn away blocks and fragments of rocks, reduced them to rolled flints or pebbles, and carried them to a greater or less distance, deposit them, in proportion as the swiftness of the water diminishes, in the inferior parts of valleys they run through, or at the confluence with rivers or in lakes. Hence the masses of debris, sometimes immense, the coarse parts of which are cemented by the mud, they deposit at the same time. Great rivers, running through valleys of little inclination, generally leave behind the coarser parts they have received, and only bear forward those whose weight is in relation to their force. But as their slope diminishes more and more, becoming almost insensible towards the end of their course, they deposit the matters they carry, and in this way generally elevate their bed, and finally they even bar up their passage, and divide into several branches, each of which cuts its way through sands. Rivers have, in this manner, covered flat countries through which they pass with sand to a considerable depth and extent. In great freshets these sands are often taken up again, transported from one point to another, forming islands in the middle of the river, or alluvions on one of its banks, while the other is hollowed out. In rivers, lakes, or seas, these deposits become most remarkable. There, if the current is not rapid enough to carry the debris to a distance, in spite of the opposition of tranquil waters, or if the waves have not sufficient force to remove the sands and mud which have been deposited, they form deltas at the mouths of certain rivers. The sea itself, which in so many places has made breaches in the mainland, in others heaves up and accumulates enormous quantities of pebbles, formed by the trituration of rocks fallen from precipices, or masses of sand and mud produced by the waves, or brought down by the rivers. In this way, banks and beaches of greater or less extent are formed on coasts, the finer parts of which, carried inland by the wind, form dunes. There are many places where accumulations of this kind are daily formed, and many points of coast have been invaded by deposits from the sea from remotest times. Sometimes, by a single eruption, entire kingdoms have been covered by sand, and fertile countries changed to arid plains, either in extraordinary tides or in tempests, or by the sudden displacement of waters consequent on earthquakes. Low countries, exposed to these alluvions, daily grow at the expense of the waters, and at certain points this growth has been estimated at several yards a year. Bays and ports have been filled up in this way. Buildings and towns, formerly situated on the seashore, are now far from it. Lakes have been transformed into marshes, marshes into solid land, and islands joined to the main by sands deposited around them. The sea, in some instances, contributes to the growth of deltas. Torrents and rivers transport not only mineral debris, but also organic remains, immense masses of plants detached from ravines or by falls. Here and there, great masses of materials are formed, especially in rivers which are bordered by immense forests. Great deposits of debris of this kind are formed in the Mississippi and its tributaries. They there form immense rafts of trunks of trees, interlaced, which are stopped here and there by the sands, and eventually are buried under the enormous alluvions daily deposited. The mass of plants that the river carries is so considerable that it has been estimated at several thousands of cubic yards per hour. Currents of the sea also often transport immense masses of various vegetables, marine plants, and organic debris of every kind and from all climates, which are here and there deposited in the bays these currents meet in their course. This is especially the case as regards the great Atlantic current, the Gulf Stream, the strongest and most considerable of all, which extends along the coast of North America to the icy regions, where the polar currents accumulate these debris with those of other parts of the world. We cannot doubt, on reflecting on the quantity of debris borne by the waters, that lakes which receive rivers are filled up, little by little, by the matters daily brought into them. This is evident in some places, where marshes and considerable alluvions are thus formed. The same must be true of the bottom of the sea, where all waters finally come. It is easy to conceive that there must be daily formed considerable deposits of all the substances which are carried there, as well as those washed away by the waves, and of all the remains of animals which perish in this vast abyss. Deposits of substances held in solution. Waters degrade and carry away different substances. Some they also dissolve, and afterwards deposit them, by evaporation, in form of solid sediments, which are sometimes more or less crystalline. To the infiltration of these waters, for example, is due all kinds of stalactites, from the Greek stalasso, eye drop, which form in various subterraneous cavities, and especially large in caverns found in calcareous countries. Certain waters are rich in dissolved materials, and sufficiently abundant to give rise to extensive deposits on the surface of the earth. Those particularly, which by carbonic acid hold a great quantity of carbonate of lime in solution, and which, from abundant or numerous springs, give origin to rivulets and even lakes, at the bottom of which is daily formed what is called travertin, or calcareous tufa. These waters are met almost everywhere in calcareous regions. Scattered over a flat country, or on the slope of a valley, these waters encrust the plants growing there, and from these agglomerated and superposed incrustations are formed considerable rocks, the mass of which is consolidated by waters which percolate the interstices they meet, and render the whole solid and uniform. When these waters flow over slopes free from vegetation, they deposit thin and successive layers, following the undulations, the whole forming compact masses which daily grow in thickness. In lakes into which waters of this kind flow, horizontal beds of solid calcareous matter are formed, which are often filled with fluviatile and even terrestrial shells, daily brought into it. Sands washed up by the waves, either in fresh water lakes or seas, are daily consolidated by waters more or less charged with carbonate of lime. Examples of this kind are seen in the sands of Lake Superior, in those of the Gulf of Messina, at several points on the coasts of England, of the West India Islands, chiefly at Guadeloupe, New Holland, etc. These arenaceous substances often become sufficiently solid for building purposes. Siliceous deposits. A great many mineral waters, particularly those which are warm or hot, contain, besides carbonate of lime, a certain quantity of silex. from the Greek chalis, a pebble. On this account, many calcareous tufas are more or less siliceous. But there are springs in which the silex is sufficiently abundant to form considerable deposits of hydrated siliceous deposits, sometimes nearly pure, and sometimes mingled with other substances. The tufas of the geyser in Iceland are deposited for nearly a quarter of a league round the spring, 3/4 of a yard thick. One of these geysers, a word which according to some means spouting and furious according to others, spouts up every half hour a column of boiling water, 18 feet in diameter and 150 feet high. Analogous springs of hot water exist in the Rocky Mountains and in India, as well as in St. Michael's, Azores, where the siliceous deposits are found in thin beds, alternating with argillaceous substances which the same waters bring from the interior of the earth. Organic remains, particularly vegetable, are found in all, some of which have passed into the siliceous state, while others have disappeared, leaving only their impressions behind. Structure of sedimentary deposits. Effects of landfalls. If we examine deposits of detritus formed at the foot of mountains by the daily destruction of its rocks, it will be seen their slopes are very variable, the greatest not exceeding an angle of 45 degrees, and the least being seldom less than 20 degrees. The variations between these limits are found to be in relation to the size, the form of the fragments, and circumstances of the fall, rather than to the nature of the substances themselves. Hence it is, if, at different successive fallings, there are variations in the form of the fragments and in the circumstances of the fall, there will be an accumulation of deposits, the slopes of which will be successively less, and which, in ravines excavated by water, will have nearly the arrangement represented, where each additional deposit is thicker at its base than at the upper part. It is evident the same thing may take place in stagnant waters, whence it follows that from the fall of a river into a lake with steep banks, a very considerable talus may be formed, and from different accessions or growths, which bring materials of different form and size, deposits similar to those just mentioned may be produced. Effects of transport. If in some places, even under water, beds may be deposited at an inclination of from 20 to 45 degrees, it must not be inferred that the same is true of extensive deposits, where running waters, if unimpeded, may force the debris in every direction. Here the inclination of the talus is much less. They never attain even the minimum angle of slopes formed of fallen matter, and never reach even 10 or 12 degrees, only in exceptional cases of very rapid torrents, or rather of true cascades, at the place where they fall into a transverse valley, and where there is as much matter tumbled down as transported. The beds of the most rapid rivers are much less inclined, and the successive deposits are for the most part nearly horizontal. Gravel and sand which the waves wash upon the coasts are also deposited at very small angles, and slopes of 10 degrees are exceptions, even in localities exposed to the strongest billows. Most frequently they are much less and nearly horizontal. It frequently happens during the drift or transportation of matters by current and by freshets in rivers, when the bottom is disturbed, that effects analogous to those of sea winds on dunes are produced. Ridges are formed across the current, various matters pushed over these initial hillocks accumulate behind them, forming a talus of successive fallings, which impart the structure represented in Figure 217. If the river change its course, the undulated surface of the first deposit is soon leveled, and quiet deposits are formed above, from which the preceding may be distinguished by the particular structure attributable to the circumstances of its formation. These effects, resulting from a mixture of rapid and tranquil deposits, that is, deposits formed from rapid currents and tranquil waters, are very clearly seen in alluvions on riverbanks, and particularly in deltas, which terminate their course when the waters have excavated some ravine nearby. We then perceive that the mass of the deposit is formed of horizontal layers, having a surface more or less undulated, which are distinguished from each other by the size of the component parts, by the color, by the structure produced by rapid accumulation, either by pushing forward the material in the direction of the ordinary current, as in the deposits A and B, or in a different direction, as in the deposit C, which indicate counter currents formed at one time or another. Often there are particular masses, formed here and there, which ordinarily consist of coarser gravel, or of different organic debris. Effects of oscillatory motion. Great masses of water, subject, like the sea, to undulatory motion, present another order of facts. Not only are suspended substances deposited there in horizontal beds, as a more weighty fluid would do, but the slightest agitation does not permit any material particle to be solidly fixed on planes of the least inclination, but tends, on the contrary, to destroy all inequalities of the bottom. It is impossible to ascertain positively these effects at the bottom of the sea, but the immense number of soundings, taken in all parts of the ocean by navigators, show that all moving bottoms have very slight inclination, that slopes at an angle of half a degree are rare, and that all above this are exceptions. Hence it follows that in great masses of water, beds formed by successive deposits must be entirely horizontal. This fact is most clearly exhibited in certain lakes, which have been entirely or in part dried up, where alternations of beds, of every kind, are seen to be perfectly horizontal. Lakes Superior and Huron furnish examples of this. This disposition of various matters deposited from water, bed by bed, at the bottom of rivers, lakes, marshes, is termed stratification. The deposits themselves are said to be stratified. This circumstance eminently distinguishes deposits formed by water from those produced by igneous fusion, which are most frequently massive or irregularly divided. Nature of deposits. Organic remains. Beds of alluvium are formed of rolled flints, gravel, and sand, as well as of various kinds of mud, analogous to matter called clay or argil. They are more or less consolidated, as much by their own weight as by waters charged with carbonate of lime, or various matters which may penetrate them. In lakes we see calcareous and argillaceous marls, which have the property of hardening in the air, as has been observed in certain half-dried lakes in Scotland, in modern building stone found in Hungary, and in Lakes Superior and Huron. Similar formations doubtlessly occur in the sea, as waters are sufficiently calciferous to consolidate the sands thrown on its coasts, and the nature of upheaved deposits in many places leave no uncertainty in this respect. These deposits are frequently filled with remains of all the organized creatures now living on the surface of the globe. In river alluvium we find remains of fluviatile shells that still live in the same localities, or land shells, such as various snails brought thither by rivulets. There are branches and trunks of trees, masses of plants, more or less changed, sometimes partly bituminized, bones of terrestrial or aquatic animals, rarely human bones, but frequently the remains of art, such as fragments of brick and pottery, etc. Alluvions formed by the sea are very similar. They contain marine debris of every kind, sometimes alone and sometimes mingled with fluviatile and terrestrial debris, brought into it by rivers. Debris of human industry, anchors, boats, etc., are frequent, and even man's remains exist, not only in cemeteries of villages that have been overwhelmed by sands, but also among the debris cast up by the sea, as at Guadalupe, where human bones are found in a sand consolidated by a calcareous tufa, and mingled with debris of human art. In deltas formed partly of fresh water and partly by the sea, we find alternate layers, the one filled with marine debris, and the others by those of fresh water. But under other circumstances, all these remains are found indiscriminately mingled. Argillaceous, marly, or calcareous deposits in lakes contain the remains of fluviatile and terrestrial mollusks, similar to those now existing in the same regions. Remains of fishes and mammals are also occasionally found. There is no doubt deposits formed in the sea also contain remains of the numerous animals that daily perish. We learn from soundings that the bottom of the sea in many places is covered by shells, broken or entire, fragments of madrepore, echinidae, etc., sometimes mingled with sand, sometimes by themselves, constituting considerable banks in progress of formation and consolidation. Coral reefs. Formations of stony polyparia, agglomerated with each other, often of great extent, are thus named. In intertropical regions they constitute a great number of islands, on a level with the sea, or submarine banks, the mass of which rises more and more. It is scarcely 20 years since it was supposed that the little animals which form these deposits, by calcareous exudation, had the faculty of living at great depths in the ocean. It was thought they began their dwelling, and gradually augmented the mass, until it formed immense mountains, the summits of which constituted the reefs, and that they gave origin to most of the large islands formed in those regions. These microscopic creatures, it was said, tended thus to fill up the ocean, and were preparing prodigious changes on the surface of the globe. But all this exaggeration had disappeared, the observations of Messrs. Coy and Gaimard having shown that the species which contribute most to the formation of reefs, such as Caryophyllae, Meandrinae, and particularly the Astriae, which sometimes cover immense spaces, and various madrepores, cannot exist except at moderate depths, and 10 or 12 yards below the surface no trace of them is to be found. It is then on pre-existing rocks already elevated under water, often very steep on the sides, as soundings show, that these animals begin to build, and from this they afterwards accumulate their solid product to the level of the sea, where their last generations perish. They cannot, then, fill up the ocean, but the incrustations they form are not the less important, since they are sometimes 10 or 12 yards thick, extending over immense spaces, and these are found in a great many places in all seas comprehended between the tropics. They crown most submarine mountains, and cover thousands of square leagues, distributed among thousands of islands and reefs. These saxigenous polyparia, attached to every kind of rock, surround most large islands with their products, forming around them a kind of rampart, separated frequently by deep water. In other instances they form islets, detached or grouped in different ways, and they are, when there are breakers, the more dangerous, because they are not seen before being cast upon them, and because the depth of water is so great as not to afford anchorage. It is these deposits which render navigation so difficult in certain parts of the South Sea, and cause so many deplorable losses by shipwreck. Some of the forms assumed by these deposits at the surface of the sea are particularly remarkable, and are not yet entirely explained. Sometimes these reefs are completely annular, with a lake in the center enclosed on all sides. Sometimes they form broken circles, having one or more openings through which the center may be reached. Again, they are in groups of islands, arranged in a circle, and frequently there are several in a series. In these internal seas the water is often very deep, but sometimes very shallow, and an immense number of polyparia are developed, which sooner or later fill up the space. It appears evident that these circular reefs are the edges of different upheaved craters, upon which the polyps have established themselves. This is inferred from the volcanic nature of most islands in the Pacific, and from the manner in which submarine eruptions sometimes take place. Nevertheless, this explanation is not received as satisfactory in respect to many reefs of the kind, and particularly those which constitute the Maldives and Laccadives groups in the Indian Ocean. The great number of circular groups found in certain localities, and the immense expanse which we must suppose craters of elevation to have in other places, are facts urged in objection to the explanation. Around coral reefs, as well as in the lakes they enclose, soft and white mud of calcareous nature, analogous to chalk, has been observed, which has sometimes been referred to the disintegration of madrepores and sometimes to dejunctions of worms which pierce the polyparia, or to those of fishes which feed on them. In many places in the South Seas, this mud seems to constitute considerable deposits. When a reef has reached the level of the water, the sea often covers it with debris of every kind, on which vegetation is afterwards developed. Most low islands in the Pacific have been produced in this way, all of which rest on masses of polyparia. A great many other islands have sprung up on their coasts in the same way, and there are many which will sooner or later grow up in the same manner, for now, at low tide, we may walk over reefs extending half a league from the shore. But one very important circumstance is, that in many places we find precisely similar deposits, composed of the same species of madrepores, in the interior of land at an elevation of from 200 to 300 yards. This is seen at Timor, where the deposits are 10 or 12 yards thick, at New Holland, Van Diemen's Land, at the Marian Islands, Sandwich Islands, etc., where they rest on argillaceous schist, sandstone, limestone, volcanic products, etc. In the Isle of France, a similar bank, 4 yards thick, is found placed between two currents of lava. The existence of these deposits in such situations evidently indicates that all these islands have been upheaved from the bosoms of the waters, and often at several different periods, for we often find banks of coral at different levels. Peat, or turf bog. They are daily formed in different excavations of the surface, in valleys of gentle slope, in low and marshy situations, deposits of vegetable matter, the decomposition of which furnishes a combustible called turf or peat, and the mass bears the name of peat bog. These deposits are formed only under particular circumstances. They are seen only in places where stagnant waters constantly exist, and only in shallow depths. The presence of light is necessary to secure vegetation, to which peat chiefly owes its origin. The production of peat, to which all aquatic plants contribute, is principally owing, however, to those which are always submerged, and which multiply rapidly. Their debris form the principal paste that envelops all the others, and probably contributes to their decomposition. A number of terrestrial plants, also, brought to these bogs by brooks, contribute to the formation. Frequently large trees are found buried in the mass, particularly in the lower parts, where they accumulate on sands and clays which form the bottom. Often they are seen broken and fallen near the root, which is found attached to the bottom of the bog. In some instances these debris are very numerous, and seem to indicate that entire forests must have been buried on the spot where they grew, before the formation of peat. The plants found in these situations all belong to existing species. They are resinous trees, oaks, birch, etc. Remains of mammals are often found in peat bogs, such as the bones of oxen, the horns of deer, tusks of wild boars, etc. Peat bogs rest on every variety of soil, sometimes even on crystalline rocks. Most generally, however, they overlie deposits of sand or clay, and sometimes the rolled flints of the country. There are places where accumulated debris of plants form but a single mass, of greater or less thickness, more compact and blacker at the lower part than in subsequently formed parts of it. There are other places where the different beds are separated by sedimentary deposits of alluvium. These are formed of sands, clays, calcareous or argillaceous marls, often containing freshwater shells in great quantity. Sometimes the surface of the deposit remains covered by water, and at others it is covered by a luxuriant vegetation. Peat bogs are numerous in different parts of the world. They occupy basins or depressions in the soil at different elevations, even in the Alps. 1/10 of the whole surface of Ireland is said to be covered by peat bog. In the Great Dismal Swamp of Virginia and North
Lesson 8, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Lesson 8, Part 1. Explanation of various phenomena. Consequences of central heat. First effect of cooling. Warm springs. Deposits referable to sediment. Freshwater deposits. Fossils of marine deposits. Fossils of carbonaceous deposits. Having established the fact of a central heat capable of keeping everything in a state of fusion at a short distance beneath the surface we inhabit, having shown the actual effects of earthquakes and of volcanic action, having pointed out those which waters produce, both by denudation or degradation, and the formation of new deposits, it is natural to attempt, by reference to these effects, the explanation of all geological phenomena which have occurred on the surface of the globe from the first moment of its existence. The causes now in action are the same as those which have acted through all time, but doubtlessly they were more energetic at certain epochs than present observation shows. Consequences of central heat. The complete fluidity of the globe gave rise to its ellipsoidal form. The heat so long preserved and still existing beneath the cooled pellicle or crust has produced, and is now producing, a great number of phenomena. The temperature of the surface is nearly stationary, and has not varied since the period of records, and will not probably change. But before reaching this state, which probably required thousands of years, the surface of the earth must have passed through every degree of heat, from the state of fusion in which the centre still is, to its present degree of cold. Consequently, there was a time when the temperature of the earth was such as to do away with differences of climate, or an atmosphere of vapour, which, by overcoming radiation, diminished the rigour of winter. Then vegetation, and life generally, could be equally maintained in all latitudes as in a hothouse. From this it follows that plants and animals now found only between the tropics could then live anywhere, even under the poles, which were not then encumbered in ice. It is therefore not astonishing that we should find the remains of these various creatures buried nearly on the spot where they lived, in countries which are now the coldest in the world, and in which it would be impossible for them to live at the present time. There is in England, on the island of Portland, and at several places on the continent, intercalated in other deposits, a bed of black matter called dirt bed, and small argillaceous beds, in which, among a great many vegetable remains, bedded and scattered, are various plants in their place of growth, the roots of which extend into the fissures of the calcareous soil beneath. Therefore, there must have been a vegetable soil, on which all the plants now buried in the earth then grew. But all the species found in this bed belong to the genera, such as cycas and zamia, which now live only in the tropics, and the remains of animals also belong to the same zone. Consequently, the mean temperature at the time of this formation was very different from what it is now in England. Most of the coal deposits of Europe lead to a similar conclusion. Entire trees with their roots, many of them still erect, are found, as in the mine of Trieul, near St. Etienne, in the mines of Anzin, north, in England, in Scotland, etc., which seems to indicate, as in peat bogs, plants that grew very near the places where they are now found. It is evident from the perfect preservation of the most delicate parts of plants, the manner in which the leaves are extended on schists, that these remains could not have been carried far. All the remains of plants found in these deposits belong to the Equisitataceae, lofty ferns, to the Lycopodiaceae, etc., and cannot be compared with those now existing in the tropics. Consequently, the climate of Europe must have been then very different from what it is at present. We find in the latitudes of Europe certain beds containing the remains of intertropical plants, but we also find above them considerable deposits in which are dicotyledonous plants of the present time. The formation of the last deposits, then, must have taken place long after the first, and it is probable that between the epochs a period of time elapsed sufficient for cooling the surface of our planet. Madrepores of reefs, which now do not exist beyond the tropics, then evidently extended to the polar circle. In fact, the limestones of different periods contain a great number, and frequently show that reefs existed comparable to those of our days. Facts show that the limits of these banks of zoophytes have retrograded from the period of the deposit of the oldest limestones to that of the chalk, after which they suddenly retired to their present limits. In other words, the climate of Europe has grown successively colder. First effect of cooling. The idea of complete fusion and of cooling, which the observation of the phenomena forcibly leads us to admit, also leads us to conceive what must have taken place on the first consolidation of the globe's surface. The first solid pellicle formed underwent from cooling more or less contraction, and on this account must have broken in all directions, from the action of the melted matter it covered, swimming in pieces on its surface, and uniting anew more or less irregularly to be broken again. but assuming greater consistence and pressing more and more on the liquid part, this must have gushed up through the rents, then more rare, and formed above the crust projecting ridges of more or less extent, which increased in height in proportion as the resistance of the crust became greater, and caused stronger and stronger reaction. Hence the first rugosities, the first ridges formed on the surface of the globe, which possibly afforded the first hold for the action of water, the precipitation of which took place, without doubt, long before the temperature of the terrestrial crust had descended to 212 degrees of Fahrenheit's thermometer, in consequence of the pressure exerted by the vapour then diffused in the air. From that moment waves produced debris, and arenaceous matters and sediments began to form. Probably the water, at a high temperature, charged with the principles disengaged from the solidified masses, like lava of the present time, attacked the stony matters, disintegrated and dissolved them, and subsequently formed chemical deposits or consolidated the debris. In fact, we find deposits formed of fragments of rolled flints and of sands, in the most ancient layers yet examined, and before meeting with organic remains. All the solid layers formed beneath the first pellicle, like it, being subjected to the law of contraction from cooling, must have been filled with cracks in all directions. Therefore, the whole terrestrial crust thus formed could not have been as solid as might be at first imagined. It could not resist, so successfully as might be thought, the internal actions, which, meeting no obstacle in the sedimentary deposits subsequently formed, must have dislocated them in all ways. In fact, there is no deposit on the surface of the globe, either sedimentary or crystalline, which is not found to be cracked in all directions. Even on the upper surface, most rocks are broken in small fragments to a considerable depth. While the crust of the earth was gradually cooling, things must have passed nearly as we have stated, but after the temperature had become stationary, as it is now, it could not have been the same. The superficial pellicle does not contract, because it does not grow sensibly cooler. Nevertheless, the interior mass is still cooling more and more, although with extreme slowness, and consequently diminishing in volume, and according to Fourier, a decrease of internal heat of not more than 1 degree and 30 yards would require 30,000 years. Now, the fluid part tending to drag with it that which covers it, and which becomes successively too large, this must contract on itself, and ridge the surface by dislocations through its whole thickness. This may take place tranquilly for some time, but at certain moments the effect cannot fail to take place quickly, and hence the sudden catastrophes experienced on the earth's surface. All observations in accordance with geometrical considerations show that these ridges and these dislocations are formed according to the great circle of the sphere, and extend over the half of its circumference. Warm springs. The different degrees of temperature of warm springs are referable to the central heat, which is communicated through fissures of greater or less profundity. The waters come to the surface with the temperature of the point whence they started, and it is known that at the depth of about 3,280 yards they boil. Now it may be readily conceived how, during earthquakes, new hot springs may appear in a country, and how those that existed there may be lost. In the first instance, all that is required is a fissure to establish a communication between the surface and a proper depth, and, for the second, that the existing communication should be interrupted. We may easily conceive, also, that before the earth had reached its present degree of cooling, hot springs must have been infinitely more numerous than they are at present, when, instead of 1/30th of a degree centigrade per yard, the temperature increased 1/3 of a degree, that is, 10 times more rapidly than at present, and when water boiled at a depth of 325 yards, it is clear there must have been a great many springs at a temperature of 212 degrees Fahrenheit, or of boiling water, and that fumaroles, now rare, were then common. Consequently, the condition of the atmosphere was then very different from what it is now. Thick fogs must have spread over the surface of the earth in the absence of the sun, and hence radiation towards the celestial space, at present an important cause of refrigeration, must then have been nothing. Winter was consequently less rigorous, and this explains, too, how so many plants and animals which cannot now exist in northern climates could then live in them as between the tropics, and precisely as southern plants now live on northern coasts and islands which are constantly shrouded in thick fogs. The whole earth, tempered by these abundant vapours, could then support the same organic creatures. Here we have reason why mineral beds of a determined age differ less in the organic remains they contain, wherever found, than existing creatures of different zones. Deposits referable to sediment. Rolled flints, sand, and mud are formed by the action of running water and of waves, and, being transported by these waters, they accumulate in lakes, in seas, at the mouths of rivers, and on coasts. Whenever we find these kinds of matter accumulated in more or less considerable deposits in the interior of countries, we have a right to conclude that there existed somewhere far or near high mountains from which these matters were detached, watercourses which carried them, undulating waters which heaped them upon their shores, and often lakes and seas that received them. By the greater or less abundance and size of the rolled flints, we can judge of the mass and force of the waters that transported them, and their nature and various course or track ought to lead to the point of their origin, if circumstances have not destroyed the traces left by currents in their course. As in the present day, we see deposits of shells formed in lakes and seas. We infer that the numerous beds of the same kind we find at all heights, even on the summits of the loftiest mountains, were necessarily formed under water. The nature of the organic remains enables us to determine whether they were deposited under fresh or salt water, on coasts or in depths of the sea. Their mixture, their alternation, indicate mouths of rivers, alternations of salt and fresh water, etc. Deposits from fresh water. These deposits are easily recognized from the organic remains they contain, being comparable to different genera, sometimes even to different species of animals now living in our lakes and rivers. There are especially remains, impressions or moulds of shells, like those of the genus Limnia, Planorbis, Paludina, Melania, and of land shells of the genus Helix. These are all univalve, unilocular shells. The bivalve shells of freshwater deposits, more rare than the preceding, are like mussels, unio, anodonta, cyclus, and sirena. The entire absence of every species of Polyparia and Echinidae is an important characteristic of freshwater deposits, which are very common in different parts of the world. Marine deposits. These are distinguished by the analogy of the organic remains they contain to the debris of different animals now living in the seas. Polyparia, more or less analogous to those which form coral reefs, are highly characteristic. Encrinites, or the remains of their joints, the Echinidae. Not one of these organic bodies is found in fresh water. Among the marine univalves, there are some which are more or less analogous to those of freshwater, previously mentioned, although they are thicker and more generally covered with tubercles. But, setting aside those on which at first sight there might be some doubt, there are many others which are sufficiently characteristic. These are shells whose aperture is terminated by a canal of greater or less length, and belong either to the genus Cerithium, of which a small number of species lives in fresh water, or to the genera Murex, Voluta, etc. They are all marine and abound in calcareous deposits. Marine bivalve shells generally differ very much from those found in fresh water. Some resemble oysters, and others are almost entirely like them. A great many are furnished with ribs, or striae, or rugosities, and possess, in a word, many characteristics entirely different from those found in the genera we have just mentioned. Chambered shells are found only in seas, such as the Nautilus, more or less like numerous species of ammonites, no analogue of which is now living, but with which certain terrestrial strata are filled. These deposits are generally formed very slowly, by the accumulation of shells left by dead molluscs as fast as they perish, and not by sudden catastrophes, which would have heaped them up alive in greater or less numbers. This is proved by the fact that frequently on the inside of shells we find parasitic animals that attach themselves to bodies of all kinds, and which could not attach themselves here in the interior of the shell if the mollusk had not been previously destroyed. Often the very shell of the parasite is covered by others, showing the first had long existed in the sea. The shells of bivalves are frequently found separated, showing the animal must have died before they were buried. And there are shells which are pierced by lithophagi, as well as the flints and fragments of limestone which accompany them, leading to the same conclusion. There are, of course, some exceptions, but these are commonly due to local circumstances. Generally, these shelly deposits are on the spot where the animals lived. In fact, they contain a great number of uninjured shells, the most delicate appendages of which are in a state of perfect preservation, a circumstance not reconcilable with the idea of transportation by currents, which would have broken the whole and rounded the fragments. Even in decomposition, the finest parts have left their impressions on the substances enveloping them. By means of the debris alluded to, we may always recognize marine deposits. Carbonaceous deposits. It is undeniable that the carbonaceous deposits found in different strata of the earth were produced there by the accumulation of the remains of plants. This is proved by the numerous and clearly characterized remains of stems and leaves met with, either in the combustible mass or in the earthy matter containing it. On this point, all are of one opinion, but all do not agree as to the manner of the accumulation of these remains. Some geologists suppose that all carbonaceous deposits result from the sinking of great rafts of diverse plants transported by great rivers, by maritime currents, and sunk in different places. Others think, on the contrary, that most of these deposits were formed in place in the same manner as peat bogs in depressions of the surface, to which rivulets daily brought debris from the surrounding vegetation. Opposed to the idea of floating rafts is the enormous thickness they must have attained to have produced beds of coal, such as are known between two layers of arenaceous matter. In fact, taking into consideration the specific weight of wood, the amount of carbon it contains relatively to that of carbonaceous deposits, we find that the latter can only be 22/100ths, or even 7/100ths, according to the kind of plants, of the primitive volume of the matters which gave origin to them. Besides, estimating the numerous voids left by the irregular interlacing of these debris in a raft, we know that coal, for example, which is formed of the lightest plants, as the Equisitaceae, ferns, etc., cannot be in the bed more than 35,000ths of the thickness of the raft that formed it. That is, a coal bed of from 1 to 30 yards thick would require the rafts to have been 28 or 57 to 857 yards in thickness, which evidently exceeds the limits of probability, and in most seas would be impossible. The idea of the formation being analogous to that of peat bogs does not present this difficulty, and only requires time for the accumulation of the necessary organic materials. In the present state of things, this time would be very considerable, for according to the calculation of M. de Beaumont on the quantity of carbon annually produced by our forests, not much more than 6/10 of an inch in thickness of coal would be formed in carbonaceous deposits in the period of a century. But everything leads to the belief that at a mean temperature of 71 degrees Fahrenheit, when the atmosphere was filled with vapour, and vegetation in the genera of plants that then grew in our country was infinitely more vigorous than at present, we are also led to believe that at the epoch of these formations, when the earth had not yet cooled to its present temperature, a great deal of carbonic acid issued from its interior, and the appropriation of the carbon by plants was then more rapid. It is not only for the formation of coal that a long period of time is required. All sedimentary and calcareous deposits formed only of shells, which acquire much greater thickness than carbonaceous deposits, have certainly required many centuries to reach this point. The hypothesis, which assimilates deposits of coal to peat bogs, is fortified by the different characters they present. Such are not only the trees found erect with their roots, and the remarkable preservation of the leaves in schists, but the deposition in isolated basins of greater or lesser extent seems to indicate swamps and marshy places formed in depressions of the surface of the soil. These deposits are often surrounded on all sides by rocks of an anterior formation, which form the pyrites of the cavity where they took place. Frequently, we also find that a certain number of small basins, independent of each other, forming part of a more extensive basin of a species of lake filled with contemporaneous arenaceous matters, on the surface of which there would be formed as many masses of combustible. There are some, too, that extend through the length of certain ancient valleys and are contained in them. All these circumstances are observable in the deposits of the centre and south of France, but in the north of France, in Belgium, in England, and in Scotland, it is different. There, the beds of combustible seem to extend over great spaces, and the assemblage of facts, as well as the immediate superposition of marine limestone found in all these countries, leads us to suppose that these deposits, now dislocated and separated by seas, have once formed part of the same whole. It was not in swamps or in closed lakes they were formed, but in a vast sea, the receptacle of all the debris of the vegetation of its coasts and islands, that they must have taken place, and in which undulatory motion stratified these materials as well as all other sedimentary deposits. Certain deposits of lignite were evidently formed in the same manner as coal, but there are others which constitute irregular masses of wood thrown pell-mell, more or less bituminous, and preserving their tissue, found accidentally buried in the midst of sedimentary deposits, and which probably had a similar origin to those transported by great rivers, which are deposited in lakes or conveyed to the middle of seas. Remains of shells are rare in deposits of coal, properly so called. There is no trace of them in any of the deposits of the centre of France, and it is only in the great formation comprising the north of France, Belgium, and England, that some examples are met. Marine shells are found in the environs of Liege and of Namur in Derbyshire, etc. Freshwater shells, similar to Unio and Anodonta, are found in the same place. In most deposits of lignite, in which the structure of the wood has generally disappeared, we find, on the contrary, a great number of fluviatile shells, which proves that the formation of these deposits took place in freshwater lakes. Lesson 8, Part 2 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Lesson 8, Part 2. Effects attributable to upheaval and subsidence. Shell deposits and raised beaches. Submarine forests. Tracks of quadrupeds and birds. Dislocation of strata. Faults. Crateриform arrangement of strata. Valleys of elevation. Upheaval without dislocation. Distortion of strata. Origin of valleys. Valleys from dislocation, from subsidence, from folding or plating, from erosion or denudation. Origin of caverns. At whatever height we may find fluviatile deposits on the surface of the globe, there is nothing to excite astonishment, for we readily conceive that lakes could have existed at all heights on continents, and that, after their waters flowed away, their deposits remained dry on the soil. But we find also marine deposits at all heights, in very extensive beds, and, at first sight, it is not so easy to account for them. It is evident that such deposits could have been formed only under waters of the sea, and, as they are now found thousands of yards above the present level of the ocean, we must admit one of two things. Either that the water was elevated above these points for a sufficiently long time to form thick beds there, or that these deposits were raised up from the bottom of the sea to the height we now find them. Nothing in the phenomena of the present time warrants a belief that the sea, which has not changed its level within the time of history, could have been so elevated, long enough to form considerable deposits. The universal deluge of the Holy Scriptures was a catastrophe of short duration, and therefore could not have produced the immense deposits referred to, which, everything leads us to believe, were formed slowly. Besides, this catastrophe is comparatively of modern date, and must be referred to the last modification of the surface. Now, all the deposits of shells of which we speak were long anterior and were independent of facts belonging to the history of the human race. Nothing informs us what became of the excess of water, a greater or less volume than now exists, above the present level, without having recourse to divine interference, which must have been frequent in ancient times, to cause these waters to appear or disappear a great many times, and even suspend the action of the laws of equilibrium. In fact, very often deposits of shells, seen here and there at a great height, are not found on corresponding summits, and are represented on the contrary with all their characters thousands of yards lower down. Hence we must suppose the waters were considerably elevated on the first of these points, and remain low on the other, which is absurd, or we must admit that the same animals could live in one place near the surface of the water, and in another at immense depths, which is contrary to all observation. Therefore, the only reasonable supposition left is that of upheaval, an idea supported at least on positive events which have taken place in our own times, and which are, doubtlessly, not the only ones which have been manifest on the surface of the globe. If an upheaving force could suddenly elevate 200 leagues of the coast of Chile, spreading as far as the islands of Juan Fernandez, if the same effect were slowly produced in all the Gulf of Bothnia in Sweden and in Finland over a surface of not less extent, we may comprehend how vast countries might have been elevated anywhere. The enormous liquefied mass forming the interior of the globe, oscillating from side to side beneath its thin crust, could emboss it in every direction, and nothing more would be required to raise continents out of the sea, and vary the slight relief in all manners. And let not such effects excite alarm, because they appear gigantic. We judge them to be so because we compare them with our feeble powers, for they are nothing compared to the globe itself. What are the 25,660 feet in the height of Himalaya, the highest mountain in the world, and the 24,580 feet depth, the deepest soundings in the midst of the sea, compared with the 19,685,500 feet measured by the mean radius of the earth? And notwithstanding such eminences or depths, the sum of which is less than 0.5 of an inch to the yard, are rarities on our planet, whose inequalities are not even comparable to the unperceivable irregularities which are formed in our manufactories on moulded glass or metals, which nevertheless pass unnoticed. If to these reflections we add our knowledge of the immense force often exerted from the interior towards the exterior, none of these phenomena will astonish us. Shell deposits and upheaval, or raised beaches. Parts of soil upheaved above the level of the sea are characterized, on the surface of exposed rocks, by the presence of various shells that live, ordinarily, attached on a level with the water, such as barnacles, mussels, etc., or by that of some small deposits of shells, identical with those daily formed at the bottom of neighbouring seas. Now, on examining the hills near the coast of Chile, there has been found on the plateau, which succeed each other in terraces, the sides of which are parallel to the present shores, shells similar to those that have been left dry in our day, and which are still attached to rocks, as well as shelly deposits, which contain the same organic remains as those now forming in the Pacific Ocean. Is it not most probable that these deposits are indications of successive upheavals similar to those which have recently taken place? This inference is sustained by observations made on the coast of Peru near Lima, in the island of San Lorenzo, where, 30 yards above the level of the sea, deposits have been found which contain wovenosia, portions of cotton thread, etc., clearly showing that the deposits in question were formed since the existence of man in those countries, as the level of seas has not changed since history began. It is only by upheaval they could be brought to light. That the coast of Sweden has been uplifted slowly has been established by the most exact observations. In digging a canal near Stockholm, in the midst of beds of sand, clay and marl, filled with shells similar to those that now live in the Baltic, there were found the remains of very ancient vessels. All this country, which must have been at some period under water, and in which some ships were wrecked, has been upheaved since the presence of man, the level of the ocean being invariable. It is therefore evident that the shelly deposit of Uddevalla, in which organic remains of the Baltic are found, 70 yards above the level of the sea, and in which Monsieur Brongniart found baleineae attached to rocks, as they are on the present coast, is a fact of elevation. Similar deposits and evidence of elevation are met in other parts of the world. The upheaval and subsidence of the Temple of Serape has been already mentioned. In thus admitting that very extensive deposits, formed of shells that are now living in the sea, have been evidently upheaved to greater or less heights, is it not therefore exceedingly probable that the same is true of all the rest? Why should this not be true in regard to the neighbourhood of London and Paris, to that of the plains of Gascony, Austria, Hungary, Poland, etc.? All the shells found in those places are not similar to those in the present seas, but there exists a considerable quantity of them, and moreover their preservation is so perfect in many places that they seem to have been recently buried. If we admit the fact of elevation for these deposits, can we refuse it to the chalk that everywhere envelops them, forming not only the Jura, but a great part of the calcareous mountains of France, or to any shell deposits, the organic debris of which bear witness to their marine origin? Subsidence of various deposits. Upheaval has been shown. Subsidence is not less demonstrable. At many points on the coasts of France and England may be seen at low tide very extensive deposits of plants similar to those now living in those countries, and which appear to have grown on the spot where they are found, for the roots are seen attached to the soil. These deposits rest on earthy matter, covered with leaves, heaped upon each other, or sunk in a peat-like substance. In these places have been found birch trees, chestnuts, oaks, and fir trees, sometimes scarcely altered, species of deer similar to those met in peat bogs, the whole covered by the argillaceous deposits, which contain freshwater shells. These submarine forests, as they are called, could have grown only on a soil more or less elevated above the sea, and as they are now found beneath it, and are not uncovered except in unusually low tides, the earth must have sunk after a period of vegetation. The dirt bed of Portland shows the existence of a vegetable earth or mould of a soil nearly dry, resting on marine deposits. This bed has been covered by a very thick deposit of lacustrine limestone, and the whole passes under the green sand which precedes the chalk, and which is of marine formation. It is clear, therefore, that there was in those places a certain upheaval of the inferior marine limestone, on which terrestrial plants grew, that subsequently a lake, or a deep estuary, was formed, in which beds of limestone, sand and clay were deposited, filled with fluviatile shells, the entire mass being sometimes from 200 to 500 yards in thickness. A subsequent upheaval must have lifted the whole to its present level. Around the Paris Basin, the deposit of marine limestone, worked for building stone, must have been at first uplifted at various points above the sea, to be covered by a freshwater lake in which the lacustrine deposits were formed, and among them the plaster of Paris. Subsequently, it must have been sunk beneath the sea, to be covered by a marine formation, and again uplifted to be covered by a second freshwater formation. Hundreds of facts of this kind might be cited, but we will only notice the impressions of feet and tracks of certain quadrupeds found at Hesburg, near Hildburghausen, in Saxony, on the faces of certain beds of sandstone, and the impressions of the feet of various birds found in the valley of the Connecticut in the United States, in the same deposits. These impressions show that the soil was in a degree soft, although partly dry, which is proved by the ridges it presents, and that it was out of water. The sedimentary bed on which these animals walked is now covered by another, which is moulded on these tracks, and afterwards by considerable deposits of the same matter, which could be formed only under water. It follows, therefore, that the soil, first uplifted enough to enable terrestrial animals to walk on it, was subsequently sunk to receive all those sedimentary deposits, and afterwards was again upheaved to its present position. Change of position and dislocation of strata attributable to upheaval. It has been already stated that sand and shells are deposited under water in horizontal beds. Indeed, we frequently find them in this position on the surface, even over extensive spaces, and we then find flattened pebbles, valves of oysters, and other shells lying flat, and turriculated shells lying on one side, and everything confirming the idea of a slow formation by the weight of these substances. But it sometimes happens that we see deposits more or less inclined in certain parts of their extent, raised up almost to a vertical position, and sometimes entirely overturned. They still preserve, however, all the characters which show they were at first horizontal, for the debris of shells and pebbles they contain are still found arranged parallelly to the planes of the beds. Besides, there are deposits which contain geodes of agate, in which are found stalactites with the axis more or less inclined, which is directly opposite to the manner of production of these substances. Consequently, these deposits could not have been formed in the position we find them, for, on the one hand, the debris of shells and pebbles would have rolled over to be surely balanced, or fallen to the foot of the talus. On the other, the stalactites would have formed in a vertical position. This last observation particularly shows that the beds were at first horizontal, and that their position has been changed subsequently to their formation. This is one of the great geological phenomena we seek to explain. The effects of earthquakes and those of volcanic phenomena will serve as points of comparison in our inquiry. On one hand, the crevices produced in the soil at the time to a greater or less depth can only be the effect of upheaval, for the separation of parts does not result here from drying, nor from cooling, which would produce a retreating of the whole mass. It is remarked in the neighbourhood of cracks that the soil is no longer on the same plane as the rest of the country, that it is more or less arched, and often one part is more elevated than another. Now, if the soil have been uplifted, it must follow that the internal beds have been disturbed in their position. Consequently, when in a formation of horizontal strata a crack is made in a straight line, the beds must be inclined on both sides through their length, like two slopes of a roof. When several divergent cracks are formed, the beds ought to incline symmetrically around the axis of elevation. Now, if we find all inclined beds in one or the other of these positions, we have a right to conclude that they have been uplifted by the same causes. Faults. When a crack is made, it often happens that one of the parts of the soil is more elevated than the other, no matter whether the crack remains open or not. These effects are often observed, and it is presumed they are all produced by the same cause, namely, upheaval. The beds are then inclined in opposite directions, and one of the parts is more elevated than that which is adjacent. The junction is sometimes distinguished by subterraneous work, either subsequently filled with gravel, or a slight fissure, or at least by a surface of separation, the planes of which are smooth and sometimes polished or striated vertically, showing a close crack and a rubbing of one part on the other. This arrangement has been called fault, from the German Fall, an accident, fall, or sinking, because one part is lower than the other. Faults are observed in every kind of soil, and present crests or ridges extending over great spaces nearly in a straight line, sometimes broken here and there, but the different parts preserve the same direction. Besides showing themselves on the surface, faults are also perceived underground by the disturbance they have caused in beds or veins worked for the benefit of the arts. It is thus, for example, in coal measures, the same bed of coal is found so much deranged in its position that the miner, after having worked on a part of its direction, finds it suddenly end, and would at once abandon all his labours, had not experience taught him that, by following the fault, he will find the deposit either above or below the point where it abruptly terminated. Sometimes there results from these disturbances serious mistakes for speculators. Observing various outcrops on the surface of the ground, they have inferred the existence of as many different beds, and consequently great wealth, when, in reality, it was only one and the same bed, dislocated and raised up to different levels by successive faults. Crateriform disposition. The known formation of Monte Nuovo, in explaining to us the uplifting of the beds seen in its crateriform cavity, leads us to attribute also to upheavals, the epochs of which are unknown, the structure of several other hillocks of the same country, such as those of the Solfatara, of Pozzuoli, of Camboldi, of Astroni, etc., where the strata are all raised towards the axis of the excavation found in the centre. In these hillocks, the bottom of the cavity, particularly at Astroni, presents the point of a trachytic dome, which doubtlessly caused the elevation of the surrounding beds of pumice tufa. These crater hillocks at once explain all those of the Champ Felgren, which are full at the top, but all the strata of which are raised around the axis. Probably there would be found at their base some point of a cone which had not been uplifted with sufficient force to crack the summit. When strata are inclined in opposite directions, like the two sides of a roof, they form what is termed an anticlinal axis, but when they dip oppositely, it is termed a synclinal axis. Similar circumstances are observed in many places, on a greater scale. At Cantel and Monte Dore, basaltic and trachytic beds, which could only have been deposited on a horizontal plane, are found raised up around one or more centres, leaving towards their point of convergence a crateriform basin of more or less extent, or rising around a more or less projecting trachytic dome, like the peak of Tenerife, above the escarpments surrounding it. Granitic masses are found under similar circumstances, in the midst of which rise hillocks of basalt or scoriae, which doubtlessly followed the first explosion, as at Monte Nuovo and the island of St. George. Calcareous countries are not more exempt from these accidents than others. Only the crateriform cavities, in place of being nearly circular, are more frequently elliptical, sometimes very much elongated, as seen in the Jura Mountains. In general, the length is produced like cracks, extending to a great distance, and forming along its direction elongated hillocks, in a line with each other, offering here and there more projecting summits. These summits are most frequently rent, and present what are termed closed valleys and valleys of elevation, which are in fact craters of elevation. Ruptures of calcareous mountains do not always present the crateriform uniformity just indicated, but vary much in this respect. One side of the rupture sometimes remains low, while the other is elevated. Sometimes the superior beds seem to have retired horizontally, and the inferior strata are arched up between the fractured extremities. Often, among the upheaved beds, some are found which are easily disintegrated, and their projection soon tumbles, inducing the fall of solid strata. From this we have ridges of rock parallel to each other, separated by little valleys, in which the rainwater flows, and they become covered by vegetation. Sometimes the summit only presents a mass of calcareous blocks piled one on the other, but arranged in a line as if the work of a mason. Again, when two parallel upheavals take place, it sometimes happens that one portion of the formation is cut off, and then forms the culminating point of the whole mass, giving the appearance of a repetition of certain strata in the same deposit. The central part of the uplifted mass is formed of matters sometimes analogous to those that essentially constitute the formation, and sometimes totally different. Upheaval and distortion without dislocation. The uplifting of strata is often accompanied by ruptures, but frequently there is no apparent dislocation. We have already noticed the isolated mounts or hillocks on the Champ Valgren, and the same is also seen for greater or less lengths, which then have more or less projecting sides or anticlinal lines formed by the uplifted strata on either side, like the dip of a roof. These effects are similar to those produced by crevices, but acting on strata of a certain degree of flexibility. The Jura Mountains present a number of instances of this. We often see there different parallel ridges of this kind, clearly marked on the simplest maps, which leave between them valleys of greater or less breadth, on the two slopes of which the beds are uplifted. The result is great undulations in the strata, remarked especially in escarpments, produced by different ruptures, which cut the ridges in a great many places. These undulations on a grand scale are not interrupted except by crateriform ruptures of summits, previously spoken of. Plating or folding of schistose strata. Distortions are also observed under other circumstances, in which it seems that beds of a degree of flexibility, or in a pasty condition, have been compressed by two opposing forces rather than uplifted. Certain facts observed in matter of the structure of schist naturally lead to this idea. It often happens that the laminae of these deposits, instead of continuing on the same plane, horizontal or inclined, are all found very much contorted without creasing to be parallel, or folded on themselves into a more or less acute zigzag. The supposition as to the mode in which this plating has been effected has been verified by experiments made by Sir James Hall. Entirely similar circumstances occur in coal measures. All the strata of these deposits, both argillaceous and combustible, are found plated and often at acute angles. This is especially remarkable in the coal measures near Mons in Belgium. Now, how did these compressions take place? In a degree, an explanation is required for each locality, but we know that in a deposit of inclined strata, the mass of which is pushed from below upwards, the superior part presses with all its weight on the inferior, and the beds of the latter, being placed between two opposing forces, may fold on themselves if they are sufficiently flexible. On the other hand, as matters in a state of fusion are often injected with great force into sedimentary deposits, it is conceived that from this results the lateral compression which produces the same effects. Origin of valleys. If mountains are only the result of dislocations which have taken place on the surface of the globe by the force of internal agents, there would be no difficulty in accounting for valleys. The first idea of the origin of valleys was based on excavation by the erosive action of water. But then mountains having been previously formed, it is clear that water would always follow the natural slope of the soil, and only excavate in that direction. When arrested by any obstacle, or in a basin, it would of preference cut through deposits of sand and gravel. We see the contrary of this natural action. Valleys do not generally follow the real slope of the soil. It is not by the lowest part of basins that waters are generally turned, nor through movable formations that they make their passage. Rivers, in place of having excavated their beds, as was thought, are simply directed by the canals they found already made. Now it is not difficult to go back to the origin of these canals. They are evidently the result of upheavals, which have embossed or ridged the soil, until then horizontal. It is clear the inflexible beds must have been broken, and consequently a number of cracks were formed. The cracks became valleys, placed in different relations to each other according to circumstances of upheaval. Parallel if the action, taking place in a certain direction, extended a sufficient length, divergent if the action occurred at one point, as in certain massive mountains, often perpendicular to the direction of uplifted chains, as the secondary cracks, manifested during earthquakes, which occurs especially when the internal action forces crystalline matter through the principal crack. It may be easily conceived that crevices would remain more open in solid matters than in arenaceous deposits, the falling of which would tend to fill the vacancy. And this is the reason why rivers seem to shun movable formations, which they could easily excavate if they had not found a bed ready prepared in another direction. It must not be concluded, however, that water has no agency in the configuration of valleys. On the contrary, we must believe that when a country has been suddenly rent, causing the accumulated waters to flow all at once, that torrents of frightful power were produced, tearing away and removing all parts fractured by upheaval, and they thus modified the passages offered to them. It is probable, also, that certain valleys which pass through a movable formation, little disposed to fracture, have been produced exclusively by water. Valleys referable to this origin are very different in character from the first. They follow the natural line of slope. They change their course on meeting masses which offer resistance, and turn round them to remain constantly in the movable deposits. Such are the valleys which cut through the great deposits of rolled flints found at the foot of the Oriental Alps. Many great rivers have themselves cut their beds in an ancient alluvium, very different from that now forming. The Seine, at Paris, excavated its bed in a deposit of rolled flints, very unlike the gravel it now deposits. Valleys from disruption are those which have been produced by cracks of every size, sometimes colossal, during the upheavals that have brought the land to its present configuration of surface. They generally present abrupt escarpments, in which are seen the section of the fractured strata, the projecting angles on one side often corresponding with the retreating angles of the other. The circles which frequently terminate them above, or those that divide them in their length, are so many craters of elevation, most of which are clearly characterized either by the uplifted strata or the barrancos they present. Valleys of subsidence are also spoken of, but it does not appear there are any arising purely from this cause. Subsidence is frequently correlative to upheaval, and valleys as well as craters of elevation may exhibit the effects of both, which must have taken place especially in the circles found along their line and at their superior extremity. Valleys from folding or plating are produced by two neighbouring upheavals, causing the elevation of strata and leaving a space between, the slopes of which being formed by their planes. This is seen in the high parts of the Jura. Many rivers flow in valleys resulting from two opposite uptiltings of the soil. Valleys of erosion or denudation are produced in loose formations like ravines, made by rainstorms, the waters of which carry off the materials constituting the soil. The origin of caverns is one of the phenomena attributed to the action of water, but although we find on a level with the sea some caverns of slight depth, which may have arisen from the repeated action of waves, it is difficult to believe that great caves, which are sometimes many leagues in extent, have been produced solely by the action of the waters running through them. The action of water on compact limestone, in which caves are principally found, is so slight that it has been supposed the open spaces now found were at one time filled by masses of salt, which the waters had subsequently dissolved and carried away. It is presumed, however, that the first origin of caverns is due to cracks, produced in the interior of the soil, which have been afterwards modified by different causes. We know, in fact, that during earthquakes, rivers as well as lakes suddenly disappear underground, sometimes temporarily and sometimes continuously. It is conceived that the water flows through internal cracks, similar to those produced on the surface, which form canals for its passage. The phenomenon is sometimes coincident with the appearance of some abundant spring in a more or less distant place, but it often happens also that the water nowhere reappears, and we must conclude that it runs directly into the sea. All these circumstances explain the disappearance of certain rivers, which are swallowed by the earth after a superficial course of more or less extent, as well as the sudden appearance of springs gushing from the side of a rock. They point to the existence of subterraneous canals, and lead us to think that, dried up by a more or less considerable upheaval, these canals may have formed the now empty caverns found at all heights, as well as those, the bottom of which are still occupied by a stream of water fed from lakes or rivers on the surface. Still, if the real origin of most of these subterraneous cavities be not doubtful, it must be admitted that subsequently important changes took place in the general form and condition of their parietes. The rounded form, wear and polish of surfaces, grooves, different excoriations, and in all positions, even on the upper part of the vault, an erosive action of which water alone is incapable. It has been thought this liquid might have been charged with carbonic acid gas, which is frequently disengaged from the earth through fissures formed in it, particularly at the time of earthquakes, and that the subsequent effects were owing to its dissolving power.
Lesson 9, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rick Sanborn, Alexandria, Virginia. Elements of Geology by William Ruschenberger. Lesson 9, Part 1. Explanation of various phenomena continued. Deposits attributable to volcanic action. Lava, basalt, action of basalt on adjacent rocks, dolomization, Giant's Causeway, trachytic formation, trap rocks, porphyry, granitic rocks, injection of granite, metalliferous veins, metamorphism, effects of erosion. Volcanic cones and lava currents. When we find conical hills isolated or arranged several together on a line and covered with scoria, sometimes having crateriform cavities at the summit, surrounded by rapilli, we may be certain they are volcanic cones, however ignorant we may be of the epoch of their activity. If on mountainsides, whatever may be their nature, we see long, straight masses, terminated below in a club, hollow in the middle, and thinning out above in a pellicle of dislocated scoria, their origin cannot be doubtful, although every other trace of volcanic action may have disappeared. These long, straight masses are lava currents. If we find these matters in pebbles, in more or less extensive tables, compact below, porous, cellular, or scoriaceous above, with a nearly uniform surface, we may conclude they were accumulated on a horizontal soil, or that in a more or less liquid state they flowed into a depression. They are evidently deposits which have issued from the bosom of the earth in a state of fusion. It is by observations of this kind we are enabled to recognize extinct volcanoes, in relation to which the history of the most remote times is entirely mute. Some of these currents resembled what is called basalt, that is, black rocks with a compact base of labradorite containing black pyroxene and almost always magnetic oxide of iron. Very frequently there is found in it more or less voluminous nodules of peridote and sometimes crystals of feldspar, which give it a porphyritic structure. These currents ordinarily form thick deposits frequently divided into prismatic columns, sometimes in large irregular pieces, all indicative of slow cooling. The Palisades on the North River are examples of basaltic columns. Basaltic deposits of different kinds. If basalt is found in well-ascertained currents traceable to craters, entirely similar matter is found in very different positions. There is a great deal of it that forms extensive tables of considerable thickness, constituting vast plateaux, or heaped-up fragments on different mountains at the same level, the heaps corresponding, and seem to belong one to the other like parts of the same whole, showing a vast dislocated table. Basalt also forms isolated masses, hillocks in the midst of plains, sometimes very distant from every other formation of the same kind. It is found in seams, sometimes enclosed in the soil that conceals it, sometimes rising here and there like a wall, or presenting various hillocks on the same line of direction. All these dispositions of basaltic deposits, as well as currents or streams, are sometimes found together in the same country. In some countries, on the contrary, there is no trace whatever of volcanic cones or of currents. In all cases, however, the rock possesses the general characters of basalt, and seems to rest indifferently on every kind of formation, even on vegetable earth. Tabular basalt brings to mind the great tables of Iceland, especially those of the eruption of 1783. They possess all the characters of lava that has been arrested on horizontal plains or filled depressions. The lower part is compact, crystalline, and most frequently divided into vertical prismatic columns, and the upper part is porous, cellular, scoriform, irregularly divided, and terminating on a plain horizontal surface. When the mass is composed of several stories, the separations are sometimes formed by thin bed of rapilli, and most generally they are distinguished by alterations of compact and porous matter, which characterizes each particular effusion. These characters leave no doubt as to the igneous origin of these deposits, but there are still others. When we can penetrate beneath basaltic tables, as in cases where they rest on movable formations, we almost always find the inferior part of the mass presents a multitude of appendages, which penetrate into the soil, indicating a liquid matter which has been molded in rents or crevices. The earth on which the mass rests is often found calcined through a greater or lesser thickness, and the debris of plants it contains are carbonized. On the other hand, there is often found on the surface of basaltic tables points of scorification, particular elevations, and even crateriform depressions towards which the melted matter seems to have retired at a certain moment before solidifying. Basaltic hillocks or bosses are of different kinds. Some seem to be the remnants of an extensive table which had been partly destroyed. In this case, the principal mass of the boss belongs to one or another species of soil, and the summit only is basaltic. In others, on the contrary, the whole hillock is formed of basalt, and the base is lost in masses of sand and debris, which prevent us from seeing what is beneath. Some others are attached to veins or seams. The composition of these hillocks, like that of tabular basalt, varies. Basaltic veins or seams. Basalt is frequently found in veins. Most frequently the mass of the seam or vein is compact or irregularly cracked, but it is often divided into prisms, perpendicular to the parietes of the crevice, which then become the cooling surfaces. The matters in these seams are rarely scorified, but some instances are met in Vivarais and Auvergne. Most frequently, basaltic veins are prolonged to the surface of the soil, where they present their outcrop, but it frequently happens, also, they terminate above in pointed masses, sometimes bifurcated, which are lost in the rocks through which they pass. This circumstance positively indicates that the basalt was not introduced from above, and that it could only have been injected from the interior towards the exterior of the earth. Sometimes the vein glides betwixt two strata, which it follows to a greater or less extent, or in ramifying, it launches a part of its mass into the interval and ends by terminating there in a corner, whence it spreads into all the little fissures of the rock. Along the course of basaltic veins, the outcrops of which are seen on the surface of the soil, various isolated hillocks are frequently observed, several together at various distances apart, which appear to be nothing more than partial ejections, like the cones formed along the same crack in modern volcanic eruptions. Most often they are almost entirely composed of scoria, but some are found which consist of pure basalt. Sometimes, instead of hillocks, there are effusions of tables of more or less thickness, which are also found along the course of a vein. All these circumstances tend to explain the formation of isolated hillocks, as well as the series of hillocks in line, found in a great many localities, where the internal vein has found here and there an outlet. Action of basalt on adjacent rocks. The calcination of clays and the carbonization of vegetable debris lying beneath basalt have been mentioned. Granite traversed by veins of it is very much altered. Portions of rocks which have been enveloped in basalt are often melted on the surface. Quartz and feldspar are cracked, sometimes enveloped or penetrated by vitreous matter. Marls, earthy limestones in contact with basalt or pierced by its veins, and especially fragments of matter drawn into the basaltic mass, are converted into compact limestone, sometimes approaching the saccharoid state. These limestones also become magnesian and are converted into true dolomites, distinguished from the rest of the enveloping mass by their slow effervescence. Dolomization seems to be due to the presence of igneous products. When basaltic veins pass through carbonaceous deposit, the clays are calcined. The coal is deprived of its bitumen and assumes a bacillar or berry-like structure. Basaltic deposits in tables, hillocks, or veins are more abundant on the surface of the globe than all the lavas in ascertained currents, which is doubtlessly owing to their mode of ejection. Basalts are found in France, on the borders of the Rhine, in Saxony, Bohemia, etc. Iceland contains a great quantity, and the same rocks predominate in the West Indies, at St. Helena, etc., and in almost all the islands of the South Seas. Basaltic formations are noticed wherever they occur, in consequence of the tendency of the principal rocks to divide into long prisms, the varied arrangements of which have often excited the admiration of the curious. Here all the prisms converge at the summit of a hillock. There they form magnificent colonnades of the most picturesque appearance. In another place all the columns, broken at the same level, present a pavement composed of pieces regularly joined, extending over a greater or less space, and sometimes formed into an amphitheater, one above the other. The grandeur, the imposing appearance of these pavements have obtained for them the name of Giant's Causeway. The Giant's Causeway in Ireland is famous, but a similar structure exists in France. Sometimes there are excavations in the middle of basaltic masses, or trappean rocks, which resemble them most, some of them forming very remarkable grottos. The most celebrated is Fingal's Cave in the island of Staffa, which is formed in the midst of a trap, divided into prismatic columns with the utmost regularity, and into which the sea continually beats. Others exist in the basalt properly so called. There is a famous one on the banks of the Rhine between Treves and Koblenz, near Bertrich-Baden, the columns of which are composed of rounded pieces, which has caused them to be compared to piles of cheeses, whence the name of cheese grotto, common in the country. The trachytic formation is very extensive. It presents itself not only in conical hillocks, running in narrow bands, but also in piled-up tables on the surface. Trachyte constitutes great mountains, most frequently united in very extended groups which form very high masses, ordinarily the highest in the country, covered with asperities. Their sides are broken into valleys and deep ravines, with steep escarpments, and with all the circumstances of lofty chains. The trachytic formation is in strong contrast with the igneous rocks we have heretofore studied, although close inspection would show them to bear various relations with deposits of basalt or lava. The rocks which constitute the trachytic formation are extremely varied. Most of these substances, as their name indicates, are rough to the touch, because they are most generally finely porous, sometimes cavernous, scoriaceous, pumice-like. But there are some that are perfectly compact and present the porphyritic structure, frequently with tints of gray, red, brown, or black, on which are white crystals of albite and of rhyolite. There are some more or less earthy, ordinarily of clear tints, called domite, because the Puy de Dôme is composed of it. The base of all these rocks, which is inattackable by acids, is albitic or rhyolitic, formed of a multitude of microscopic crystals mingled together, the whole constituting a mass which is more or less compact. The disseminated substances are albite, in crystals of greater or less size, rhyolite, black mica, amphibole hornblende, but rarely pyroxene augite. Quartz in crystals and chalcedony in small nodules are also found in it sometimes, and especially in a certain very cavernous species, hitherto found only in Hungary, the cement of which also contains many small striated balls of spherulite, from the Greek spheria, a sphere, and lithos, a stone. The name phonolite, from the Greek phone, a sound, and lithos, a stone, has been given to rocks more or less analogous to trachyte, but differing from it in this, that their base is attackable by acids, leaving a residue of rhyolite. These rocks are often compact, grayish or greenish, sometimes porphyroid, but in which disseminated substances are rare. They are frequently divided into plates or leaves of variable thickness, and in certain cases the whole mass is divided into prismatic columns, which are more frequently divergent and contorted than vertical. These rocks are most often compact, grayish or greenish, and sometimes porphyroid, but in which disseminated substances are rare. They are frequently divided into plates or leaves of variable thickness, and in certain cases the whole mass is divided into prismatic columns, which are more frequently divergent and contorted than vertical. Phonolites have been sometimes confounded with certain porphyroidal varieties of trachyte, which possess nearly the same appearance, but not the same solubility. Some trachytic formations contain considerable deposits of obsidian and of pearlite, with all their graduations to pumice. Their abundance and character vary according to locality. They preponderate in some countries, while in others scarce a trace of them is to be seen. Diorite, trap rocks, amygdaloid, etc. There is nothing more analogous to basalt than certain black rocks, some of which, according to the numerous graduations they present in deposits of which the elements are distinct, must be mixtures of albite and of amphibole, and others are of an unknown or at least doubtful nature. The first are designated in France under the name diorite, and in Germany they are known as grunstein. The others have long borne the appellation of trap, from the Swedish trappa, a stair, the nature of which it is still impossible to determine definitely. These rocks bear some relation as much by their position in certain localities as by their mineralogical character to certain substances called amygdaloids, in consequence of the nodules of various matters they contain, which are known in England as toadstone and winestone, the nature of which is often not better known. For a long time these rocks were supposed to be of aqueous origin, but it is now ascertained they are from igneous causes. At first, in spite of the absence of scoriaceous matters, these rocks, and especially those named trap, present all the features of basaltic deposits. They are found in isolated hillocks, or in tables of greater or less extent. Their mass is often divided into prismatic columns, which possess precisely the same appearance as basaltic colonnades, giants' causeways, and all the forms of basalt. On the other hand, these substances are frequently found in veins, and it is remarked that these veins or seams terminate above in a pointed mass, or in their course send off small ramifications into the rocks through which they pass, small masses, sometimes isolated, sometimes communicating with the principal mass by a thin seam. The enclosing rocks are sometimes occasionally perforated by small ramifications, even to the finest fissures. These circumstances evidently show these are not cracks filled from above, and can be regarded only as injections from the interior, thrown with sufficient force to penetrate the smallest fissures, to detach and carry away fragments of rocks sometimes found in their substance. All of these circumstances are exactly the same as those seen in basalt. It is the same with beds, in appearance regular, seen between sedimentary layers. Observation shows they are only ramifications of veins. This is clearly seen at Trotternish in the Isle of Skye, where a great seam of trap communicates with a bed of similar matter, which is itself divided further on into 3 branches. Hence it is evident the intercalation of trappean rocks in arenaceous beds is the result of an injection, which followed the separation of the beds of the sedimentary deposit to a greater or less distance, as in the case of the basalts of the Villeneuve de Berg. Serpentine and diallage. Different porphyries. Magnesian rocks called serpentine often accompany trap and diorite. They very frequently form seams or veins of themselves. Serpentines and euphatides are often injected in all manners into calcareous deposits belonging to the Jurassic period. Sometimes they form veins. They often present breccias of every species which constitute the marbles called verd antique, verd d'Egypte, etc. The limestones mingled with these rocks are all in the saccharoid state, and furnish the most beautiful statuary marble and the most brilliant breccias. Yet, if we examine them carefully, we find they belong entirely to the compact and more or less earthy limestones, the surrounding deposits of which they are evidently a continuation. The schistose clays and sandstone, which alternate with the last, are found converted in the others into jaspers of different varieties. The appearance of pyroxenic rocks, melipharies, porphyries, the constituents of which are united by a black cement, and other porphyries which belong to them, is productive of circumstances of the same kind. M. de Beau long since pointed them out in the Tyrol, and subsequently in Upper Lombardy. They are also found all along the Alps, and are represented in the same direction in Provence in the midst of the mountains of Esterel. All is upturned in the neighborhood of these rocks, which in coming today have upheaved around them calcareous deposits of different formations, dislocating and placing them in the most abnormal positions. Wherever they are in contact with these porphyries, and to a considerable distance beyond, limestones are transformed into dolomite, and in such a manner that the same deposits are of simple limestone in some parts, and of dolomite injected into those which are near to rocks of crystallization. What is most remarkable is that the few organic remains met in these modified limestones, even the shells of mollusks or madrepores, are found changed into magnesia. This clearly proves that an action subsequent to the formation of the deposit has produced the dolomization, for no shell or madrepore exists which naturally contains magnesia, either in the living or fossil state, where the deposit has undergone no modification. Feldspathic porphyries are often so characterized that there can be no doubt of their igneous origin. Not only are they found in the veins of the midst of rocks, but they act like trachytes in passing through split rocks, the fragments of which they glue together to form conglomerates. They often unite themselves in the most intimate manner to arenaceous deposits, which Lesson 9, Part 2 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Rick Sanborn, Alexandria, Virginia. Elements of Geology by William Ruschenberger. Lesson 9, Part 2. Granitic Rocks. There can be no doubt as to the igneous nature of the preceding rocks, from the manner in which they are injected into all kinds of deposits, and from the modifications they produce in the substances they pass through or upheave. The same is true of all granitic rocks, that is, of granite properly so called, of syenites, which resemble them more or less in appearance and pass into them in all manners, of certain gneiss rocks, which belong immediately to one or the other, etc. In short, it is inferred from a great mass of observations, collected first in England by Dr. McCulloch, afterwards verified by other geologists, that the granites, which are massive rocks, and therefore distinct from aqueous deposits, which are ordinarily stratified, act, on their appearance, exactly like the traps, diorites, and porphyries. In the valley of Glentilt in Scotland, granite is found injected into calcareous deposits, which alternate with argillaceous schists, into which it sometimes forces separate masses. Fragments of limestone are also found enveloped in the granite itself. In other places, vertical veins traverse the rocks, sometimes entirely, sometimes terminating in pointed masses like the diorites and basalts, which also shows that the matter came from below upwards, and that it was driven with great force. These facts do not present themselves in a particular locality only, but are observed in all parts of the world. The state of pasty fusion in which the granites were is indicated by the manner in which these rocks are enveloped in certain sedimentary deposits, or effused on the different soils they pass through. In the coal measures of La Plau, to the southwest of Ussel, a portion of the formation has been enveloped by porphyroid granites, which are found above and below. The coal there is hard, as on all the plateau, and the deposit is very irregular. In a great many localities we find granite superposed on all sedimentary deposits from schists, and the most ancient rocks to those of the Jurassic period. There are different places in the Alps where one may touch at the same time superposed rocks of crystallization and the subjacent sedimentary deposit. The action of granitic rocks on those through which they pass is the same as that of the preceding rocks. Compact, oolithic, and earthy limestones are converted into saccharoid limestones, from which organic remains have most frequently disappeared. They assume bright colors of every kind, green, red, black, etc., and in contact with mica are filled with garnets and various other crystalline substances. They are often converted into dolomites, which are nowhere more abundant than in formations of granite, and sometimes into gypsum, as proved by the outcroppings of this substance in certain parts of the Alps. Clays and various arenaceous substances are transformed into jasper, and finally assume the characters of micaceous or talcose schist and gneiss. Simple sandstones of sedimentary formations, on the approach of granite, are converted into beds of granular quartz. It sometimes happens that modified schistose sandstones still preserve their arenaceous structure, although they may have been very solid. Even mica schists to which they pass contain here and there thin strata of sandy quartz, interposed between laminae of mica, which seems to announce the remains of ancient modified sandstone. Granitic rocks referred to different ages are very abundant on the surface of the globe, being sometimes found in very lofty mountain chains, and sometimes forming rounded hills disintegrated on the surface and covering considerable extents of country. Metalliferous lodes, veins, masses. The dolomization and sulfatization of limestones, the presence of various substances in adjacent rocks, are not the only facts referable to the passage of igneous rocks from the bosom of the earth. It also happens that on the contact of the new with the ancient rock, the deposits are filled with different metallic minerals, either disseminated or injected into fissures and between beds, or accumulated in small masses, sometimes united by slender threads. This has been remarked by M. Dufresnoy in regard to iron ores in the Pyrenees, which are found either in limestone or placed between sedimentary deposits and the granite which upheaved the solid mass. It is evident lodes or seams of ores are related to igneous action. As to those which are deposited in veins, it is to be remarked we have never had occasion to follow them to a sufficient depth to ascertain whether they terminate abruptly, and consequently whether they fill cracks opened from the surface towards the interior, but they are known to terminate in pointed masses upwards, as at Joachimsthal in Bohemia, and in many other places in small veins which have been worked. This circumstance leads us to think that metalliferous veins have been produced by an injection from the interior towards the surface, in the same way as the stony veins we have mentioned. Besides, veins of this sort are strongly united to the others. Thus, at Pontgibaud, the same veins are sometimes granitic and sometimes metalliferous. In many other places, metalliferous veins accompany porphyritic veins, and even veins of basalt, as in Bohemia, and the two substances mutually penetrate each other, sometimes one and sometimes the other being above. On the other hand, we very frequently find in the same localities stony and metalliferous veins running parallel to each other, sometimes crossing in different ways, one throwing the other aside, and thus mutually producing more or less marked faults. Sometimes the stony displace the metalliferous veins. Sometimes, on the contrary, the latter turns aside the others. In everything, they act exactly alike, and it is impossible not to refer them to the same origin. It is also remarked that veins generally follow great lines of dislocation of the crust of the earth. We find in metalliferous veins the influence of those which pass through or accompany them, and which deposit, to a certain extent, substances not previously observed. The influence of the rock pass-through is seen in metalliferous veins as well as in those of trap, and it has been long known to miners that a poor vein in a determined bed at once becomes rich by passing into another, and on the contrary, hence the sudden success and unforeseen reverses in mining operations. Metalliferous masses being in general but accumulations of small veins running in all directions, or an abundant dissemination in the midst of a stony substance of the kind attributed to the action of fire, it is clear these deposits are produced in the same way as those just mentioned. These masses, the principal of which present us with ores of tin, copper pyrites, and magnetic iron, are chiefly composed of granites, porphyries, various magnesian rocks in which the ores are found. The metalliferous mass of Zinwald in Bohemia is a particular granite enclosed in a porphyry. That of Altenburg in Saxony is a porphyritic mass enclosed in gneiss. The celebrated mass of magnetic iron of Taberg in Sweden is a mass of diorite enclosed in gneiss. That of Cognac in Piedmont is a mass of serpentine driven into the calciferous micaceous schist. Metalliferous lodes in regular beds are merely veins which have followed the stratification, as we observed in traps, or deposits which were formed in contact with sedimentary beds and the fused matters that upheave them. But we must not confound the masses and veins just mentioned with certain deposits of oolithic iron ores found in sedimentary formations. Among the latter, some form beds of more or less extent in the midst of calcareous formations. Others fill wide apertures of little depth from above, which sometimes communicate with caverns, but these facts are of a different order from those just described. Metamorphism. From all the facts we have cited, which might be vastly augmented in number by reference to details in many localities, we must conclude that crystalline rocks, which are all formed of silicates, extensively varied and mixed with each other, have been produced by the action of fire. that at different epochs they have dislocated, uplifted, or overturned the sedimentary deposits, modifying the mass in all manners, and it is to these great phenomena that are due all the seeming disorder observed on the surface of the globe, as well as all the successive changes, the traces of which may be perceived at every step. When we see earthy or compact limestones become crystalline on the approach of these different kinds of rocks, to fill with various substances they do not contain at certain distances, to be charged with magnesia in cracking in all parts, and to disintegrate with more or less facility, when schistose clays and arenaceous substances are converted into different jaspers, and become charged with mica and amphibole, and assume the characters of gneiss, of micaceous or talcose schist. Finally, when sandstones are transformed into beds of solid quartz, can we be surprised that most modern geologists have adopted the idea of complete changes effected in a great number of sedimentary deposits, and that they resort to this metamorphism, long since perceived by Hutton, Playfair, and Dr. McCulloch, to explain a multitude of facts observed especially in deposits anciently designated under the names of primitive and transition formations. The facts appear so extraordinary that we may be led to suppose a little exaggeration, but we must reject evidence to deny that there are saccharoid limestones, dolomites, mica schists, gneiss, granular quartz, etc., which are the result of a change produced in earthy or compact limestones, clays, sands, etc., of sedimentary formation. Is it then so ridiculous to suppose that such has been their origin in all cases? These ideas, now more striking because they are expressed by a proper word, are nevertheless not absolutely new. All works on geology are actually full of them, and the facts are not less remarkable from being expressed in other terms. There is no description of a country, going back to the time of Saussure, whose works are still remarkable for the fidelity of details, in which are not seen numerous passages of different arenaceous deposits to rocks of crystallization, of schistose grauwackes to talcose schists, to micaceous schists, and from these to gneiss, or the passage of sandstone to different kinds of granite and porphyries on which they rest, etc. Is not the fact of these modifications, now described under the term of metamorphism, here clearly indicated, to which time has added only more details and greater precision? It is certain that in departing from schistose grauwackes, for example, and going towards some mountain or islet of crystallization, we find these substances themselves become more crystalline in character, and sometimes, without losing the organic remains they contain, become filled with new minerals. In Brittany, these schists are filled with andalusite, sometimes staurotides, near all granitic deposits. Elsewhere, as in Vosges, in the mountains of Var, we see them pass to mica schist, and the latter to gneiss, which itself insensibly becomes granite. Now, as if the intimate union observed were not sufficient, these mica schists, then the gneiss itself, contain carburetted schist, or even graphite, veins of anthracite, which remind us of the deposits which are found further in the schists of grauwackes, and sufficiently marked to determine the pursuit of coal. It is, then, evident that all the rocks we have cited, no matter how they may differ, are only modifications, mere metamorphoses of one or all, and as it is in approaching granitic rocks, evidently produced by igneous action, that these metamorphoses become more and more marked, it is clear that it is to the influence of the latter that they are due. The same influence is manifest on the sandstones of different ages, at various points where they are in immediate contact with granite. The modifications are such that the special name arkose has been applied to them. They then pass through all shades to granite and become filled with different substances that they do not contain elsewhere. Near porphyritic ejections, schists frequently present modifications of another kind. Here the most earthy and the most evidently sedimentary parts pass by degrees to compact substances, more and more feldspathic, preserving more or less of their schistose character, and finally end by containing crystals of feldspar. Elsewhere these same matters pass to solid clays containing veins of limestone, then nodules of the same substance, which assume all the characters of amygdaloids, losing only little by little their schistose structure. The same phenomena are remarked between diverse sandstones and porphyries that intersect them. The arenaceous matter gradually hardens, becomes more compact, and finally unites with the porphyry in such a manner that it is not easy to determine where one begins and the other ends. All these facts pertain really, with the exception of some details, to ancient geology, and it is only the manner of explaining them that has changed. Everything conspiring to demonstrate that crystalline substances have been produced by the action of fire and forced through sedimentary deposits, we now understand that the latter have been modified or metamorphosed in different ways by their influence in a degree corresponding to their proximity. The effects entirely cease only at greater or less distances. It is conceived that one part of these metamorphoses of sedimentary formations arise from the simple action of heat without new fusion, but sufficient to modify the texture of masses, and even to unite elements in other proportions, as happens when transparent glass is submitted to a temperature insufficient to melt it, in which, nevertheless, a new crystallization takes place. But this idea is not sufficient of itself. We must conceive another action which we are not yet able to explain or account for, in virtue of which particular substances have been born or developed in the midst of rocks found in the neighborhood of diverse upturnings, of which the globe is the theater. We readily conceive of the introduction of sulfuric acid, which is frequently formed in volcanoes, but we do not understand that of magnesia and different species of silicates, and as respects them, all is still purely hypothetical. We may compare these facts to cementation, by means of which iron is converted into steel, a phenomenon which is manifested not only in contact with carbonaceous matter, but extends far into the ferruginous mass, and even takes place at a distance, according to the experiments of M. Laurent, who has shown that carbonaceous matter may penetrate iron even through porcelain tubes. We also know from experiment and many effects observed in manufactories that the peroxide of iron, the oxides of chrome, etc., are volatilized and penetrate the substance of bodies that envelop them. The experiments of M. Gaudin with a blowpipe on a detonating mixture show that silex, magnesia, and lime are also volatile oxides, the first after fusion, the others before being melted. These facts evidently lead to an explanation of all the phenomena of metamorphism and the intrusion of foreign substances into sedimentary deposits, either in veins or in a state of dissemination. Effects attributable to erosion. We have seen that waters act by the carbonic acid they contain, by their weight, by their dissolving power, by their transporting power, by their shock, as in waves of the sea, and thus denude continents. We have also pointed out that in arenaceous formations, valleys are produced by erosion, precisely as ravines are formed in sandy soils by the action of rainwater. Hence we may infer that in every revolution that movements of the soil must have necessarily determined the waters, thrown forcibly sometimes on one side and sometimes on the other, must, as in our time, during earthquakes, have ravaged, divided, and modified pre-existing deposits in various ways. Many circumstances may be explained by erosion of waters and the denudations it occasions. At first, when we see more or less numerous hillocks of sedimentary matter in a country, whose summits are nearly on the same level, and whose strata correspond with each other, we are naturally led to consider them as evidence of great removals effected by the waters at certain epochs, the relative dates of which remain to be ascertained. In this way we explain according to appearance all the sections which the sandstones present on the eastern slope of Vosges, that remarkable assemblage of peaks of every form seen at Aldersbach in Bohemia, the numerous hills that cover Ross-shire in Scotland, the Gypsius Hills in the neighborhood of Paris, all composed of the same beds placed at the same height, and the division of the basaltic tables that crown the hills in certain localities, as well as the rupture of certain lava floods that had barricaded valleys, etc., etc. Valleys which intersect movable formations are evidently produced in the same way, and there is no doubt that most of those existing in solid formations have been modified by erosion of water after the rupture which gave origin to them. In this way we may explain the smoothing of all their parietes in a great many localities, and the widening of their upper parts. The great lakes sometimes found at the extremity of valleys, as on the two slopes of the Alps in Switzerland and Piedmont, may be attributed to the efflux of waters which rushed through them at the period of some great catastrophe, and emptied with violence on the plain in which they terminated. Many other facts are explained by the power of erosion and transport by water. When, by studying faults in the interior of mines, we clearly see that the beds no longer correspond and that a part of the formation must have been uplifted, then, if the soil is level on the surface, we naturally ask what has become of the beds which ought to have formed a hillock. It is clear these beds must have been removed, which we may conceive was only by a posterior action of waters, which carried away the debris and perhaps spread them over the surface. In the same way, when we see a vein form a projection, a dike on the surface of the soil, we conceive that it could not have been formed in this manner, and that the uncovered part must have been once encased, just as that is which is now covered. The surrounding formation has been uplifted then afterwards, at least along the whole actual height of the projection. Something similar necessarily took place at points where veins crop out on the surface, or are covered by movable soil. It is not probable that melted matter injected in the crack would be immediately arrested at the surface of the earth, and it is presumable that the soil has been removed and subsequently covered by various clearings. We are thus led to understand how many basaltic masses now offer no trace of scoriaceous matter, neither in themselves nor in their vicinity. These imperfectly aggregated debris have been subsequently carried away by the action of water, and perhaps it is the same with the scoriaceous matter which must have accompanied the appearance of trap. The prodigious power exerted by waves and the effects they have produced in our times lead us to think also that all the rocks formed around islands and reefs at a short distance from coasts, or the often fanciful groups in the midst of the sea, are also remnants of some great division caused by water, as much in removable matters easily disintegrated as in masses broken by earthquakes and different movements of the soil, and certain parts of which have been afterwards removed either by repeated shocks of waves or sudden debacles. In this way we may explain the numerous accidents in rocks which bound coasts, or are isolated in the midst of the ocean, as in the sinkings of the chalk of Etretat, and the sections of porphyritic or granitic rocks in the Shetland Islands. It is conceived that straits, more or less extended, may have been formed by the two combined actions of currents of water and rupture which the soil might have undergone by upheaval or subsidence at determined epochs. From these observations we see that many effects may be attributed to the action of water which cannot be in any other way explained. We may see denudations in the midst of mountains and valleys, recognize the ancient sinkings which bordered seas at different ages, and hence appreciate their limits, as well as all the other circumstances connected with them. Reference to the immediate action of water should be always carefully restricted to the movable or loose matters found on the surface of the globe, for when solid matters are in question, which water attacks too slowly, we are led to think that currents and waves cannot act effectively until the soil has been previously prepared by the fissures or deteriorations caused in rocks by movements of the earth. We must not confound with divisions produced by water certain accidents which may result from shrinking produced by metamorphism. This probably takes place in dolomites, which follow compact limestone in a great many places, as in the Tyrol and the Cevennes. Masses of these matters are frequently split and slashed in all directions on the surface, particularly on the summits of mountains or on plateaux, very nearly in the same way that calcareous deposits are cut by water. Now the change from a simple to a double carbonate, specifically heavier, requires contraction in masses submitted to dolomization. Therefore the latter must be split and cracked in all directions, and the denudations they
Lesson 10, Part 1 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Amy Craymore. Elements of Geology by William Ruschenberger. Lesson 10, Part 1. Classification of formations. Different kinds of stratification. Dip, strike, conformable stratification, unconformable stratification, false stratification, the form and habits of an animal deducible from a single bone, relative ages of the principal catastrophes of the globe, systems of upheaval, classification of, state of Europe at different epochs of formation, deluge, geogeny. Classification of formations. As already mentioned, the several formations are divided into two classes, namely, first, massive or igneous formations, which are produced by the action of fire and are not stratified. The terms primitive and transition have been applied to these formations, but, as they are inexact, they are going out of use. Second, sedimentary formations, which are deposited by the action of water and are stratified. Massive or igneous formations escaped from the earth in a state of fusion and became solid by cooling, but without being stratified. They are divided into two classes. First, those crystalline rocks which are not traceable to the crater or any volcano now recognizable, such as granite, trachyte, etc. Second, massive rocks of a slightly crystalline structure, traceable to volcanoes, such as modern and ancient lavas and basaltic formations. Sedimentary formations are arranged according to their relative antiquity. They are divided into groups composed of those which appear to have been formed either at the same epoch or during a geological period, during which the general condition of the earth appears to have undergone no important change. These formations are commonly divided into 5 groups, namely, first, primary stratified rocks, in which neither organic remains nor fragments of the most ancient rocks are found. This group includes gneiss, mica schist, quartz, transition limestone, and argillaceous schist. Second, the transition formations, which rest on the primary stratified rocks and contain fossils of plants or animals, but which appear to have been deposited prior to the creation of the most perfect beings of either kingdom, and only contain the remains of aquatic animals, which are all very different from those of our times, such as trilobites. This group includes fossiliferous schists, transition limestones, etc. Third, the secondary formations were deposited at periods less remote than the transition, and consequently rest on beds of the latter, or on primary rocks, but they go back to a time when the state of the globe was very different from its present condition. Very few mammals then existed. Ammonites are among the most characteristic fossils of the secondary formation. The secondary formations are subdivided into, first, the Carboniferous, which includes old red sandstone, mountain limestone, and coal. Second, the Saliferous, embracing new red sandstone, muschelkalk, and variegated marls, forming the Triassic system. Third, the Jurassic, embracing the Liaskic, the Oolite, the Wealden groups. Fourth, the Cretaceous, embracing the lower greensand, Gault, upper greensand, chalk marl, chalk without, and chalk with flints. Fourth, the Tertiary formations, which, being more recent, covered all the preceding formations. They date from a period when animals and plants belonging to all the great classes existed, but still anterior to the creation of man. The Tertiaries are subdivided into three groups. First, the older Tertiary or Eocene, which embraces the London clay, Bagshot sand, and Paris basin. Second, the Middle Tertiary or Miocene, which embraces the coralline crag, red crag, and molasse of Switzerland, etc. Third, the Newer Tertiary or Pliocene, which embraces Norwich crag, the sub-Apennine beds, the brown coal of Germany, etc., as well as the superficial deposits called Pleistocene, consisting of diluvium and alluvium. Fifth, the modern formations, which are contemporaneous with the existence of man on the earth and are still being formed. The subdivisions embrace, first, peat bogs formed by the accumulation of the debris of certain plants. Second, coral formations, from the multiplication of polyparia, as seen in the coral islands of the Pacific. Third, concretiary formations, formed by calcareous and other matters, found in solution in the waters of certain springs, etc., as travertine, stalactites, stalagmites, etc. Fourth, formations from transport or drift, as fluviatile, terrestrial or marine alluvions, dunes, etc. Fifth, humus, or vegetable earth, formed directly by the disintegration of other formations, and their mixture with the products of decomposition of plants and animals, spread in a layer of more or less thickness on almost every point of the earth's surface. All these deposits are superposed one on the other, in a constant order, and if it were possible to make a sufficient section in a part of the globe where they all exist together, we should find a succession of 27 stories or layers, distinguishable by their different characters. But each of the great deposits is divided and subdivided into various layers, more or less distinct, composed most frequently of arenicious substances, clay and limestone, of different degrees of consistence, and beds of varying thickness. The assemblage of their alternate beds often forms successive layers, several hundred yards thick. It is evident that if such sections existed in the crust of the earth, we could see all the beds and easily distinguish their relative ages by their number in the order of succession, the deepest being the most ancient, and that forming the surface being the most modern. It would then be sufficient, in sections of different depths, which would be found elsewhere, to count from above downwards, to know always where we were, and even the variations that a determinate bed might undergo in different places would offer no difficulty to observation. But such is not the case. The numerous escarpments we meet always present us with but a very small portion of the series, sometimes in one part of its thickness, and sometimes in another. We never see the entire series, and it is only by combining the observations made in different places that we have been able to establish what we now know. At the same time we discovered the particular circumstances of formation of each deposit. In consequence of the divisions of the whole, it is conceived, it might become very difficult to distinguish them, and that in presence of an escarpment one might frequently be unable, at first sight, to decide on the point in the series to which it ought to be referred. Indeed, different beds of the same nature, which succeed each other in the series, are often very analogous, the limestones of one story more or less resembling those of another, and the same is true of different deposits of sandstone and clay. It also happens that the same deposit varies at different points. Here it is a compact, and there an earthy limestone. In another place the same limestone is found mixed with sands, and further on it is nearly pure sand, etc. The injection of crystalline matter adds to the embarrassment, by the modifications it causes in the texture, and even in the nature of everything in its vicinity. It is also conceived that the fewer the beds superposed in the same place, the greater the difficulties, and they are at a maximum when we meet an isolated deposit, without knowing on what it rests, and not being able to perceive anything it covers. This occurs in a great many countries. It often happens, too, that one or more beds are entirely wanting in one locality, and then the deposits which should naturally separate them, being immediately superposed, exposes the observer to attribute to the succeeding beds an age very different from that which really belongs to them. To obviate this difficulty, we have observations on the continuity of beds, some of which we can follow from points where they present certain characters, to others where they offer different characters, from points where they are entirely isolated, to others where we can see on what they rest, and what covers them, etc. We have also observations on stratification and inclination of different beds towards one point or the other, which enable us to infer that such a species of deposit passes below or above another, found isolated or at a distance. Fragments and rolled flints may evidently indicate the priority of deposits which contain them, to those from which they came, and thus furnish a good means of distinction when they are sufficiently characterized. And the nature of organic remains has now become a very decided aid in distinguishing different formations. Different kinds of stratification. There are two kinds of stratification, one horizontal, which is the natural stratification, according to which all transported matters are deposited under water, the other more or less inclined, resulting from upheavals which have taken place at different epochs. In the latter we distinguish the degree of inclination or dip, which may be vertical, and the point of the horizon towards which the beds dip. The last part of the observation determines the direction of the crests of the strata, or, as we say, the strike, or direction of the strata, which is always at right angles to the dip, or direction of the inclination, and which also indicates the direction of the movement by which the effect was produced. But the first observation of horizontal or inclined strata is not always sufficient. It is frequently necessary to distinguish the relative stratification of different deposits, which is reduced to the concordance or the discordance which may exist between them. The dip of strata is the point of the compass towards which they slope, while the angle they form with the plane of the horizon is called the angle of dip. The term dip refers to the inclination of a stratum, and the term strike is used to express its direction. Thus, strata may dip to the north at an angle of 45 degrees. In this case, the strike or line of bearing must necessarily be east and west, because the strike is always at right angles with the dip. Dip and strike may be aptly illustrated by a row of houses running east and west, the long ridge of the roof representing the strike of the stratum of slates, which dip on one side to the north and on the other to the south. The angle formed by the roof with the plane of the horizon would be the angle of dip. Conformable stratification. When all the strata of a formation are parallel to each other, that is, when there is a concordance between them, whatever may be their general position, horizontal or inclined, convex or concave, they are said to be conformable. Unconformable stratification. When the strata of a formation are not parallel to each other, when there is a discordance between them, as where horizontal strata come in contact with inclined beds, or where the relative inclination of beds is different, they are said to be unconformable. Where a superior deposit, whether stratified or not, rests on a section of the beds of an inferior deposit, there is a peculiar kind of unconformable stratification, sometimes called transgressive stratification. There is another kind of unconformable stratification where the beds are parallel, This occurs where a horizontal deposit, after being furrowed in different ways by water, is again entirely covered by a deposit of the same nature, which fills up all the excavations. In this case the strata are unconformable where they join end to end with beds on the slope of ancient valleys. To ascertain the relations in the stratification of two deposits, it is necessary to pay great attention to the particular structure of the beds, which in certain cases may lead us into error. For example, seeing that the divisions of the bed A dip towards the left of the figure, we must not conclude that the stratification is unconformable with the bed B. This appearance results altogether from the structure which the bed A owes to its rapid formation under particular circumstances. Schistose substances often present many difficulties in this respect, because their divisions run in every direction, and sometimes the least apparent is the real stratification. For instance, we might suppose the deposit A rested conformably on the deposit B, and that the mass C is an unconformable stratification, from regarding the finest divisions of the schist as indicative of the stratification. But we might also consider the deposit A as unconformable and the deposit C as conformable, from regarding the parallel joints I to K as those of stratification, and it is possible to view both A and C as unconformable relative to B, by considering the other joints as those of the strata. It may be often difficult to decide. Nevertheless, in general, the schistose division is frequently a structure which has perhaps a certain crystallization of micaceous matter, and it is this character, therefore, among others, that we must ordinarily select. Now the joints of dislocation, for one or the other division must have been thus produced, are splits united and well marked, often a little open, which are ordinarily prolonged into several consecutive deposits, while the joints of stratification are more undulated and more adherent. The most irregular undulations of true strata are often traversed throughout by the schistose structure, without alteration. This circumstance evidently shows that this structure is in effect posterior to the contortion of the beds, and may be attributed to a metamorphism more modern than their derangement. The extraordinary Lesson 10, Part 2 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Elements of Geology by William Ruschenberger. Lesson 10, Part 2. Organic remains, which are very numerous in most sedimentary deposits, also furnish a means of recognizing strata. There are some which are peculiar to certain deposits, and are not found elsewhere, and which are therefore distinguished as geognostic horizons. Thus the Silurian or Devonian formations are clearly recognized by the presence of the remains of a certain family of crustaceans named trilobites. The Gryphea arcuata is found in the lias, and only in it. The Exogyra virgula belongs to the upper part of the Jurassic formation. Baculites and Turrilites begin and end in the Cretaceous period. Although the remains of mollusks and small animals are found entire, and therefore easily recognized, those of large mammals, etc., often exist only in fragments, and without the necessary knowledge, the family, genus, or species could not be discovered. But those well acquainted with comparative anatomy, and the laws which govern in the organization of animals, can deduce the form and even the habits of an animal often from a single bone. Quote, "Every organized being may be considered as an entire and perfect system, of which all the different parts mutually correspond, and concur in the same definitive action by a reciprocal reaction. No one part can undergo a change without a corresponding change taking place in all the others, and consequently each part taken separately indicates and gives the key to a knowledge of all the rest. Thus, if the stomach of an animal is so organized as only to digest fresh animal food, its jaws must also be so contrived as to devour such prey, its claws to seize and tear it, its teeth to cut and divide it, the whole structure of its locomotive organs to pursue and obtain it, its organs of sense to perceive it from afar, and nature must have even placed in its brain the necessary instinct to enable it to conceal itself and to bring its victim within its toils. Such will be the general conditions of a carnivorous animal. They must inevitably be brought together in every species intended to be carnivorous, for its race could not subsist without them. But under these general conditions there exist also special ones, relating to the size, the habits, and the haunts of the prey on which the animal is to exist. And from each one of these special conditions there result certain modifications, in detail, of the form required by the general conditions, so that not merely the class, but the order, the genus, and even the species will be found expressed by and deducible from the structure of each part. In order, for example, that the jaws may be enabled to seize the prey, there must be a certain shaped prominence for its articulation, a certain relation between the position of the resistance and that of the power with respect to that of the fulcrum, a certain magnitude of the muscle that works the jaw, requiring corresponding dimensions of the pit in which that muscle is received, and of the convexity of the arch of bone beneath which it passes, while this arch must also possess a certain amount of strength to enable it to bear the strain of another muscle. That the animal may be enabled to carry off its prey, a certain degree of strength is necessary in the muscles which support the head, whence results a peculiar structure in the vertebrae to which these muscles are attached, and in the back of the skull where they are inserted. That the teeth may be adapted to tear flesh, they must be sharp, and they must be more or less so, exactly according as they are likely to have more or less flesh to tear, while their bases must be strong in proportion to the quantity of bone and the magnitude of the bones they have to break. Every one of these circumstances will have its effect on the development of all the parts which assist in moving the jaw. That the claws may be able to seize the prey, there must be a certain amount of flexibility in the toes and of strength in the nails, and this requires a peculiar form of the bones and a corresponding distribution of the muscles and tendons. The forearm must possess a certain facility in turning, whence also result certain forms of the bones of which it is made up, and these bones of the forearm, articulating to the humerus, cannot undergo change without corresponding changes taking place in this latter bone. The bones of the shoulder also require to have a certain degree of strength when the anterior extremities are to be used in seizing prey. In this way, again, other special forms become involved. The proper and free play of all these parts requires certain proportions in all the muscles concerned in the motions of the foreleg, and the impression of the muscles so proportioned will determine still more definitely the structure of the bones. It is easy to perceive that similar conclusions might be drawn as to the structure of the posterior extremities which contribute to the rapidity of the general movement of the body, or of the vertebrae which influence the facility of those movements, and also as to the structure of the bones of the face, in their relation to the degree of development of the external senses. In a word, the structure of a tooth involves that of the socket in the shoulder bone and of the nails, just as, to use a mathematical but very apt illustration, the equation to a curve involves all the properties of the curve, and as the curve may be drawn when we know the root of the equation, so in comparative anatomy, by making each property separately the base of investigations, one may deduce all the other properties. Thus the shoulder bone, the articulation of the jaw, the thigh bone, or any other bone taken separately, gives the structure of the tooth, or conversely from the tooth a knowledge of all these peculiarities may be derived, so that, taking any one bone, he who is familiar with the laws of the animal economy may reproduce the whole animal. Ansted. End quote. Relative ages of the principal catastrophes of the globe. From observations it would seem that the dry land must have appeared in successive portions to cause on the surface all the variations of nature, form, humidity, and dryness, the combination of which should procure for man all the happiness designed for him by the Creator. The study of the successive appearances of land is now one of the most beautiful points of view in which geology can be presented. We are indebted to Monsieur Elie de Beaumont for pointing out the course to follow to establish the chronological order of the principal catastrophes which happened in Europe, and around which all facts of the same nature may be grouped. As soon as we perceive some part of inclined sedimentary beds, we may decide that they have been displaced from their ordinary position by upheaval. The period of this accident remains at first undetermined. But if, at the base of more or less elevated projections which these beds produce, we find other sediments deposited in horizontal strata, resting against the preceding, it becomes evident that the upheaval of the first took place after the formation of the second, which are still found as they were when they were deposited from water. We now have a term of comparison, and, if we succeed in recognizing the relative age of the horizontal deposits, we also have an epoch of the catastrophe, relatively determined, which produced the uptilting of the other. These differences of stratification are everywhere seen on the sides of mountains, and we then see that the several sedimentary deposits, A, B, C, are not all in the same position. In certain places the stratum A, for example, is uptilted, and the stratum B is horizontal. In another, A and B are both uptilted, and C is horizontal. In a third, A and B and C are uptilted together, and another stratum, D, rests upon them. We must infer from these observations that a first upheaval took place after the formation of A, and before that of B. A second took place between the strata B and C, a third between C and D, etc., and so on, chronologically as far as they have been observed. Systems of upheaval. If the inclined position of sedimentary strata reveals to us the existence of upheavals, the strike or direction of these beds, which is nothing but the line produced by their swelling upwards, or the crest or ridge resulting from their rupture, shows us the course followed by the phenomenon. Hence it follows we may take one fact for the other as the basis of observation, and that the different directions, strikes, of mountain chains are also indications of the different kinds of upheaval. In fact, it has been long and perfectly established, on one hand, that the inclination of strata is intimately connected with the direction of chains, excepting the perturbations which result from crossings. On the other hand, we now know that the phenomenon of uptilting of a determinate number of beds extends as far as the chain itself. It has also been ascertained, at least for Europe, that parallel chains correspond, in general, in the epoch of upheaval. That is, in these chains, strata of the same age are found everywhere uptilted, and that the succeeding ones are horizontal. It follows from this circumstance that an upheaval does not take place purely on a mathematical line, but on a band of formations more or less wide, on which it is manifested by several parallel ridges. The same line does not continue always from one end to the other, but we find here and there high and low parts, and those which are concealed by the subsequent deposits. Therefore, it is the common line of all the elevated ridges which must be taken for the general direction or strike. The word strike is formed from the German streichen, to stretch, to extend. The assemblage of directions on the same line and parallel directions form what is called a system of upheaval, which is synonymous with the expressions system of fractures, system of uptilted beds, and even system of mountains, although in a more restricted sense than in geography. To designate the different systems, The names of places in which each system is particularly developed have been borrowed. We say system of the Pyrenees, system of the Western Alps, etc. The great catastrophes which have successively occurred on the surface of the globe appear to have always taken place suddenly. At greater or less distances from places where the stratification is unconformable, we often find the same deposits in conformable stratification, and even joined to each other by a gradual passage. Hence it follows that deposition has not been suspended, but the movement of the soil has been local over a more or less considerable space of the terrestrial surface, and the interval during which it took place must have been extremely short. This is clearly seen, for example, at the period of the system of the Rhine, in which the Vosgian sandstone is found upheaved, without the Bunter sandstein having participated in the action. And nevertheless, at a short distance, the two arenaceous deposits, where their stratification is conformable, are so joined to each other that it cannot be determined where one begins or the other ends. The same is the case with the Cretaceous formations. If their different deposits are dislocated in a certain direction, they are conformable for great extents, and they then pass from one to the other in such a manner that they were for a long time confounded as a single formation. Submerged and uncovered formations. Sedimentary beds found resting horizontally on the sides of mountains show that the sea beat against escarpments by deposits upheaved in an anterior epoch. Hence the expression of the sea of this or that formation as the Cretaceous Sea, the Jurassic Sea, etc., which indicate the waters beneath which each of these sedimentary deposits was formed. When a deposit is wanting in a certain extent of formation, we should infer the formation was then above the sea of the epoch, and formed there a more or less elevated island or continent. Thus, at the time when the Parisian limestone was formed, a great part of France, and indeed of Europe, must have been dry, as we scarcely see traces of these deposits anywhere except in the neighborhood of Paris or Bordeaux. But it also happens that the deposits which we must regard as having been dry at a certain time were afterwards covered by marine sediment, more modern than the preceding, and hence we must conclude that, although uncovered prior to the anterior formation, they must have afterwards sunk to receive new deposits. Such sinkings make certain catastrophes particularly remarkable. The several systems of upheaval have been classed according to their direction, and the epochs in which they occurred. The following table exhibits the supposed epochs of the European upheavals. First, upheaval or system of Hunsrück, between the Cambrian and Silurian formations. Second, upheaval or system of Ballons, between the Silurian and the Coal formations. Third, upheaval or system of the north of England, between the Coal and Pennine formations. Fourth, upheaval or system of Hainault, between the Pennine and Vosgian formations. Fifth, upheaval or system of the Rhine, between the Vosgian and Trias formations. Sixth, upheaval or system of the Thuringerwald, between the Trias and Jurassic formations. Seventh, upheaval or system of Côte d'Or, between the Jurassic and Greensand formations. Eighth, upheaval or system of Mont Viso, between the two Cretaceous formations. Ninth, upheaval or system of Corsica, between the Parisian limestone and the Molasse formations. 11th, upheaval or system of the Western Alps, between the Molasse and Subapennine formations. 12th, upheaval or system of the Principal Alps, between the Subapennine and Diluvium. 13th, upheaval or system of Tenaire, between the Diluvium and perhaps some modern alluvions. Since in Europe the different great chains of the same direction, which are found on the same line or on parallel lines, belong to the same epoch of upheaval, there is room to suppose, as nothing indicates limits to the phenomena which gave rise to them, that the same effects were continued far beyond the countries whose geological structure is known. Hence it follows that wherever we find parallelism in the chains, we should be led to believe also that the formations were contemporaneous. It is at least interesting to examine, under this point of view, the principal chains we are acquainted with. The direction of the Pyrenees extends from the Alleghanies in North America to the peninsula of India, through the Carpathian Mountains, a part of the Caucasus, the mountains of Persia, from Erivan to the Persian Gulf, and through the Ghats, which determine the position of the coast of Malabar. To the south of this line or direction, several parallel ridges are also represented. Those which go from Cape Ortegal in Asturias to Cape Crow in Catalonia, the small chain of Granada which ends in Cape de Gat, the mountains which bound the desert of Sahara on the north, cutting the direction of Atlas, finally the Apennines, the Julian Alps, the mountains of Croatia, of Romelia, and those of Moria. The system of Balance, so near to that of the Pyrenees, appears to be represented also in the Alleghanies. It is to be observed on the coast of Brittany, and will no doubt be found in several of the groups just mentioned when careful study enables us to distinguish it from the neighboring system. The direction of the Western Alps is remarked from the Empire of Morocco to Nova Zembla, passing through the eastern coast of Spain, the south of France, and a great part of the peninsula of Scandinavia. It is recognized in the Cordillera of Brazil, from Cape St. Roque to Montevideo. Parallel to the direction, the same system is seen in the Kingdom of Tunis, in Sicily, the point of Italy, and in Asia Minor. All the shore of the ancient continent, from North Cape and Lapland to Cape Blanco in Africa, is parallel to the direction of the system. The principal Alps form part of a system of direction of great extent. From the chains of Spain and those of Atlas in the northern part of Africa, we find parallel chains which extend to the China Sea. On this line of direction we find, starting from Sicily and Italy, the chains of Olympus in Greece, the Balkan, Taurus, the central chain of Caucasus, crowned by Elbrus, between the Black and Caspian Seas, the long series of mountains which extend through Persia and Kabul, comprehending Paropamisus, Hindukush, etc. Finally, Himalaya, the highest mountain in the world. State of Europe at different epochs of formation. From what has been stated, we are led to infer that the surface of the globe, so often disturbed, must have presented great variations in the relative extent of land and sea, and successively passed through many different shapes to reach its present state. But even in Europe, the only part of the world in relation to which positive information has been obtained, it is very difficult to say what may have been its condition in the most ancient epochs. The reason of this is that, having for a long time confounded, under the name of transition formation, deposits of very different epochs, we are not now able to distinguish with sufficient clearness throughout the limits of different formations comprised in it. Nor do we know, and this is a great obstacle to tracing the continents of the ancient world, what parts were successively sunk at each catastrophe, and the extent of which we can only know from induction. It was not until after the appearance of the Jurassic formation, the limits of which are clearly marked, that we are able to distinguish with precision the shape and extent of lands in the midst of the seas in which these deposits were formed. By the term epoch of this or that formation, we understand the period of time during which the formation was produced beneath the sea, around the upheaved deposits of the preceding epoch. For example, the Jurassic epoch indicates the time during which the deposits of the Jura were formed in the seas, where the upheaved deposits of the Trias and all that preceded were traced. The term sea of such an epoch, as Jurassic Sea, Cretaceous Sea, etc., is often used in the same sense. Silurian and Devonian epoch. At the time when the Silurian and Devonian systems were formed in the midst of seas, it is evident there were different portions of land in Europe uncovered, which resulted as much from the upheaval of the Hunsrück as from previous catastrophes. We have seen those of considerable extent which entirely escaped these deposits, and which, in consequence, must have been raised above the waters in which they were formed. In France there was at least one island of the Cambrian formation near the Gulf of St. Malo, on a part of Brittany and of Normandy. The great granitic plateau, which comprises Limousin, Auvergne, etc., where the upheaval of the Hunsrück was manifest by the direction of certain uptilted beds of gneiss, and by the anfractuosities in which the coal formation was subsequently deposited, must have been at that time above water, and perhaps adjoined at the south to the ancient group which preceded the Pyrenees. The mountains of Maures also existed, and perhaps a part of the formations comprised between Toulon and Innsbruck, in a southwest and northeast direction. Some parts of the centre of Vosges and of the Black Forest, Eifel, the Hunsrück, where the first upheaval is clearly indicated, and Ardennes were necessarily above water, as well as the county of Nassau, the Harz, all the centre of Germany, including Saxony, Bohemia, and Moravia. The same is true of Scandinavia, and a part of the British Islands. From this moment lands were covered with vegetation, in arborescent ferns, equisetaceae, etc., sufficiently abundant to form the masses of anthracite formed in the Devonian formation. The seas were then inhabited by trilobites, orthoceratites, orthis, productus, different kinds of terebratula, and several species of polyparia, of the same genus as those found in madreporic reefs, which, as well as the tree forms, indicate a climate analogous to that of present tropics. All these circumstances show that heat was not in that epoch distributed over the surface of the globe as it now is. Without doubt the increase of temperature from the surface to the interior was more rapid. All springs were warm, and according to M. Elie de Beaumont, the fogs, which were the result, hindering radiation in the absence of the sun, everywhere tempered the rigor of winter, and thereby augmented the mean temperature of the seasons. Coal epoch. The upheaval of the Ballons, in bringing today the Silurian and Devonian deposits, no doubt, increased the extent of lands, and more or less changed their configuration. Vegetation must have been prodigiously developed at that time, and over vast surfaces, which is proved by the enormous mass of coal formed, and the manner in which the deposits are piled up. On one hand, the carboniferous limestone and the different marine beds found in the midst of the sandstone of the coal formation itself seem to indicate at first a deep sea, and perhaps afterwards an immense maritime marsh, which extended from Ardennes and the Harz to the ancient mountains of the British Islands. On the other hand, the numerous coal basins known to exist in the surface of France and central Germany clearly show there were extensive lands on which marshes were found, here and there, in which were formed, just as peat bogs are in our times, all the coal deposits we have discovered. The ancient and uncovered formations which constitute Brittany and the central plateau of France clearly indicate high land on which are found the lakes of Bayeux, Quimper, Laval, and Vouvant, placed between in the anfractuosities caused by upheaval of the Ballons. Then those of Burgundy, Limousin, Auvergne, Forez, etc., situated on a direction parallel to the elevation of the Hunsrück. This land, the limits of which cannot be fixed, extended at least to a peninsula towards Strasbourg. To the east of this land, and perhaps united to it, there is another, which was evidently uncovered because there is nothing of the Pennine formation deposited on it. The latter probably extended over the space now occupied by Innsbruck, Milan, Briançon, Genes, Nice, Toulon, and to the islands of Corsica. Towards Toulon are the marshes in which was formed the coal now found in that part of France. Lands also evidently existed over the space occupied by Bohemia and Saxony, with several coal lakes on their surface. The coal deposits of Moravia and Galicia seem to show their extension towards these countries. There was one island at least between Cologne and Frankfort, presenting in its southern part the great coal basin of the country of Treves, and uniting at the north with the ancient formation of the Harz. Dry land also existed in the peninsula of Scandinavia, where nothing has been deposited since the Silurian formations, but it seems to have been sterile and without swamps, for it affords no trace of coal. We are entirely ignorant of what existed where the great cities now stand, but the absence of Carboniferous limestone out of Belgium and England may lead us to think that a great portion of Western Europe was then uncovered and perhaps presented coal lakes which subsequent catastrophes have sunk beneath the seas. A part of the land just mentioned has always remained uncovered to the present time, or has been even upheaved more and more by various subsequent catastrophes, as Brittany and the central plateau of France. At certain points, in fact, coal deposits have been pushed upward to a great height, as the plateau of Santa Fe de Bogota, and in the Cordillera of Huarochirí, where some are found from 2,700 to 4,600 yards above the sea. In other places, on the contrary, it is evident the formations have sunk, to be covered by more modern deposits through which the coal is sought in the depth, as at Anzin under the chalk, and Vasquez under the red sandstone, and Cevennes under the Jurassic limestone, etc., and in general on the borders of new formations exposed by subsequent catastrophes. Without doubt there is some deeply buried and forever lost to us, either under different sediments or under water, as at Whitehaven in England, where the mine extends more than 1/4 of a league from the shore and 100 yards beneath the bottom of the sea. The vegetation of this epoch, favored no doubt by the insular form of the land, as now is in all islands, consisted of Lycopodiaceae, Equisetaceae, ferns, etc., of arborescent species, the analogous of which are no longer found except within the tropics, with conifers resembling the Araucaria. The mass of coal was formed of their debris, with cellular cryptogamia, which then grew under water, as now in peat marshes, and under a still more favorable temperature for their development. The seas of this epoch had lost their trilobites, but contained in great abundance spirifers, productus, orthoceras of particular species, different cephalopods analogous to the nautilus and argonaut, and various other shells. The encrinites were so extensively multiplied that their debris constitute, almost of themselves, certain varieties of Flemish and Belgian marble. Sauroid fishes of great size and especially vigorous organization then existed, and the family of sharks, still feeble, presented cestracions and hybodons. The fresh waters which fed the coal marshes contained, as it appears, few conchiferous mollusks. The debris which are rarely found resemble anodonta and unio. Fishes were numerous in some localities. They belonged in the genera Palaeoniscus and Amblypterus, living, without doubt, in the rivulets which meandered at the bottom of abrupt fractures of the ancient formation. Pennine epoch. The disturbance caused by the upheaval of the north of England appears to have exerted more influence on the surface of the then uncovered lands than on their extent and form. Only the bottom of the sea, where the coal beds of England and Belgium were formed, was elevated in part to escape, like all France, to the Pennine formation. On the other hand, a small corner of the southwest of Vosges must have sunk under water to receive the red sandstones which there cover the coal formation. Further, in Mansfield, the presence of the Pennine formation, which is there developed on a great scale with its shell limestones, demonstrate the submersion of the country beneath sea water. It was also beneath the sea, in the country of York, that Magnesian limestone was deposited, which there represents the whole formation of this epoch. Very little is known of the terrestrial flora of that time, for we find little, save the algae in the bituminous schists of Mansfield, and some silicified trunks of conifers in the sandstone. Deposits of coal suddenly ceased to form, and it seems from that time there were neither ponds nor rivulets on the lands. Nevertheless, there were still diverse fishes of the genus Palaeoniscus, which lived perhaps as well in salt as in fresh water. The land was for the first time inhabited by saurian reptiles, resembling the iguana and monitor. the remains of which are found in cuprous schists. The seas beneath which all these deposits were formed contain the same genera, often the same species of mollusks and radiata as those in which the Carboniferous deposits were formed. Vosgean Epoch. The system of Hainault, in dislocating the coal formation and ridging the surface of the land, had little influence on its form. In the Vosges, some of the points where the red sandstone were deposited were elevated, around Saint-Dié, Schelestad, Mont-Bellard, and escaped the succeeding formations, while all the rest of the chain, which had escaped the deposits of the red sandstone and consequently found elevated at this epoch, must have been sunk now to receive the Vosgean sandstone. The same has taken place in the Black Forest. Such was the state of things in this modification, that animals could not have lived on this part of the earth, and that plants, if any then existed on the surrounding soil, could not have been carried under the waters except in very small numbers. The Trias Epoch. After the system of the Rhine, subsequent to which the Vosgean sandstone was upheaved, Vosges and the Black Forest underwent a little change in shape, but other lands in Europe have undergone scarcely any modification. We observe only a secondary elevation of the central plateau of France, by the peripheroid granites of Lozère, by the hills which edge the coal formation from Fins to Mauriac. Subsidences occurred, on the other hand, in Bourbonnais and Rouergue, as well as in lands between Toulon and Nice. Vegetation then underwent great modifications. The ferns and Equisetaceae of great height had considerably diminished, and conifers, on the contrary, became more numerous. Plants analogous to Zamia and perhaps to Cycas then formed an important part of the flora of Europe, beginning a prelude to the immense development they took in the succeeding epoch. In this epoch new saurians appeared, and traces of birds, which had not appeared in preceding epochs, are recognized. It was at this period also that those creatures existed, whatever they were, whose tracks are found imprinted on Bunter sandstein, freshly lifted above water. Mr. Owen, who considers them enormous batrachians, supposes them to have been of the form represented. The Jurassic epoch, at the same time of the elevation of Thuringewald, the Triassic formation, which had just been deposited beneath the sea, was upheaved at different points. Some patches of Bunter sandstein were added around the central plateau of France, between Moulins and La Châtre, between Brives and Tulle, in the environs of Rodez, of Saint-Affrique, and of Lodive. The island of Var was increased from these sandstones and Conchylian limestone. The Vosges and Black Forest were also considerably augmented, the one to the west in Lorraine, the other to the east, extending into Germany and uniting various islands which had been separate till then. The same was the case with different islets, which already marked the place of the British Islands, and were then united to a continuous land by Triassic deposits upheaved between them and with them. But at the same time that the new lands were raised above water, there were great subsidences in those which previously existed. The land which extended from Cherbourg to Perpignan was then divided towards Poitiers, forming a strait now occupied by the Jurassic deposits. It was variously divided on its borders and almost cut again towards Rodez. That which extended from Nice towards Innsbruck was entirely sunk to receive the new deposit which covers it. If perchance there existed at the period of the coal some portions of land where Paris, London, etc. now are, everything leads to the belief that they then disappeared, for the Jurassic formation appears to be prolonged everywhere beneath the soil which serves them as a base. All the data on the state of Western Europe at the period of which we speak are furnished by the presence and disposition of the Jurassic deposits. Developed on a vast scale and upheaved later from the bosom of the waters, they clearly show what was then the configuration of the lands around which they were formed under the sea. The ocean of the Jurassic epoch also had its peculiar characteristics. It was inhabited by saurians, eminently swimmers, the Ichthyosaurus and Plesiosaurus, whose paws, in form of paddles, remind us of those of the chelonians of the present day. These voracious animals, all aquatic, took the place of the sauroid fishes of the Carboniferous group, which had now disappeared. At the same period lived those flying saurians, called pterodactyls, which peopled the air and completed the series of singular creatures of an ancient creation now entirely annihilated, the exterior forms of which Dr. Buckland has attempted to paint from the skeleton. Those seas had lost the Productus, and spirifers had almost disappeared. The numerous terebraculi which lived in this epoch belonged to species entirely different from those seen in the preceding seas, but there were found a great number of mollusks with chambered shells, and generally called ammonites, the race of which, as yet little developed, had begun to appear in the seas of the Trias. There existed belemnites, the remains of which, until then unknown, are numerous from the lias to the chalk. And the Gryphea arcuata multiplied there for a moment, to disappear afterwards, when the lias was formed, and to give place to other species of the same genus. As at present coral reefs were formed in those seas, remains of which are found, showing a mean temperature analogous to that of our intertropic seas. On the land, freshwater lakes, without doubt, supported paludini, and the freshwater streams carried helices, remains of which are now found in the Portland group. There must have existed also on land several species of insects, which served to feed the pterodactyls, the remains of which seem to show they were Coleoptera and Neuroptera, resembling the Bubrestes and the Liblui. Small marsupial mammals, analogous to possums, were met there, a skeleton of which was found in the beds of Stonesfield, but these creatures seem to have been in small numbers, if we judge from the remains that have been as yet found, and no one of the great animals which characterize the Parisian epoch has been found with them. The flora was not the same as that which furnished so many remains to the coal formation. The Lycopodiaceae and the gigantic ferns had disappeared, and it seems that many new species had been created after the Pennine and Triassic epochs. Then the Cycadea and conifers considerably exceeded all other families, and probably some palms were already in existence, the fruits of which are found in the lias. Also, the carbonaceous combustible formed in this epoch is very different from that of the great coal formation. They were at the same time much less abundant, which indicates a great difference in the extent of lands. Lesson 10, Part 3 of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Amy Greenmore. Elements of Geology by William Ruschenberger. Lesson 10, Part 3. Cretaceous Epoch. After the system of upheaval of Côte d'Or, which elevated a part of the Jurassic deposits above the sea, the form and disposition of continents were considerably changed. The inferior limits of the chalk mark the shape of lands which then existed, and determine the extent of the seas of the epoch. The three islands of the preceding epoch were now united, but without any change of shape. Brussels, which was inland, was now found on the coast. Aarhus, Dunkirk, Maastricht, Wessel, Breslau, and Vienna were sunk under water. A lake was formed between Dresden, Brunn, and Prague. A strait was found in the place of Perpignan and Carcassonne, and what existed previously to the Pyrenees was in part submerged. By compensation, the Vosges, washed by the sea in preceding ages, was then found in the middle of the continent which joined the central island of France. The space of sea which separated them was filled up. Langres, Nevers, Lyons, Toulouse, and Oxford were on terra firma, and an isthmus was formed about Poictiers to join the great island that existed to the west. A shore extended from the environs of Cracovia to about Perpignan by Ratisbon, the position of which was not changed, and to Zurich and Lyons. An immense gulf was formed between Brussels and Oxford, extending to Poictiers. Between Salzburg and Avignon a new island was formed, which marked the future site of the Alps. Briançon, Turin, Trent, and Innsbruck might have been already placed there, but Switzerland was then a channel which separated this island from terra firma. The island of Toulon was at the time limited, and some small islands marked the environs of Marseille. Little change, however, had taken place in living creatures. At the same time, diverse species of ferns and cicadae vegetated on the soil. Conifers, especially, became more and more abundant, and gave origin to masses of lignite found at the base of the chalky formations. But there were few terrestrial mammals, for no remains of them are found in the chalk, although they were met with in Jurassic deposits. There existed, however, diverse cetaceae, such as lamantins and dolphins, some of which had already appeared in the Jurassic seas. Reptiles were among the animals capable of living on the earth, still the most elevated creatures of the creation. Aquatic and terrestrial species were very numerous. Among them were the iguanodon, the megalosaurus, and diverse crocodiles. Fluviatile tortoises, fishes and mollusks of fresh water, lived on the borders of lakes or in their waters. The seas fed baculites and turrilites, of whose interior existence there is no trace, and which, towards the end of the epoch, disappeared at the same time with all mollusks having peculiar chambered shells. Here and there true sharks existed, and have been continued to the present time, although their dimensions are considerably diminished. Parisian epoch. The upheaval of Mount Viso, and later that which gave birth to the Pyrenees, to the Apennines, and all the parallel chains we have cited, prodigiously changed the geographical constitution previously established. The last especially produced one of the greatest convulsions Europe has experienced. Everything was shaken by it, and the greatest part of what was then under water was elevated above it, to form an immense continent. This proves the little extension of the Parisian sediments then formed, and which are found concentrated, one part in Belgium, Artois, Picardy, Isle of France, Normandy, and the opposite coasts of England, and the other in the environs of Bordeaux. Very few traces are found elsewhere. Hence it follows that the seas of this formation did not penetrate far into this continent, although they covered the two capitals of the world. Of the vast ocean of preceding ages, there only remained a part of the gulf already limited, about Cambridge, Oxford, Exeter, Cherbourg, Angers, and Poictiers, which was then narrowed in many places, and widened elsewhere at the expense of the ancient peninsula of Brussels. It probably communicated with some remains of the North Sea. In the middle were two islands of chalk, the Wealds of England and the country of Bray in France. Another portion of the gulf also remained between Bordeaux and Dax. The fauna of the land, at the Parisian epoch, was very different from what it had been in preceding epochs. The gigantic saurians had disappeared, but there remained great freshwater crocodiles, marine and lacustrine chelonians, and the earth was inhabited by mammals. The last were then pachyderms, analogous to tapirs, as the Anoplotherium and Paleotherium, which must have been nearly of the form represented. They lived at the same time with some carnivora of the genus dog, etc. Belemnites and all similarly chambered shells had disappeared from the seas. The nautilus only remained, and it lived with the Cerathium giganticum, and a multitude of species of mollusk, more or less resembling those of existing seas. At this age of our planet, the flora of Europe was still modified. The cicadae had disappeared, and the conifers, presenting still new species, to which were joined the dicotyledons, were found with palms to the centre of Europe. The last, which are not now found closer than Africa, at the nearest point evidently indicates a mean temperature higher than what we enjoy now, which must have been about 72 degrees, the present mean temperature of Lower Egypt. This circumstance may be attributed to the fact that the increase of internal heat was greater than at present, and that the fogs, by diminishing radiation, rendered the winters less rigorous. Watercourses necessarily must have existed on the continent, and may account for deposits of lignite and the remains of freshwater mollusks being found in place in the midst of marine deposits. We are especially led to suppose that one of these watercourses, emptying about Leon and carrying lacustrine deposits from Soissonnais, and another, somewhere between Exeter and Oxford, formed the deposits of the Isle of Wight, at the southwest of the Wealds. Around Paris, some parts of the sea must have been separated from the rest, at a certain time, and converted into a freshwater lake in which the gypsum was formed. Epoch of the Molasse. It was after the system of Corsica that the molasse was formed, and in such a manner that it is generally deposited where the Parisian limestone is entirely wanting. It follows that lands which were then elevated above the waters must have necessarily sunk, often to great depths, to receive this new formation, which is sometimes extremely thick. Consequently, great modifications of the continent of the preceding epoch again took place. Partial subsidences must have occurred in many parts of Touraine, of Guyenne, of Gascony, Languedoc, Provence, Dauphiny, and also in all Switzerland, etc. Lakes were formed, often extensive, sometimes isolated, and sometimes communicating with the sea, and it is this which indicates the contemporaneous deposits, some of which are fluviatile and others marine. In opposition, more or less considerable upheavals took place at the same time in many parts of the northern Gulf, in Belgium, in Picardy, in the Isle of France, and all the coast of England. The marine limestone, laid bare, escaped in all this extent. The succeeding deposits and the sites of London and Paris were brought to light, although surrounded by water in which the molasse was deposited. It was the same in the Gulf of Bordeaux, where all the northern part of the Parisian formation was upheaved, and escaped the deposit of the molasse, which is found in all the rest of the present basin, which was from that time submerged. This epoch was accompanied by a new change in the creatures which lived on the surface of the soil, and from that moment, besides some new species of Pelotherium, Mastodons and the Dinotherium giganticum appeared in Europe, the last nearly of the form represented, as well as the rhinoceros, hippopotamus, monkeys, and many rodents, as castors, squirrels, etc. The flora was principally composed of conifers, with dicotyledons, which, however, had not attained, in all probability, the development they acquired in the succeeding epoch. There still existed palms, the remains of which are found in deposits of lignite, and particularly in those of Liblar, near Cologne, as well as in the plaster works of Aix. Sub-Apennine epoch. The upheaval of the Western Alps caused a new disturbance. Not only the soil comprised between Constance and Marseille, rendered mountainous by preceding events, suddenly assumed a considerable height, and a great part of the relief it now presents, but still the movement extended over all Europe. The greatest part of the Anglo-French Gulf was filled by an elevation which brought to-day all that is referred to the molasse. It was the same in Guyenne, in Languedoc, in Provence, in Piedmont and Switzerland, and the form of the seas was once again changed. But in time great lakes were formed in the interior of the lands, one from Dijon to near the Isère, another in the southern part of Alsace, and a third in Provence, from Sisteron to the borders of the Durance. At the same time all the carnivora appeared of the genera Ursus, Hyena, Felis, Canis, etc., which inhabited caverns. Their remains are not found in the Parisian formation, Their species disappeared not only from the European continent, but from the face of the globe in the next epoch. There also appeared several new rodents, horses, ruminants, and probably the gigantic edontate animal with slow and heavy gait, the megatherium, whose head and whole aspect were similar to the sloth's, although its size was that of the largest rhinoceros, and its body must have been covered by a bony cuirass like the armadillo. Epoch of Diluvium. At this time Europe took its present form, and its relief was definitely fixed. The upheaval of the principal Alps, in forming all the chains which extend to Austria, in elevating likewise some portions of the Western Alps, also raised up the soil in a great part of Europe, and especially caused the division of the waters between the ocean and the Mediterranean. The effects produced show that enormous currents of water were established in all directions, which furrowed all the deposits then uncovered, but the volume of waters furnished by lakes, previously formed in the interior of lands, whose barriers were no doubt broken in the new catastrophe of upheaval, was in relation to the vastness of the result produced. It must have been prodigiously increased by some circumstances, attributable, perhaps, to the sudden melting of the snows and glaciers then accumulated on the Western Alps. The currents which were formed, in furrowing the surface of lands, carried their debris in all directions. Hence the alluvions of the valley of the Rhone, of Grau, of the plains of Lombardy, those of Bavaria, the valley of the Rhine, etc. Hence the last configuration of the valleys, the denudations, and the dislocations seen in so many different places. It is from the upheaval of this part of the Alps that the separation of France and England appears to date, as well as that of Ireland, by ruptures effected between Brest and Cape Lazard, between Carnarvon and Dublin. It was then that the Mediterranean took its present limits, in consequence of the subsidence of formations which extended to the south of Marseilles, at the epoch of the Parisian Sea. The Gulf of Bothnia was perhaps produced in this epoch, since the shell deposits found on some points of the coast are all referred to the sub-Apennine formations. But change of configuration in the soil was not the only consequence of the appearance of the principal Alps. This catastrophe, extending over a great part of the world, from the height of Spain to the centre of Asia, was marked by the sudden cooling of European countries to their present temperature. From that time palms ceased to grow in Europe, and dicotyledonous plants were prodigiously increased. The rhinoceros, elephants, and panthers, which had just appeared in that part of the world, became entirely extinct there, and if the cavern bear is represented in our present bear, its size is considerably diminished. The fauna of that part of the world was again completely changed, and replaced by that we now see. Besides, it was at this moment, probably, that man appeared on the earth. In fact, on one hand, there are no human remains in what has been too lightly named diluvium, for the skeletons of Guadeloupe are of the modern epoch, and cannot be reckoned, and on the other, the animals which then began are precisely those with which man has always lived, since historic time. Modern epoch. From the epoch of the principal Alps, no general geological disturbance has taken place in Europe, and some volcanic eruptions and upheavals, produced by earthquakes, are the only effects that have been manifest. Such also appears to have been the action of the 13th upheaval, which was revealed in the Morea, in Naples, Sicily, and in some parts of Provence, and which, perhaps, also determined the eruption of the modern volcanoes of Auvergne and Vivarais. Though ancient fissures, the beautiful preservation of which attests their posterity to the great denudations which followed the events of the principal Alps. But if scarcely anything occurred in Europe after this great event, perhaps it was not the same in other parts of the world. We may suspect that a great part of the immense mountain range which extends through America and traverses Asia from Kamchatka to the Burman Empire is the result of a more recent catastrophe, This direction, at least, offers the most extended, the most decided, and, so to speak, the least effaced feature of the exterior configuration of the earth. It is there we see the greatest number of active volcanoes, and consequently the most extensive and best preserved communication between the interior and exterior of the globe, and perhaps also the greatest mass of volcanic products known. Deluge. The successive appearance of the great mountain chains has produced great disturbances in different parts of the globe. But it is evident that these catastrophes, at least those of great energy, and those which extended over large spaces, as the upheavals of the Alps, Pyrenees, etc., must have manifested their action over all the rest of the earth in secondary phenomena of more or less importance. If a simple earthquake is enough to produce a violent agitation of the sea, a sudden eruption of waters on continents, these terrible revolutions could not have failed to cause more or less impetuous movements in the ocean, and temporary derangement of level of more or less extent. Hence, without doubt, the extraordinary inundations which, at each catastrophe, have ravaged the surface of existing lands, and produced, as in our day, various denudations, or superficial alluvions, of more or less extent. Now, since, without counting all that escaped the investigations of science, we clearly see, in Europe, a series of successive movements of the soil, which have modified the whole continent, and many even a whole hemisphere, there is nothing absurd in admitting that what took place at so many different times, from the most ancient to the most modern epochs of formation, may have happened once, somewhere after the appearance of man on the earth. Consequently, there is nothing contrary to reason in the belief of a great eruption of water over the lands, a general inundation, a deluge, in fact, which we find described not only in the Bible, but deeply impressed in the traditions of all people, and at an almost uniform date. Thus, in recognizing in the recital of Moses the extraordinary circumstances which bear witness to the supernatural intervention of the divine will, we see on one hand the material possibility of the fact transmitted to us, and on the other hand we find even the secret of the means brought into play, that is, the upheavals, the subsidences, the consequent oscillations of the water, which from that time became efficient causes of the great chastisement then inflicted on the human race. If, because the known results it had produced are feeble, we cannot too carefully seek the cause of this great phenomenon in the last of the upheavals to this time classed, which dislocated the deposits in which traces of human industry have already been found. Perhaps it may be discovered in that which caused the rise of the Andes in America, and the volcanic chain of Central Asia, which, with a colossal development, also present striking characters of relative novelty. As to the future of our planet, everything leads to a belief that the state of tranquility we now enjoy is but temporary, like all the intervals of crises during which the different sedimentary deposits were formed. In fact, in the series of perturbations which, through all time, have formed part of the mechanism of nature, we perceive no law authorizing us to conceive a termination to the succession of these phenomena. To accidents of little importance succeed indistinctly, either crises of the same order or frightful catastrophes. Long periods of tranquillity suddenly succeed terrible convulsions. To the small upheaval of Mount Viso, for example, succeeded the great catastrophe of the Pyrenees. To this the small accidents of the system of Corsica, which were followed by the great event of the Alps. The long period of the Jurassic formation was disturbed by the upheaval of Côte d'Or, as the deposit of the Vosgian sandstone was almost immediately arrested by the system of the Rhine. All was irregular in those revolutions of which we have acquired a knowledge. No fact presents itself suggesting the idea of a gradual diminution in the intensity of subterranean actions, and leading us to think the earth has lost the property of being successively broken and ridged in all directions. Nothing, therefore, can assure us that the period of calm in which we have lived for upwards of 5,000 years, the period of the deluge, will not be disturbed in its turn unexpectedly by the appearance of some new system of mountains, the effect of a new dislocation of the soil, the foundations of which earthquakes show not to be unshakable. Hence it follows that the idea of an end, or a renewal of things, here below, as widely spread as the great inundation which has passed, is also in the order of the laws which govern the universe. Geogeny. The history of the various systems which have been imagined to explain the origin of the universe, and of the earth in particular, might perhaps afford some attraction to the curious, but besides occupying a great deal of time in pure romance, it is, perhaps, better to forget the many mental vagaries we should be forced to expose. A single geogeny is worthy of our attention. It is that which is related in the Book of Moses, and which, after a lapse of more than 3,000 years, still presents, on one hand, the clearest application to the best established theories, and on the other, the most succinct account of the great geological facts. What is more rational, in fact, and more in conformity with even our most precise knowledge, when we think of bringing order into the general confusion of things, than to create the vehicle by means of which the phenomena of light, of heat, etc., may be manifest, and infuse life everywhere, than to collect the scattered elements into groups separate from each other, than to establish here and there centres of attraction around which all may gravitate according to an immutable law. Nevertheless, this is what we find, with fewer details, no doubt, than we could give by means of our acquired knowledge, in brief and common language intelligible to all, in the first verses of Genesis, which thus state 3 successive and distinct facts. We there find indeed an outline, deus fecit, lucum, the fluid of light, of heat, etc., firmamentum, space and all the masses scattered through it, solum et stellas, the centres of attraction, etc. As to the organic creation, it is divided into 4 successive and also rational epochs. The first established vegetative life, or life of nutrition, which is manifested not only in plants, but also in the inferior animals, in which we find scarcely any other phenomena than those of nutrition, growth, etc. Afterwards came the life of relation or sensibility, instinct, intelligence, and will, successively added, in different proportions, to the phenomena of simple existence. This new life first takes a certain development in fishes, including reptiles, no doubt, then birds, which together constitute the second epoch of creation. It acquired a new extension in mammals, which appeared at a third epoch, and finally reached its highest degree in man, with whom terminated the work of the Omnipotent, receiving a soul in the image of God, to distinguish him from all other creatures. This is, without doubt, a wonderful example of successive organic combinations, but it is also precisely the order in which all the remains buried in different ages successively present themselves. Those we meet in deposits we regard as the most ancient are the calcareous remains of certain polyparia, mussels, sometimes even the shell of some acephalous mollusks, the trilobite crustaceans, and the remains of plants, the accumulation of which formed the anthracite of the Devonian formations. The abundance, the extent, the thickness of these combustible beds announce the great luxuriance of vegetation, which leads us to believe that plants existed for a long time, and that perhaps their first debris have disappeared in the profound metamorphisms which modified the deposits in which they might have been. Fishes are not met with prior to the Devonian formations, and it is only in the coal deposits they present a strength of organization, which is lost in the succeeding deposits, and which is not known even now on the globe. Reptiles have left their remains in the new red sandstone, or penine formations which followed, and the birds, the creation of which Genesis also places in the same epoch, have left the imprints of their feet on the sandstones. Mammals did not appear until long afterwards. The traces of those found in the great oolite belong to the least perfect orders. It is only in the tertiary strata that their debris of every species are found in abundance. Human remains are not found in any of the beds which have been upheaved from the bosom of the waters, and now forming parts of our continents. It therefore follows that this privileged being of the general creation did not appear on the globe until after the animals whose fossil debris have been found. He dates from an epoch comparatively very recent, which is placed after the upheaval of the principal Alps. His formation would consequently go back about 6,800 years, according to admitted chronology. It is in the deposits formed under the waters since this catastrophe that the bones of man should be found, and they will not appear from that time in the series of geological beds until new revolutions shall have transformed the sediments still found under water into dry land. It is clear from this outline that the brief statement of sacred history is entirely in conformity with geological generalities. Observation alone enables us to add a great number of details, useless, no doubt, to most men, but interesting at least to the small number of those who dedicate themselves to study, if indeed they are not destined perhaps to enlighten their belief. The assemblage of data we now possess leads us to perceive that each of the particular creations briefly indicated in Genesis, with the exception of that of man, did not take place in a single moment; that, on the contrary, it was successively in a considerable space of time, and in proportion as the terrestrial globe itself was fashioned. Indeed, if the vascular cryptogamia appeared nearly from the commencement of things, the gymnospermous phanerogamia did not appear until about the epoch of the coal formation, and did not exist in abundance until long afterwards. It is the same with the monocotyledons, the remains of which are at first few and indistinct, and not clearly seen until after the chalk. The dicotyledons did not appear until still later, in the midst of the tertiary formations. In all this interval of time, the species successively changed, and those which were created have in turn also entirely disappeared, one after the other, to give place to the new. Fishes, reptiles, and mollusks respectively present us with the same phenomena, and still more clearly show the successive extinctions of the different races, and the appearance of many others. The sauroid fishes, which lived at the time that coal was formed in Belgium and England, disappeared forever in the new order of things established in the Pennine Formation. True sharks did not exist then, but appeared long after in the Cretaceous Sea. Gigantic saurians, with paws in form of paddles, and flying saurians existed in abundance in the Jurassic epoch, but disappeared in the following period, and were replaced in it by enormous terrestrial saurians, of which there are no previous traces, and, after long having inhabited the earth by themselves, the latter were also successively lost, leaving only crocodiles after them, still very different from those of the present day. The same is true of the trilobites, productus, and spirifers, which, after having multiplied for some time, disappeared one after the other. The ammonites and belemnites succeeded them, and are found in abundance in the Jurassic Sea. Then they became completely extinct, after having successively changed species at the moment in which the chalk formation ceased to take place. All the mollusks that followed after more and more resemble those now existing, of which there was then no trace. Mammals present themselves under similar circumstances. The different orders and different species appeared only in succession. The first were only the feeble marsupials. Long afterwards came the pachyderms, analogous to the tapir, the first species of which were soon annihilated. Other species of the same genus succeeded them, and these were found associated with new animals, the mastodon and dinotherium, but they soon afterwards became extinct forever. Still later came the elephants. They only appeared with the carnivora, the rodentia, etc., the species of which were still only the prelude to those which appeared at the same time with man. All these successive changes in the series of creatures coincide with the great disturbances of the surface of the globe. It was at the instant of catastrophes produced by movements of the soil that families, genera, species of organic bodies which had until then disappeared. In times of the succeeding calm, on the contrary, the new organization was developed in harmony with the new atmospheric circumstances and new dispositions of the isothermal lines, etc. These details, which observation enables us to add to the recital of Genesis, are in general harmony with the facts there found briefly enunciated, and of which they are but the development. The only difficulty presenting itself is that of the amplification of the word day, which happily, even in the eyes of legitimate judges, from St. Augustine down, does not seem to possess the value which people have naturally attributed to it. This expression seems in fact to have been adopted only as an indication of relative epochs, as the means of making understood and retaining the order and succession of things which were at once revealed. It is clear, indeed, that minute details categorically established by figures, which would satisfy the curiosity of a small number of men, would not be either received or comprehended by the vulgar, who, nevertheless, are entitled to this important instruction. We ourselves often resort to ways still more crooked to make ourselves better understood by all. It is in this way, for example, we speak of the rising and setting of the sun, to describe the arrival of this luminary to the meridian, to the solstice, etc., although we knew very well that we must attribute these phenomena to the inverse movements of the earth. According to geological observations, this common expression, days, ought to signify epochs, which embrace long periods of time, each being relative to a certain system of creation in which there were different formations of creatures, as well as successive extinctions of those previously existing. Each period began at a particular date, clearly determined and marked by a catastrophe which overturned the order of things anteriorly established on the earth. It was extended for a longer or shorter time, sometimes through succeeding epochs, and often up to the appearance of man himself. According to the conjectures of the scientific, an immense time elapsed between the formation of the first sediment and the last, without counting the period required for the consolidation and first cooling of masses of planetary matter. It was in long series of ages, which are but as instants in eternity, that the earth was fashioned, as we now behold it, by every kind of movement in the soil, by sedimentary deposits of different kinds, and finally prepared as the sojourning place of man, for whom God has disposed.
Glossary A through C of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. The Elements of Geology by William Ruschenberger. Glossary A through C. Abnormal, from the Latin ab, from, norma, rule, not conformable to rule. Abnormus, out of rule, misshapen. Acephalus, acephalus, from the Greek a, without, cephala, head, without a head, headless. Actinolite, from the Greek actin, a ray, lithos, a stone, a variety of hornblende, which usually occurs in fascicular crystals. There are three varieties of this mineral: crystallized, asbestos, and glassy. Aculeatus, Latin aculeate, having a sharp point. Acuminata, Latin acuminate, pointed, peaked. Acuta, Latin acute, sharp, pointed. Acuticosta, Latin acutus, pointed, and costa, rib, having pointed ribs or sides. Acutuloba, Latin acutus, pointed, loba, a lobe, having sharp or pointed lobes. Adult, from the Latin adolesco, I grow, full grown. Agate, from the Greek agathos, good, precious, an aggregate of certain silicious minerals, chiefly chalcedony, variously colored. Moss agate or mocha stone is a chalcedony containing within moss-like delineations of a yellowish brown or green color. Agglomerate, from the Latin agglomero, I wind up, to gather together. Agglomeration, a mass made up of parts gathered together. Agglutinated, from the Latin ad, to, gluten, glue, united together, adhering. Aliformis, Latin ala, wing, forma, shape, wing shaped. Albite, from the Latin albus, white, a mineral. Albitic, of the nature of albite. Algae, Latin, plural of alga, seaweed, systematic name of a family of plants. Alluvial, of the nature of alluvium. Alluvion, alluvium, from the Latin alluo, I wash upon. Gravel, sand, mud, and other transported matter washed down by rivers and floods upon land not permanently submerged beneath water. A deposit formed from transported matter. Alpine, belonging or relating to the Alps. Alumina, from the Latin alumen, alum, pure argil, the basis of alum, one of the earths. Aluminous, from the nature of alumina. Alveolatus, Latin alveolate, having the surface covered with numerous depressions, comparable to the alveoli or sockets of the teeth. Amblypterus, from the Greek amblus, obtuse, and pteron, wing, a fossil fish. Ambulacra, Latin, plural of ambulacrum, the narrow longitudinal portions of the sea urchin, the Echinus, which are perforated with a number of small orifices, giving passage to tentacular suckers, and alternate with the broad tuberculate spine-bearing portions. Ambulacrum, Latin, an alley. Ammonia, Latin, relating to Ammon, a name of Jupiter, specific name of a fossil shell. Ammonis, Latin, genitive case of Ammon, a name of Jupiter. Ammonite, from the Latin ammon. Amorphous, from the Greek a, without, morphe, form, shapeless. Amphibole, from the Greek amphibolus, equivocal. Amplexus, from the Latin amplecto, I embrace, generic name of a fossil. Ampullaria, from the Latin ampulla, a round swelled out bottle, name of a genus of snails. Amygdaloid, from the Greek amugdalon, an almond, and eidos, almond shaped, applied to certain rocks in which other minerals are occasionally embedded like almonds in a cake, a particular form of volcanic rock. Analogy, from the Greek ana, between, logos, reason, resemblance or relation things bear to each other, although not exactly alike in all respects. Analogous, having analogy or resembling. Analog, a substance or article having analogy to others may be called the analogue of those things with which its properties or points of resemblance are comparable. Anenchites, a genus of fossil sea urchins. Andalusite, a mineral first observed in Andalusia in Spain. It is very hard and infusible, and consists chiefly of alumina and silica. Anfractuosity, From the Latin infractus, the bending or winding of a way, an irregular hollow or groove. Anhydrous. From the Greek, without, udor, water, without water, applied to salts and certain acids when deprived of water. Annular. From the Latin annulus, ring, shaped like a ring. Annularia. From the Latin annulus, ring. Generic name of a fossil plant. Anodonta. From the Greek, without, odous, genitive odulus, tooth. Systematic name of a kind of mussel. Anodonte, plural of anodonta. Anoplotherium. From the Greek, without, oplon, arm, or anoplos, unarmed, and therion, beast. Anticlinal axis, anticlinal line. From the Greek, anti, against, klinein, to incline. An imaginary line towards which strata, dipping in opposite directions, rise. Antiquatus. Latin, antiquated, out of date, abolished. Anthracite. From the Greek, anthrax, charcoal, mineral charcoal, a kind of stone coal difficult to inflame. Anthracitiferous. From the Latin, anthracite, and the Latin fero, I bear, containing or affording anthracite. Apiocrinites. From the Greek, apion, a pear, krinon, lily. The pear encrinite, a subgenus of fossil encrinites in which the stem is rounded and dilated at its upper part into a pyriform shape. Aquatic. From the Latin aqua, water, relating or belonging to water. Aquilina. Latin, of or like an eagle, rapacious. Araucaria. From Araco, a district of Chile. Fir trees with very rigid branches, having leaves like scales, either small and sharp pointed, or stiff, spreading, and lanceolate. The Norfolk Island pine is one of this genus. Arborescent. From the Latin arbor, a tree, branching like a tree. Arculata. Latin, arched, bent like a bow. Arenaceous. From the Latin arena, sand, sandy, of the nature of sand. Argil. From the Latin argilla, clay, which is formed from the Greek argos, white, because when pure it is white. Old name of alumina. Argillaceous, of the nature of clay. Argillaceous schist, clay slate or argillite. Argillite, a slaty rock of fine texture, with a faintly glistening or earthy surface of fracture, and mostly of a dark colour. Roofing slate and novaculite or hone slate are varieties of argillite. Argillo-arenaceous, partaking of the nature of both clay and sand. Arietina. Latin, belonging or relating to a ram. Arkose, a name given to different metamorphic sandstones. Articulation. From the Latin articulus, a joint between bones. Asaphus. From the Greek asaphis, obscure, a name devised to express the obscure nature of a genus of trilobites, fossil crustaceans. Asbestos or asbestos. From the Greek asbestos, unconsumable, a fibrous soft mineral composed of easily separable filaments of a silky luster. It consists essentially of silica, magnesia, and lime. Astarte, name of a genus of fossil bivalve shells. Astrea. From the Greek aster, a star, a genus of Polyparia. Astræae, plural of Astrea. Athleta, specific name of a mollusk. Augite. From the Greek auge, luster, a mineral the same as pyroxene. Augitic porphyry, crystals of Labrador feldspar and of augite, in green or dark grey base. Avalanche, mass of hardened snow detached from lofty mountains, which overturns everything in its way. often causing great destruction. Applied also to slides of earth and clay. Avicula. From the Latin avis, a bird. Name of a genus of bivalve mollusks. Axis of elevation. Line of elevation. Bacillar. From the Latin bacca, a berry. Berry-like. Baculites. From the Latin baculum, a stick. A genus of tetrabranchiate cephalopods, the chambered shells of which are quite straight, but differ from those of the orthoceratites in having sinuous or undulated partitions with lobated margins. In this structure they are allied to the ammonites. Bagshot sand, a siliceous bed which overlies the London clay formation, corresponding in age with the Paris basin. Balani, plural of balanus. Balanus, Latin, a barnacle. Ballons, French, ballon, a ball. Rounded mountains are so called. A system of upheaval. Barranco, Spanish, a ravine. Basalt, a rock essentially composed of feldspar and augite, of a compact texture and dark green, grey, or black color. It occurs in columnar masses. When light colored, with the feldspar predominating, it is sometimes called greystone. Basalt closely resembles greenstone. Basaltic, of the nature of basalt. Basset, outcrop or emergence of strata at the surface. Basterote, specific name of a fossil. Batrachian, from the Greek batrachos, frog, a kind of reptile resembling a frog in its mode of organization. Belemnites, from the Greek belemnon, a dart, a genus of fossil dibranchiate cephalopods, the shells of which are chambered and perforated by a siphon, but internal. They are long, straight, and conical, and commonly called thunderstones. Bicordatus, Latin, bicordate, double heart shape. Bifurcated, from the Latin bis, two, furca, fork, divided into two branches. Bioculata, from the Latin bis, two, oculus, and eye, two-eyed. Bitumen, from the Greek pittos, the pitch tree, because it resembles pitch, a variety of inflammable mineral substances, which, like pitch, is included under this term. Bitumenized, converted into bitumen. Bituminous, of the nature of bitumen. Bituminous shale, a slaty rock containing bitumen. Bivalve, from the Latin bis, two, valve, doors. Shells composed of two pieces united by a hinge are termed bivalves. Blende, sulphuret of zinc, a common shining zinc ore. Blumenbachii, the name of Blumenbach latinized. Beauce, French, a hillock, a rounded projection or elevation. Botryoidal, French, from the Greek botrus, a bunch of grapes, and eidos, resemblance. Clustered like a bunch of grapes, covered with smooth rounded masses. Brachiopod, from the Greek brachion, arm, pous, foot, a mollusk with a two-lobed mantle and bivalve shell. Brachyphylum, from the Greek brachus, short, phullon, leaf, a genus of fossil plants. Bradford clay, an English bed of the great oolite, usually consisting of a pale greyish clay, containing a small portion of calcareous matter, and enclosing thin slabs of tough brownish limestone. It abounds in fossil apiocrinites. Brash, a provincial word used in England to describe the alluvial mass or quantity of broken and angular fragments of subjacent rock, found usually between the vegetable mould and the regular rocks. It is also called rubble. Breccia, Italian, a rock composed of an agglutination of angular fragments. When the fragments are rolled pebbles, it constitutes a conglomerate rock called pudding stone. Brevifolia, Latin, from brevis, short, folium, leaf, short-leaved. Brongniarti. Specific name of a fossil in honour of M. Brongniart, the eminent French naturalist. Buccinium. Latin. A trumpet or horn. Name of a genus of mollusks. Bucci. The name of Von Buch, Latinized. Bucklandi. Specific name of certain fossils given in honour of the eminent geologist Dr. Buckland. Buprestes. Latin. Noxious insects, certain beetles. Calamites. From the Greek kalamos, a reed. Common fossil plants in the coal strata. Calamites usually consist of jointed fragments, which are supposed to be portions either of the trunk or the branches of a plant, which appears from some of the larger specimens to have attained the dimensions of a tree. Both stem and branches are deeply ribbed along their whole length, and the ribs or furrows are crossed by horizontal rings at irregular intervals. Kalksinter. German sintern, to drop, a German term for limestone deposited from springs and waters containing it. Travertin. Calcar grosse. French. Marine limestone. Calcar siliceaux. French. Fresh water or silicious limestone. Calcareous. From the Latin calx, lime, containing lime. Calcareous grits, sandy beds intermixed with calcareous matter found in the oolite. Calceola. From the Latin calceolus, a little shoe, a fossil bivalve shell. Calciferous. From the Latin calx, lime, fero, I bear, containing lime. Calcined. From the Latin calx, lime, converted into calx or a friable substance by the action of fire. Calcination. The reduction of bodies to a calx or friable condition by the action of fire. Calvus. Latin, bald. Specific name of a productus. Calimony. From the Greek kekalumene, concealed. A name of a genus of trilobites. Coniformis. Latin, from cana, a reed, formis, form, reed shaped. Canis. Latin, dog. Carbon. From the Latin carbo, a coal. The pure inflammable principle of charcoal. In its state of absolute purity, it constitutes the diamond. Carbonate. A compound of carbonic acid with a salifiable base. Carbonate of lime, for example, is a compound of carbonic acid with lime, constituting chalk, limestone, marble, etc. Carbonaceous. Belonging or relating to carbon. Carbonic acid. An acid compounded of carbon and oxygen. Carbonous. Of the nature of carbon. Carboniferous. From the Latin carba, a coal, fero, I bear, containing carbon. Carbonized. Converted into carbon. Carbonization. The action of forming or converting a substance into carbon. Carburet. A combination of carbon with a metal or other substance. Steel and black lead are carburets of iron. Carburetted. Converted into a carburet, containing carbon. Cardium. Latin, a cockle, a genus of bivalve shell. Carinata. Latin, from carina, a keel. Carinate. Having a keel like elevation. Carnivora. Latin, carnivorous, carnivorous animals. Carnivorous. From the Latin caro, genitive carnis, flesh, voro, I eat, flesh eating. Caryophilia. From the Latin caryophyllus, the garden pink, a genus of madrepora. Cascade. From the French, a cataract, a waterfall. Catena. A chain. Specific name of an ammonite. Catenated. From the Latin catena, a chain, linked together. Catapora. From the Latin catena, a chain, pora, pore. Generic name of a polyp. Catullus or Catillus, Latin, a little dish. A genus of fossil shells. Caudatus, Latin, caudate, having a tail. Cavernous, from the Latin cavus, a hollow. Containing hollows, excavated. Cemented, joined together by cement. Cementation, when a solid body is surrounded by the powder of other substances, and the whole heated to redness, the process is termed cementation. Iron is converted into steel by cementation with charcoal. Centigrade, thermometer, from the Latin centum, 100, gradus, a degree. Division into 100 parts. The scale of the centigrade thermometer is made by dividing the space between the points of freezing and boiling water into 100 parts or degrees. Cephalospis, Cephalospis, from the Greek cephala, head, aspis, shield, a genus of fossil fishes. Cephalopod, Cephalopod, from the Greek cephala, head, pous, in the genitive case, poudos, foot. A mollusk which has the head situated between the body and feet. Cerathea, plural of ceratheum. Ceratheum, a genus of turriculated univalve mollusks, both recent and fossil. Ceroid, from the Greek keros, wax, eidos, resemblance, wax-like. Cestration, French, from the Greek kestreos, name of a fish, a genus of the family of sharks. Cetacea, Latin, from the Greek ketos, a whale, name of an order of mammals. Cetaceae, plural of cetacea. Cetaceous, belonging or relating to cetaceae. Chalcedony, from the Greek chalcedon, Chalcedon, in Asia, where the finest specimens were originally found. A semi-transparent siliceous mineral, apparently found by the infiltration of siliceous matters in a state of solution. The chalcedonic varieties of quartz include chalcedony, chrysoprase, cornelian, sard, agate, onyx, cat's eye, flint, and hornstone. Chalk, from the German kalk, earthy carbonate of lime. Chalk has been discovered, it is said, for the first time in the United States in Alabama, 1845. Chalk marl, marl belonging to the Cretaceous formation. Kama, from the Greek kau, I gape, a cockle. Chara, origin of this word is unknown, a genus of aquatic plants. Chelonians, from the Greek chelone, a sea tortoise, animals of the tortoise tribe. Chert, a siliceous mineral resembling flint. It is usually found in limestone. Chlorite, from the Greek chloros, green, a soft green scaly mineral, slightly unctuous. Chloritic chalk, chalk containing chlorite. Chloritic schist, schist containing chlorite. Chrome, from the Greek chroma, color, the oxide of a metal called chromium. Oxide of chrome is green and furnishes a valuable color for porcelain. Chronology, from the Greek chronos, time, logos, discourse, the science which treats of the division of time and the order and succession of events. Cicatrices, plural of cicatrix. Cicatrix, Latin, a scar. Sidaris, Latin, a cap or turban, name of a genus of Echinidae. Cinders, matters remaining after combustion. Clavellata, Latin, from clavulus, a little nail, marked by little projections or points, knotted. Cleavage, the mechanical division, the laminae of rocks and minerals, to show the constant direction in which they may be separated. Clinkstone, see phonolite. Clymenia, from the Greek klumenon, the marigold, a genus of fossil cephalopods of the Devonian system. with a chambered shell analogous to that of the ammonite. Coal measures, the formation in which coal is found. Coccinelloides, from the Latin and Greek coccinella, cochineal, eidos, resemblance, resembling the cochineal insect. Cocosteus, name of a genus of fossil fishes. Coleoptera, from the Greek koleos, sheath, pteron, wing, name of an order of insects. Columba, Latin, a dove, specific name of a fossil shell. Columnar, Latin, columnar, in the form of a column. Coming today, when a vein or stratum crops out or appears on the surface, it is said to come to the day. Comminuted, fractured into small pieces. Communis, Latin, common. Comparative anatomy, the comparative study of the various parts of the bodies of different animals. Comptonia, a genus of plants named in honour of Henry Compton, Lord Bishop of London. Concentric, having a common centre. Concentricus, Latin, concentric. Conchiferous, from the Latin concha, shell, fero, I bear, shell bearing. Conchylian, consisting of or containing shells. Condensable gas, any gas that is susceptible of being condensed into a fluid or solid. Conduit, a water pipe, a canal. Conformable stratification, when the strata are parallel to each other. Congeners, from the Latin con, with, genus, race, species belonging to the same genus. Conglomerate, from the Latin conglomera, I heap together, a rock composed of pebbles cemented together by another mineral substance, either calcareous, silicious, or argillaceous. Conica, Latin, conical. Conifer, from the Latin conus, a cone, fero, I bear, a tree or plant which bears cones, such as pines, fir trees, etc. Conoidae, Latin, conoidal, cone-shaped. Conoidal, from the Latin conus, a cone, and the Greek eidos, resemblance, cone-shaped, like a cone. Contemporaneous, from the Latin con, with, tempus, time, existing at the same time. Contorted, from the Latin con, together, torqueo, I twist, twisted together, bent. Coprolites, from the Greek kopros, dung, lithos, stone, fossil excrement. Coral, from the Greek koreo, I ornament, als, the sea, the hard calcareous support formed by certain polypi. Coral rag, certain beds of the middle oolite, consisting chiefly of corals. Coralline, belonging or relating to coral. Coralloids, Latin, from coral, and the Greek eidos, resemblance, coral-like. Specific name of a Devonian fossil. Coringunum, Latin, cor, heart, ingunum, snake-like. Specific name of a fossil. Cornbush, an oolite bed consisting of clays and sandstones. Its name is probably derived from the excellence of the cornland, which results from the decomposition of the limestones and their mixture with the sandstones and clay. Cornutus, Latin, horned. Coronata, Latin, crowned. Costatus, Latin, ribbed. Procitella, a genus of bivalve shells. Crassus, Latin, thick. Crater, from the Latin crater, a great cup or bowl, the mouth of a volcano. Crater form, in the form of a crater. Crenatum, Latin, crenate, having rounded teeth. Cretaceous, from the Latin creta, chalk, of the nature of chalk, relating to chalk. Crinoidae, from the Greek krenon, lily, eidos, resemblance. A family of radiate animals. Crioceratites. From the Greek kyros, a ram, and kyros, a horn. A fossil cephalopod. Crises, plural of crisis. Crisis, Greek. The point of time when any affair comes to its height. Crocodilian. Any animal of the tribe of crocodiles. Crop out. When a rock in place emerges on the surface of the earth, it is said to crop out. Crustacean. Any animal of the class of Crustacea, a crab. Cryptogamia. From the Greek, kryptos, concealed, gamos, marriage. Name of a class of plants. Crystal. From the Greek, kristallos, ice. This term was originally applied to those beautiful transparent varieties of silica or quartz known under the name of rock crystal. When substances pass from the fluid to the solid state, they frequently assume those regular forms which are generally termed crystals. A crystal is any inorganic solid of homogeneous structure, bounded by natural planes and right lines symmetrically arranged. Crystalline. Relating to or resembling crystals. Crystallization. The process of forming crystals. Ctenoidians. From the Greek, kteis, in the genitive, kteos, a comb, an order of fishes. Cucullatus. Latin, hooded. Cuprous. Belonging to copper. Cuvieri. The name of Cuvier latinized. Cyathocrinites. From the Greek, koathos, a cup, krinon, lily. A genus of crinoideae. Cyathophila, plural of cyatophyllum. Cyatophyllum. From the Greek, koathos, a cup, phyllum, a flower. A genus of Polyparia. Cycadae. From cycas, one of the genera. An order of plants. Cycas. A name employed by the ancients to designate a little palm. Cyclades. Plural of cyclas. Cyclas. From the Greek, kuklos, a circle. A genus of gasteropods. Cycloidians. From the Greek, kuklos, a circle. An order of fishes. Cymbium. From the Greek, kumba, a boat. Specific name of a shell. Cypraea. From the Greek, kupris, Venus. A genus of gastropod mollusks. Cyprus. From the Greek, kupris, Venus. A genus of crustaceans. Sirena. A genus of bivalve mollusks. Glossary D through L of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. Elements of Geology by William Ruschenberger. Glossary D through L. Data. From the Latin datum, given, a gift. Admitted facts. Debacle. French. Sudden escape of water from a lake following a bursting of its barrier. Debris. French. Wreck, ruins, remains. Defranchi. The name of de France, Latinized. Degrade. From the Latin de, primitive, gradus, step, degree. To lessen, to cut down. Degradation. The act of lessening, reduction. Dejections. Matters evacuated from the bowels. Deltoidae. Latin. From the Greek letter delta, eidos, resemblance. Resembling a delta. Dentatum. Latin. Dentate. Having sharp teeth. Denude. From the Latin denudo, I strip, to lay bare. Denudation. a removal of a part of the land so as to lay bare the inferior strata. Deposition. From the Latin depono, I let fall. The falling to the bottom of matter suspended or dissolved in water or other liquid. Depressus. Latin, pressed, sunk. Deus. Latin, God. Diadema. Latin, a diadem, a crown, a genus of Echinidae. Diagram. From the Greek dia, through, grapho, I write, a figure drawn for illustration. Diallage. From the Greek diallage, difference, a mineral of foliated structure easily divisible in one direction, its natural joints and fractures exhibiting a very different luster and appearance. Dicheras. From the Greek dis, two, keras, horn, generic name of a fossil bivalve. Dicotyledons. From the Greek dis, two, kotylidon, seed lobe, a division of plants according to the natural order. Dicotyledonous. Relating to dicotyledons. Digona. From the Greek dis, two, gona, angle, having two angles. Dilatata. Latin, dilated, swelled out. Diluvial. Relating to diluvium. Diluvion, diluvium. From the Latin diluo, I wash away, a superficial deposit. Dinotherium. From the Greek dinos, circular, therion, a beast. Diorite. A variety of trap rock consisting of albite and hornblende. Dip. Direction of the inclination of strata. To take a dip is to measure the degree that a stratum inclines or dips from a horizontal line. Direction of strata, the strike or line of bearing. Disaggregated. From the Latin de, privative, aggregero, I gather together, separated, divided, broken up. Disaggregation. The breaking up of a mass into small parts. Discordant stratification, unconformable stratification. Disengaged, separated from, freed. Disintegrate. From the Latin de, privative, integer, entire, whole. To separate or break up an aggregate into parts. Disintegration. The act of separating or dividing a whole into parts. Dislocate. From the Latin de, privative, locus, place, to put out of place. Dislocation. Displacement of a part. Disposition. From the Latin dispono, I arrange, arrangement, method, order. Disruption. From the Latin disrumpo, I break off, the act of breaking asunder. Distortion. From the Latin de, from, tortum, twisted, the act of distorting or twisting out of place. Dolichos, iris. Latin, from the Greek, dolichos, long, diere, neck, long-necked. Dolomite. Named after Dolomir, magnesium marble, granular magnesium carbide of lime. It contains about 45% of carbonate of magnesia. It is commonly more friable or crumbling than pure limestone, and less durable as a building material. Dolomization. The conversion of common into magnesium limestone or dolomite. Dome. From the Latin domus, house. A rounded projection. Domite, a trachytic rock. Dunes, French, downs. Duvalli, name of Duval Latinized. Ubulation, the act of boiling. Echinidae, Echinidae. From the Greek echinos, a hedgehog. Eidos, resemblance. Systematic name of the order of sea urchins. Echinoderms, From the Greek ikonos, a hedgehog, derma, skin. A class of invertebrate animals. Indentate, an order of mammals without teeth. Indentate, from the Latin a, without, dens, tooth, without teeth. Effervescence, from the Latin effervesco, I grow hot, the commotion produced in fluids by the sudden escape of gas in the form of bubbles. Effusion, from the Latin effundo, I pour out, the pouring out of a liquid. Elegans, Latin elegant. Emboss, from the French bosse, a protuberance, to cover with lumps or bunches. Encrinites, from the Greek krinon, a lily, a genus of echinoderms. Entomostracans, from the Greek entomos, incised, ostrakon, a shell, a division of the class of Crustacea. Epidemic, from the Greek epi, upon, demos, the people, a prevailing disease. Epoch, the time from which dates are numbered. Equalis, Latin equal. Equation, from the Latin aequare, to equal, equivalent, a mean proportion between extremes. Equilibrium, from the Latin aequa, equality, libro, I balance, equal balance. Aquesta, plural equestum. Equestaceae, from equestum, one of the genera, a natural order of plants. Equestum, from the Latin equus, horse, seta, hair, a genus of plants. Erode, from the Latin erodo, I gnaw, to wear away, to corrode. Erosion, the act of wearing away. Erosive, corroding, wearing. Eruption, from the Latin a, from, rumpo, I burst, the act of bursting from any confinement. Escarpment, from the Italian escarma. Escarpment, from the Italian scarpa, sharp, formed from the Latin carpere, to cut or divide. The steep face often presented by the abrupt termination of strata where subjacent beds crop out from under them. Escharoides, from the Greek eschara, a fireplace, a gridiron, eidos, resemblance, specific name of a coral. Euphotide, a rock composed essentially of feldspar and diallage. Evolutus, Latin unfolded. Excoriation, from the Latin ex, from, corium, skin, an abrasion, mark of a part having been rubbed from the surface. Exogyra, from the Greek exo, without, gyros, circle, not circular, a genus of unimuscular bivalves, allied to the oyster. Explosion, a sudden bursting with noise and violence. Extremities, the limbs, legs, arms, etc. Exudation, from the Latin ex, from, sudo, I sweat, transpiration. Exuviae, Latin, the sloths or caskins or shells of animals. Fasciculus, Latin, plural of fasciculus. Fasciculus, Latin, a bundle. Fascigiata, Latin, sharpened at top like a pyramid. Fathom, a measure of 6 feet. Fault, from the German fall, an accident, sinking, fall. Fauna, from the Latin faunus, the name of a rural deity Among the Romans, all animals of all kinds peculiar to a country constitute the fauna of that country. Fecit, Latin, he made. Feldspar or felspar, from the German feldspath, an important mineral composed of silica, alumins, and potash, with traces of lime and often of oxide of iron. It enters into the composition of granite. Feldspathic, of the nature or belonging to feldspar. Felis, Latin, a cat. Phenionis, specific name of a fossil zamia. Ferruginous, from the Latin ferrum, iron, containing iron. Ficoides, from the Latin ficus, a fig tree, and the Greek eidos, resemblance, specific name of a fossil plant. Firmamentum, Latin, the firmament. Fissile, from the Latin findo, I split, easily split. Fissure, a crack, a separation, a split. Flora, from the Latin flora, goddess of flowers. All the plants of all kinds of a country constitute the flora of that country. Fluviatile, bringing or relating to a river. Foliatia, Latin, foliated. Foliated, from the Latin folium, a leaf, in form of leaves, leafy. Foraminifera, from the Latin foramen, hole, fero, I bear, name of a tribe of minute shells. Formation, any group of rocks formed during a particular epoch, or of common origin. Fossil, from the Latin fodio, I dig, any organic body or the traces of any organic body, whether animal or vegetable, which has been buried in the earth by natural causes. Fossiliferous, containing fossils. Fossilized, converted into a fossil. Fulcrum, Latin, a prop, the fixed point on which a lever moves. Fumihole, French, subterraneous emissions of hydrogen gas in consequence of the ebullition of certain sulphurous waters, the hole or orifice through which the gas escapes. Fumes, vapours. Fusion, the act of melting, state of fusion is being melted. Fusiform, Latin, fusiform, spindle shaped. Galena, from the Greek galena, lead ore, sulphuret of lead, that is, a compound of sulphur and lead. Ganoidians, an order of fishes. Garnet, a mineral consisting of silicates of alumina, lime, iron, and manganese. There are several varieties of this mineral. Garnet occurs embedded in mica slate, granite, and gneiss, and occasionally in limestone, chlorite slate, serpentine, and lava. Gas, from the German Geist, spirit, the name given to all permanently elastic fluids or airs different from the atmospheric air. Gaseous, of the nature of gas. Gault, a kind of clay. Gelatinous, jelly-like. Genera, Latin, plural of genus. Generic, relating to genus. Genus, Latin, a kindred, breed, race, or family. Geodes, from the Greek geodes, earthy. Nodules of ironstone hollow in the centre. Rounded pebbles having an internal cavity lined with crystals are also so called. Geogeny, from the Greek ge, the earth, geonomy, I beget. Science embracing the theories of the formation of the entire universe. Geognostic, relating to geognosy. Geognosy, from the Greek ge, the earth, gnosis, knowledge. Knowledge of the mineral substances which constitute the mountains and strata of the earth. Geological, relating to geology. Geologist, one skilled in geology. Geology, from the Greek ge, the earth, logos, discourse. That branch of natural history which treats of the structure of the terrestrial globe. It is divided into descriptive geology, dynamic geology, which treats of the forces by which the surface of the earth has been modified, practical and economic geology, embracing the application of geological science to mining, road making, architecture, and agriculture. Geysers, from an Icelandic word signifying raging or roaring. Celebrated spouting fountains of boiling water in Iceland. Gibbosite, from the Latin gibba, a bunch, a protuberance. Giganteum giganteus, Latin, gigantic. Glauber, Latin, smooth, bald, bared. Glaciers, French, masses or beds of ice formed in high mountains, derived from the snows or lakes frozen by the continued cold of those regions. Globata, Latin, globate, rounded. Gneiss, German, a rock resembling granite in its constitution and general characters, but it contains more mica and the colors are banded, but owing to the arrangement of the minerals, especially the mica, in parallel planes. In consequence of this structure, the rock splits into coarse slabs along the planes of the mica, besides having the cross fracture or cleavage of granite. It is often described as a stratified or stratiform granite. A rock intermediate between granite and gneiss is called gneissoid granite. Gneiss is used for building and flagging. Goodhalley, the name of Goodhall Latinized. Gralliae, Latin, wading birds. Granite, a crystalline aggregate of quartz, feldspar, and mica. The ingredients of granite vary in their proportions, and the rock is described as micaceous, feldspathic, or quartzone, according as mica, feldspar, or quartz is the predominating mineral. It is called porphyritic granite when the feldspar is uniformly disseminated in large crystals. They appear like white blotches, often of a rectangular shape, over a worn surface of the rock. Granitic, belonging or relating to granite. Granular, consisting of grains. Graphite, from the Greek grapho, I write. A mineral composed of carbon and iron, constituting carbonate of iron. It is known as plumbago and black lead. It is used in the manufacture of lead pencils. Grauwacke and Greywacke, German, grey rock. A name given to some of the older shales in the geological series, and also to the sandstones that accompany them. Gravel, small rounded stones varying in size from a small pea to a walnut or something larger. Gravitate, from the Latin gravis, heavy, to tend towards the centre of the earth, as all bodies do from their weight. Greensand, a formation of the Cretaceous group. Greenstone, a tough variety of trap rock, consisting chiefly of hornblende. Gris bigare, French, a fine-grained solid sandstone, sometimes white, but more frequently of a red, blue, or greenish color. It is the same as bunter sandstein. Grit, a coarse-grained sandstone. Grunstein, German, greenstone or diorite. Gryphia, from Greek grupos, incurved, a genus of fossil bivalves. Gryphites, generic synonym of the Productus oculatus. Rhyolite limestone, a marl, so called from containing rhyphia. Greifetenkalk, German, a name sometimes given to zechstein. Gymnospermous, from the Greek gumnos, naked, sperma, seed, having naked seeds. Gypseous, of the nature of gypsum. Gypsum, native sulphide of lime. The transparent varieties constitute selenite, and the fine mass of alabaster. Gypsum is converted into plaster of Paris by heat. Hamites, from the Latin hamus, a hook, a genus of extinct cephalopods, inhabiting chambered shells, losing their spiral form after their commencement, and then continued for a considerable extent with a single bend on themselves like a hook. They are found in the greensand of England. Helices, plural of helix. Helix, Latin, a snail. Heterocircle, from the Greek heteros, opposite, kirkos, a tail, having the spine prolonged into the tail. Heterophylla, from the Greek heteros, opposite, phyllum, leaf, specific name of a fossil plant. Hiberti, name of Hibert, Latinized. Hieroglyphics, from the Greek eros, sacred, glypho, I write, sculpture or scripture writing. Hipparites, from the Greek hipparis, horsetail, a certain fish, a genus of extinct mollusks supposed to be bivalve. The principal valve is of a subcylindrical or elongated conical form, traversed by one or more internal longitudinal ridges, enclosed by a small subcircular valve like an operculum. Hippopotami, Latin, plural of hippopotamus. Hippopotamus, from the Greek hippos, horse, potamus, a river, the river horse. Holopticus and Holotychus, from the Greek olos, the whole, tukios, folded, a fossil fish of the ganoid order, the enamelled surface of whose scales was marked by large undulating furrows. It had sharp conical teeth. Homocercal, from the Greek omos, joined, kirkos, a tail, applied to the tail appended to the termination of the spine, as in most of the fishes now existing. Hornblende, a mineral of dark green or black color, abounding in oxide of iron and entering into the composition of several of the trap rocks. There are three varieties: common, hornblende schist, and basaltic hornblende. Hornblende schist, of slaty variety of hornblende. Humus, Latin, moist earth, vegetable earth or mold. Humerus, Latin, shoulder, name of the bone placed between the shoulder and elbow. Hybodones, from the Greek ubos, bent outwards, and odos, tooth, a division of the shark family. Hydrated, from the Greek udor, water, containing water. Hydrochloric acid, an acid composed of hydrogen and chlorine, formerly known as muriatic acid. Hydrostatics, from the Greek udor, water, and stio, I stand, the science which explains the properties of the equilibrium and pressure of liquids. Hypersthene, Labrador hornblende, it contains iron, silica, and magnesia. Hypersthene rock differs from common hornblende only in its foliated crystallization and its pearly or metallic pearly luster. It is a very tough rock with a structure resembling gneiss. Hypnoides, from the Greek upnon, a sort of moss, eidos, resemblance, specific name of a fossil plant. Hypogeny, from the Greek upo, under, geonome, I am formed, a class of rocks which have not assumed their present form and structure at the surface of the earth, but are apparently of igneous origin and thrust up from below. Hypothesis, from the Greek upo, under, Antithemi, I place. A theory or supposition, a rational conjecture. Hypothetical, of the nature of hypothesis. Ichthyosaurus, the fish lizard. Igneous, from the Latin ignis, fire, relating or belonging to fire. Iguanodon, from iguana and the Greek odos, tooth, an extinct genus of gigantic herbivorous reptiles, discovered in the south of England. Imbricatoria, Latin, as if imbricated or tile-like. Imbricata, Latin, imbricate, tile-like, arranged like tiles. Impressa, Latin, impressed, engraved, marked. Inequivalvus, Latin, inequivalve, having unequal valves. Incandescence, from the Latin incandescere, to grow very hot, to be inflamed, the condition of great heat showing a certain light, as if the heated substance itself were burning, melted. Incandescent, greatly heated. Incoherent, from the Latin in, not, con, with, hearo, I adhere, loose, wanting cohesion. Inclination of beds, dip. Incrustation, from the Latin crusta, a crust, a covering like a crust. Inequilateral, from the Latin inequalis, unequal, latus, in the genitive lateris, side, having unequal sides. Infiltration, from the Latin filtrare, to filter, the act of filtering through, producing an accumulation of liquid. Inoceramus, from the Greek an, with, keramos, earthenware, a genus of bivalve fossil shells, which are chiefly characterized by their hinge and the fibrous structure of their constituent substance. The shell, in consequence of the vertical arrangement of the fibres, readily breaks into pieces, and it is often extremely difficult to extricate a specimen with the hinge and beaks tolerably entire. In place, in their original position, where they were formed. Inquinata, Latin, stained, dirty. Inserted, attached. In situ, Latin, in place. Intercalated, from the Latin intercalo, I place between, placed between. Intercalation, the placing one substance between others, as one stratum between two others. Interposed, from the Latin inter, between, pano, I place, placed between. Intertropical, between the tropics. Intrusion, the act of thrusting or forcing in. Isolated, from the Italian isola, an island, separated like an island. Isothermal, from the Greek isos, equal, therma, heat. Isothermal lines are those which pass through those points on the surface of the earth at which the mean annual temperature is the same. Jasper, a siliceous mineral of various colors. Jurassic, belonging to the Jura Mountains. Cooper, German, the upper portion of the new red sandstone formation. Cooper-Schiefer, German, copper slate. Labradorite, Labrador spar. It consists of silicate of alumina, lime, and soda, with traces of oxide of iron. It is a variety of feldspar. Labyrinthica, Latin, labyrinth-like. Labyrinthodon, from the Greek labyrinthos, a labyrinth, odos, tooth, an extinct genus of batrachians characterized by teeth of a peculiarly complicated structure. The remains of this genus peculiarly characterize the Cooper formation in Germany and the corresponding sandstones in England. Lacustrian, from the Latin lacerta, a lizard, any animal of the lizard tribe. Lacustrine, from the Latin lacus, a lake, belonging or relating to lakes. Laevus, Latin, smooth, bare, bald. Lemononis, specific name of a fossil plant. Lamberti, the name of Lambert latinized. Lamina, Latin, plural, laminae, a plate. Landslip or landslide, the removal of a portion of land down an inclined surface, from its attachment being lessened by the action of water beneath or by an earthquake. Lapilli, from the Latin lapillus, a little stone, small volcanic cinders. Lateralis, Latin, lateral. Lava, the substances which flow in a melted state from a volcano. Lavas vary in consistence and texture. Lenta, Latin, slow, heavy, stupid. Lepiodendra, plural of lepiodendron. Lepiodendron, from the Greek lepis, scale, dendron, a tree. A genus of fossil plants having a scaly bark. Leptena, a synonym of the genus Productus. Lemeri, the name of Lemeri latinized. Ligneous, from the Latin lignum, wood, woody, of the nature of wood. Lignite, from the Latin lignum, wood, a kind of coal. Lima, Latin, a file, name of a genus of bivalve. Linearis, Latin, linear, line-like. Line of bearing, strike. Liquefaction, the act of becoming liquid. Lithoites and lituites, from the Latin litus, a crooked staff. Fossil chambered shells, curved or bent at one end. Lithographic, from the Greek lithos, stone, grapho, I write. Lithographic stone, used for the purposes of lithography. Lithophagy, from the Greek lithos, stone, phrago, I eat. Small worms found in slate which give it a red color. Littoralis, Latin, littoral, belonging or relating to the shore. Loam, a mixture of sand and clay. Loess, a German geological term applied to a tertiary alluvial deposit which occurs in patches between Cologne and Basel. The term is applied by the English to that particular yellow loam with calcareous concretions. Longirostrus, Latin, from longus, long, rostrum, beak, long billed. Longiscata, Latin, a little longer. Lycopodiaceae, from the Greek lukos, a wolf, pous, foot, a natural order of plants which includes the lycopodium. Laeli, the name of Lyell latinized. Limnaea or Limnaea, from the Greek limne, a pool, a genus of freshwater snails. Lusum, Latin, light. Lugdunensis, Latin, belonging or relating to Leon. Glossary M through Z of Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michelle. Elements of Geology by William Ruschenberger. Glossary M through Z. Madrepora, Latin, compound of the French madre, spotted, and Latin porus, pore, a genus of corals. Madrepore, a kind of coral. Madreporic, of the nature of madrepore. Magnesia, a white, tasteless, earthy substance. Magnesian, relating to or containing magnesia. Magnesian limestone, limestone which contains magnesia. An extensive series of beds lying above the coal measures. Magnetic, having the properties of the magnet or lodestone. Magnum, Latin, great. Mammal, any animal that suckles its young. Mammaliferous, containing mammals. Mammillary, from the Latin mammilla, a little nipple, studded over with small rounded projections. Mammoth, an extinct species of elephant. Mantellia, a genus of fossil Cycadiae, named in honour of Mr. Mantell. Margaritifera, from the Latin margaritum, a pearl, fero, I bear, pearl bearing. Marine, from the Latin mar, the sea, relating to the sea. Marl, argillaceous carbonate of lime. There are several varieties of marl. Marshy, the name of marsh latinized. Marsupial, from the Latin marsupium, a pouch. Any animal having a peculiar pouch in front or on the abdomen. Mastodon, from the Greek mastos, a nipple, odos, tooth. A genus of extinct quadrupeds allied to the elephant. Matrix, Latin, the stony substance in which metallic ores and crystalline minerals are embedded. Maximum, Latin, greatest. Meandrina, a genus of polyps. Meandrinae, plural of meandrina. Medicaginella, specific name of a chara, a kind of fossil moss. Medullary rays, from the Latin medulla, marrow. The vertical plates of cellular tissue which radiate from the centre of the stem through the wood to the bark in exogenous plants. Megalixus, from the Greek megas, great, ixus, fish. An extinct genus of fishes, including species of great size. Megalodon, from the Greek megas, great, odous, tooth. A genus of peculiar fossil bivalve shells. Megalonyx, from the Greek megas, great, onyx, a claw. A large fossil mammal found in Virginia. Melania, from the Greek melos, black. A genus of fluviatile univalves. Mellophyre and Mellophyra, from the Greek melos, black. A kind of porphyry, the constituents of which are united by a black cement. Mephitic, French, Mephitis, the goddess of foul smells, applied to impure or foul exhalations. Metalliferous, containing metal. Metamorphic, relating to metamorphism. Metamorphism, from the Greek meta, indicating change, morpha, form. Metamorphosis, plural of metamorphosis. Metamorphosis, change of form. Mica, from the Latin mico, I shine. A mineral generally found in thin elastic laminae, soft, smooth, and of various colours and degrees of transparency. It is one of the constituents of granite. Micaceous, of the nature of mica. Mica schist, mica slate. Microscope, from the Greek mikros, little, scopeo, eye view. An optical instrument which enables us to examine objects too small to be seen by the unassisted eye. Microscopic, minute, perceivable only by aid of a microscope. Miliolites, or miliola, from the Latin milium, a millet seed, and Greek lithos, stone. A genus of foraminiferous fossil shells found in the neighbourhood of Paris. Millstone grit, coarse grained quartzose sandstone. Mine, German, any subterraneous work or excavation which has for its object the extraction of any mineral products as metallic ores, coal, etc. Mineral, any inorganic natural object, whether solid, liquid, or gaseous. Mineralogy, that branch of natural science which treats of the properties of minerals. Minima, minimum. Latin, least. Minus, Latin, little. Minuta, Latin, minute, very small. Mollusc, French, a fine-grained sandstone, usually soft and loose, but sometimes sufficiently hard for building purposes. Mollusk, from the Latin mulus, soft. Any animal of the class of mollusca. Monile, Latin, belonging or relating to a necklace. Moniliformis, Latin, from monile, a necklace, forma, form, in form of a necklace. Monocotyledons, from the Greek, monos, single, cotyledon, seed lobe, a class of plants having but one seed lobe in the embryo. Moraines, longitudinal deposits of stony detritus found at the bases and along the edges of all the great glaciers. Mucronatus, Latin, pointed, sharp-pointed. Multilocular, from the Latin multus, many, loculus, a partition, having many chambers or partitions. Mural, from the Latin muros, a wall, belonging or relating to a wall. Murex, Latin, a shellfish, a genus of univalve mollusks. Muricata, Latin, full of sharp prickles or points. Muscle, an organ of motion, the flesh of animals. Mussel, a bivalve mollusk. Mutable, Latin, mutable, changeable. Maya, a genus of bivalve mollusks. Nagelfluh, German, a coarse conglomerate. Nautilus, a genus of cephalopods. Navicula, Latin, a little boat. Neocomian and Neocomin, French. The lower beds of the Cretaceous system in the south of France and elsewhere are described by the French geologists under this name. Neptunian, from Neptune, god of the sea, belonging or relating to water. Neurenia, a genus of fossil univalves, resembling both Cerithium and Turritella. Nervures, veins of leaves, also the tubes for expanding the wings of insects. Neuroptera, from the Greek, neuron, a nerve, petron, wing, an order of insects. Neuropterus, a genus of fossil plants. Nidiformis, Latin, in the form of a bird's nest. Nilsonia, a genus of fossil plants. Nodosus, Latin, knotty. Nodule, from the Latin, nodus, a knot, a rounded irregular lump or mass. Normal, from the Latin norma, a rule, according to the peculiarities of a family or genus, without the least departure. Norwich or Norfolk crag, a tertiary formation which rests on the London clay or chalk, and includes marine shells. Nucleus, Latin, a kernel, the solid core of a body. Nucula, from the Latin nux, a nut, a genus of bivalve shells with numerous teeth like those of a comb. Nummulites, from the Latin nummus, money, and from the Greek lithos, stone, fossil money, an extinct genus of cephalopods of a thin lenticular shape, divided internally into small chambers. Nummulite limestone obtains its name from the presence in it of these shells in great abundance. In Alabama there is a mountain range entirely composed of one species of nummulite. Nutrition, the animal function by which the various organs receive nutritive substances, previously prepared by the several organs of digestion, necessary to repair their losses and maintain their strength. Oblongus, Latin, oblong. Obovata, Latin, obovate. Obovate, from the Latin ob, for opposite, Ovum, egg. Reverse of ovate or egg shaped. Obsidian, named after Obsidius, a glassy lava, volcanic glass. It consists of silica and alumina with a little potash and oxide of iron. Octoplicata, Latin octo, 8, plicata, folded, having 8 folds. Oolite, from the Greek oon, an egg, lithos, stone. A granular variety of carbonate of lime, frequently called rowstone. Oolitic, belonging or relating to oolite. Opalescent, resembling opal, a beautiful mineral characterized by its iridescent reflection of light. Operculum, from the Latin operio, I cover, the lid which protects the gills of fishes, and closes the opening of certain univalve shells. Orbicularis, Latin orbicular. Orbit, from the Latin orbis, a circle. The circular cavities in which the organs of vision are lodged are named the orbits. Ores, from the German Erze, mineral bodies from which metals are extracted. Organ, from the Greek organon, an instrument, part of an organized being, destined to perform some particular function. The ears are organs of hearing, the muscles organs of motion, etc. Organic, relating to organs. Organized, possessing organs. Organization, a mode of structure. Organisms, Latin from the Greek organo, I arrange, or provide with organs, organizing or constructing. Orthis, a genus of fossil bivalve shells. Oscillation, from the Latin oscillum, an image hung on ropes and swung up and down in the air, the act of moving backwards and forwards like a pendulum. Oscillatory, swinging backwards and forwards like a pendulum. Ostracea, family of bivalves which includes the oyster. Ostrea, genus of bivalves, an oyster. Outcrop, the emergence of a rock in place at the surface. Outlier, a hill or range of strata occurring at some distance from the general mass of formation to which it belongs. Ovatus, Latin ovate, egg shaped. Overlying, when one stratum lies over or overlaps another, it is said to be overlying. Oxide, from the Greek oxus, acid, eidos, form, a compound which is not acid, containing oxygen. Oxygen, from the Greek oxus, acid, Ghanaian, to generate, vital air. Pachyderma, Latin from the Greek pachos, thick, derma, skin, thick skinned. Pachydermata, Latin pachyderms. Pachyderms, an order of quadrupeds including the elephant, horse, pig, etc., distinguished by the thickness of their hides. Pachydermatus, relating to pachyderms. Pachynatus, Latin from the Greek pachos, thick, gnathos, jaw, specific name of the labyrinthodon. Paleontologist, one skilled in paleontology. Paleontology, from the Greek paleos, ancient, on, creature, logos, a discourse. That branch of zoological science which treats of fossil, organic. Paleozoic, relating to ancient life. Palmacites, a genus of fossil plants. Polendina, from the Latin palos, a marsh, a genus of freshwater gastropods. Polendinae, plural of Polendina, Polendine, belonging to a marsh. Parallel, extended in the same direction and preserving always the same distance. Parallelism, the state of being parallel. Parallelepiped, a solid contained by 6 planes, 3 of which are parallel to the other 3. Parasite, an adherent, a hanger-on. Parasitic, of the nature of a parasite. Parietes, from the Latin paries, a wall. The sides are parts forming an enclosure. Plecopterus. From the Greek pekos, sheepskin, pteris, a fern. A genus of fossil ferns. Pecten. Latin. A comb. A genus of bivalve mollusks. Pectinata. Latin. Pectinate. Like the teeth of a comb. Pellicle. From the Latin pellis, a skin. A thin skin or crust. Pennine Formation. New red sandstone. Pentamerus or Pentamerus. From the Greek pente, 5, meros, apart. Pentangulatus. Latin. Having 5 angles. Percolate. From the Latin per, through, colo, I strain. To strain or drip through. Peridot. Prismatic chrysolite. Perlite. Pearlstone. A gray variety of obsidian. Permanent gas. Any gas which remains in the aeriform state under ordinary circumstances. Peroxide. The highest degree of oxidizement of which a metal or other substance is susceptible without becoming an acid. Pespelicani. Latin. Pelican foot. Phanerogamia. From the Greek phaneros, evident, gamos, marriage. The division of the vegetable kingdom in which all the plants bear flowers and are multiplied by means of true seeds. Phanerogamous. Belonging or relating to the Phanerogamia. Phenomena. Plural of phenomenon. Phenomenon. Greek. Appearance, visible quality, event. Pholos. From the Greek pholos, a lurking place. A genus of mollusks. Pholades. Plural of pholas. Pholodomia. A genus of mollusks. Phonolite. Clinkstone. A species of compact basalt which is sonorous when struck. Phosphoric, phosphorescent. From the Greek phos, light, emitting light in the dark. Pistiliformis. Latin. In the form of a pistil. Placunea. Latin. From the Greek plakois, broad, flat, even. Plagiostoma. From the Greek plagios, oblique, stoma, mouth. A genus of bivalve mollusks. Planorbis. From the Latin planus, flat, orbis, a circle. A genus of marsh snails. Planos. Latin. Flat. Plaster of Paris. A substance prepared by heating gypsum. Plateau. French. An elevated plain or tableland. Plateau. Plural of plateau. Platina or platinum. From the Spanish plata, silver, on account of its color. A metal of whitish color, exceedingly ductile, malleable, and of difficult fusion. Pleistocene. From the Greek pleistos, the most, kainos, recent. The newest Pliocene formation or newest tertiary. Pleuronectes. From the Greek pleura, side, nectes, swimmer. A genus of fishes. Pleurotoma. From the Greek pleura, side, toma, a notch. A genus of univalve mollusks having a notch in the side of the shell. Pleurotomaria. A tribe of mollusks. Plicatula. From the Latin plica, a fold. A genus of mollusks. Plutonic. After Pluto, the god of fire. Relating to fire. Poikilotic. From the Greek poikilos, variegated. A name applied to the new red sandstone formation in consequence of the varieties of colours it exhibits. Polyp. From the Greek polos, many, pous, foot. A radiated animal which has a cylindrical or oval body or sac with an opening at one extremity around which are long feelers. Polyparia and Polypiaria. Groups of polyps or animalcules which form coral. Polyparium. The skeleton or framework formed by coral animalcules. When this framework is of a stony hardness, it constitutes coral. In fossils, the polyparium alone remains. Porous. Containing pores. Porphyric. Of the nature of porphyry. Porphyroid. Resembling porphyry. Porphyry, from the Greek porphyra, purple, originally applied to a red rock found in Egypt, a compact feldspathic rock containing disseminated crystals of feldspar, the latter when polished forming small angular spots of light color thickly sprinkled over the surface. The rock is of various colors, dark green, red, blue, black, etc. Porrecta, Latin, extended. Pozzuolana and Puzzolani. Volcanic ashes used in the manufacture of mortar which hardens under water, exported from Pozzuoli near Naples. Precipitation, the action by which a body abandons a liquid in which it is dissolved or suspended and becomes deposited at the bottom. Prismaticum, Latin, prismatic. Productus, a genus of extinct mollusks. Pterodactyly, Latin, plural of pterodactylus. Pterophyllum, from the Greek pteron, wing, phyllum, leaf. A genus of fossil plants. Pudding stone, conglomerate. Pumice, vesicular obsidian. Pyrites, a compound of sulphur and iron. Pyroxenic, of the nature of pyrocene. Quadersandstein, German, the lower Cretaceous beds in Germany, any sandstone fit for building purposes. Quaquaversal, turning each way. Quarry, a stone mine, a place where stones are dug. Quartz, German, rock crystal, a constituent of granite and some other rocks. Quartzose, of the nature of quartz. Radiata, Latin, radiate, the name of a class of zoophytes. Radiate, from the Latin radius, a ray, furnished with rays. Radius, Latin, a ray, the semi-diameter of a circle, a ray drawn from the centre to the circumference. Radiation, the emission of rays of light or of heat from a luminous or heated body. Radiolites, a genus of fossil shells, the inferior valve of which is in the shape of a reversed cone, the superior valve convex. Raft, trunks of trees and other vegetable debris matted together by natural causes and sunk in a river or stream. Rapilli, small volcanic cinders. Reaction, the force exerted by two bodies which act mutually on each other. Realgar, red sulphuret of arsenic, a compound of sulphur and arsenic. Refrigeration, the act of cooling. Resinous, containing resin. Retusus, Latin, retus, blunted. Revoluta, Latin, turned again. Rock, any mineral aggregate. Rodentia, from the Latin rodere, to gnaw, an order of mammals. Rodents, gnawers, animals of the order of Rodentia. Rostellaria, from the Latin rostellum, a little beak, a genus of univalve mollusks. Rothomagensis, Latin for Rothomagum, a temple of Roth, a divinity of that part of Gaul now called Normandy. Hence too the name of the city Rouen, belonging or relating to Rouen, specific name of an Ammonite. Ratitodi ligente, German, new red sandstone. Rotata, Latin, rotate, wheel shaped. Rotundus, Latin, round. Rubble, angular and broken fragments of subjacent rock lying beneath the superficial mould. Rudistes, from the Latin rudis, unacquainted, because the characters of the animal were unknown. Name of a family of extinct mollusks, in the shells of which neither the hinge, the ligament of the valves, nor the muscle of attachment is discoverable. The family contains 6 genera: spherolites, radiolites, calceola, burostrites, dicina, and crania. Rugosa, Latin, rugos, wrinkled. Rugosity, a wrinkling. Ruminantia, order of mammals which chew the cud. Ruminants, animals that chew the cud. Saccharoid, from the Latin saccharum, sugar, and the Greek eidos, resemblance, resembling loaf sugar. Sal ammoniac, a compound of ammonia and hydrochloric acid, muriate of ammonia. Salt, any combination of an acid with a solidifiable substance. Sandalina, Latin, sandal-like. Sandstein, German, sandstone. Sandstone, any rock consisting of aggregated grains of sand. Saurians, from the Greek, sauros, a lizard, animals of the lizard tribe. Sauroid, from the Greek, sauros, a lizard, eidos, resemblance, resembling a lizard. Saxiogenous, from the Latin saxum, rock, and the Greek geonomy, I produce, rock producing, rock forming. Scabra, Latin, rough. Scaphites, from the Greek, scaphe, a boat, the boat ammonite. Schist, German, from the Greek, schistos, split, slate. Schistose, slaty. Scoriae, Latin, plural of scoria, dross, volcanic cinders, cinders and slags of basaltic lavas of a reddish brown and black color. Scoriaceous, of the nature of scoriae. Scoriaform, in the form of scoriae. Seams, thin layers or strata interposed between others. Secreted, separated by the action of organs. Sediment, from the Latin sedeo, I sit, that which subsides or settles to the bottom of any liquid, dregs. Sedimentary, belonging or relating to sediment. Selenite, a variety of gypsum. Sella, Latin, a saddle. Semi-crystalline, partly crystalline. Sensibly, perceptibly. Sepia, a kind of paint or ink prepared from the cuttlefish. Septa, Latin, plural of septum. Septaria, flattened balls of stone which have been more or less cracked in different directions and cemented together by mineral matter which fills the fissures. Septum, Latin, a partition. Cereale, Latin, ceria, a jar, jar-like. Serpentine, a magnesian rock of various colours and often speckled like a serpent's back. It is generally dark green. Serpula, from the Latin serpo, I creep, a genus of annelidans which inhabit a calcareous tube, usually adherent to the shells of mollusks. Sessile, from the Latin sessilis, dwarfish, without a pedicle or support. Shale, an indurated slaty clay or clay slate. Shingle, loose, water-worn gravel and pebbles. Singularia, from the Latin cingulum, a seal, fossil plants found in the coal formation. Silex, from the Greek callus, a pebble, the principal constituent of quartz, rock crystal, flint, and other silicious minerals. Silica, silicious earth, the oxide of silicon, the elementary basis of silica, constituting almost the whole of silex or flint. It combines with many of the metallic oxides and is hence sometimes called silicic acid. Silicate, a compound of silicic acid and a base. Silicate of iron is a compound of silicic acid and oxide of iron. Plate glass and window glass are silicates of soda and potassa, and flint glass is a similar compound with a large addition of silicate of lead. Silicious, containing silica. Silicified, petrified or mineralized by silicious earth. Silt, the name given to the sand, clay, and earth which accumulate in running waters. Silurian system, series of rocks formerly known as the Greywacke series. Sinutata, Latin, hollow, excavated. Sinus, Latin, a hollow or excavation. Sinuosity, a hollow, an irregular winding excavation or hollow. Siphon, from the Greek siphon, a tube, a cylindrical canal perforating the partitions of multilocular shells. Siphuncle, a small siphon. Slate, a well-known rock which is divisible into thin plates or layers. Socialis, Latin, social, relating to companions. Solfatara, Italian, a volcanic vent emitting sulphur and sulphurous compounds.
Solum, Latin, the sun. Spatongus, from the Greek, spatogos, a species of Echinus, a genus of sea urchins having the mouth situated laterally, but 4 rows of pores. Species, a kind, a subdivision of genus. Specific weight or specific gravity, the relative weight of one body with that of another of equal volume. Sphenopterus, from the Greek sphen, a wedge, pteris, a fern, a genus of fossil plants. Sphenophylites, from the Greek sphen, wedge, phullum, leaf, lithos, stone, a family of fossil plants. Spherolites, from the Greek sphaira, a sphere, lithos, a stone, a variety of obsidian or pearlstone, which occurs in rounded grains. Spinosa, spinosum, Latin, spinous, covered with spines. Stalactites, from the Greek stalactio, a drop, conical concretions of carbonate of lime attached to the roofs of calcareous caverns, and formed by the gradual dropping of water holding the carbonate in solution. Stalagmites, stalactical formations of carbonate of lime, found on the floors of calcareous caverns. Staurotide, from the Greek stauros, a cross, eidos, form, cross stone, prismatic garnet. It is very abundant in New England. Stellus, Latin, stars. Stigmaria, from the Greek stigma, an impression, a vegetable fossil. Strata, Latin, plural of stratum. Stratum, Latin, a layer, a bed. Stratification, an arrangement in beds or layers. Stratified, arrangement in strata. Striae, Latin, diminutive channels or creases. Striated, marked with striae. Strike, the direction of strata, the line of bearing. Sub, Latin, under. Sub-Apennine, applied to a portion of the Pliocene strata, low hills which border the Apennines. Sublimation, the process by which volatile substances are raised by heat and again condensed into the solid form. The substances so obtained are called sublimates. Submarine, beneath the sea. Submerged, immersed or covered by water. Sublicata, Latin, somewhat plated. Substratum, an underlayer or bed. Sulcata, sulcatus, Latin, sulcate, grooved or furrowed. Sulfatization, the act of converting into compounds containing sulphur. Sulphuret, a compound of sulphur with another solid. Sulphuric, sulphurous, relating to sulphur, applied to acids composed of sulphur and oxygen. Superposed, from the Latin super, above, pano, I place, placed above. Syenite and sienite, a granitic rock from Sinai or Siena in Egypt. It consists of quartz, feldspar and hornblende. It is tougher than granite and a more durable building stone. Synclinal, from the Greek sun, with, klinine, to incline. Synclinal axis. Tabular, in form of a table, horizontal. Talc, a foliated magnesian mineral of an unctuous feel, often used for tracing lines of wood, cloth, etc., which are not so easily effaced as those of chalk. Talcose, of the nature of talc. Talus, a sloping heap of fragments accumulated at the foot of a steep rock. Temperature, a definite degree of sensible heat. Tendon, from the Greek teino, I stretch, a fibrous cord at the extremity of a muscle, by which the muscle is attached to the bone. Terebellum, from the Latin terebo, I bore, a genus of gastropod mollusks. Terminal, belonging to the end. Testaceous, from the Latin testa, a shell, consisting of carbonate of lime and animal matter. Testudinaria, a tribe of chelonian reptiles. Thermal, from the Greek therma, heat, warm, hot. Thermometer, From the Greek, therma, heat, metron, measure. An instrument for measuring heat. Thin out. Strata are said to thin out when they diminish in thickness. Tissue. From the Latin, tela, a web. A web or web-like structure constituting the elementary structures of animals and plants. Trachyte. From the Greek, trachos, rough. A variety of lava. A feldspathic rock which often contains glassy feldspar and hornblende. When feldspar crystals are thickly and uniformly disseminated, it is called trachytic porphyry. Trap. From the Swedish trappa, a flight of stairs, because trap rocks frequently occur in large tabular masses, rising one above another like the successive steps of a staircase. Applied to certain igneous rocks composed of feldspar, augite, and hornblende. Trappean. Relating to trap rocks. Trapezoidal. In the form of a trapezium. Travertine. From the Italian travertino, limestone deposited from water holding carbonate of lime in solution. It is found in the sweet springs of Virginia and at the hot springs of the Washita in Arkansas, as well as in many other places. Tremolite. A mineral often of a fibrous structure, generally containing silica, magnesia, and carbonate of lime, originally found in the valley of Tremola on St. Gothard. Trenchant. Cutting. Trias. From the Latin tres, three. Triassic. Of the nature of trias. Trigonalus. Latin, from the Greek trias, three, gona, angle, having three angles or corners. Trigonia. From the Greek trigonos, three cornered. A genus of bivalve mollusks, most of which are extinct. Trigonula. Latin, having three little angles. Trituration. From the Latin tritus, rubbed, the act of rubbing or grinding. Truncate. Terminating very abruptly, as if a portion had been cut off. Truncatus. Latin, truncate. Tufa. Italian, a volcanic rock composed of an agglutination of fragmented scoriae. Turbo. Latin, a twisting, a genus of univalve gastropods. Turbinata, turbinatum. Latin, shaped like a top. Turriculated, resembling a tower with turrets. Turritella. Latin, a little tower or turret, a genus of gastropods. Undulation, a wave, arranged in a wave-like manner. Undulatus. Latin, waved, having a waved surface. Unilocular. From the Latin, unus, one, loculus, partition, having but one chamber or compartment. Unio. Latin, a pearl, a genus of mussels. Uniones, plural of unio. Unstratified, not stratified. Uptilted, tilted up, raised at one end. Ursus. Latin, a bear. Varians. Latin, varying, changing. Vascular. Containing numerous vessels. Vegetative life, life of nutrition. Venericardia. From Venus and cardium, a genus of bivalve mollusks. Ventricosa. Latin, ventricose, inflated, swelled in the middle. Vertebra. From the Latin vertere, to turn, a joint or bone of the spine. Vertebrae, plural of vertebra. Vertebral column, the spine or backbone. Vertebrate, having vertebrae or a spine. Vesicularis. Latin, vesicular, containing vesicles. Virgula. Latin, a little rod. Viridius. Latin, green. Vitreous. From the Latin, vitrea, glass, resembling glass. Vitreoresinous, partaking of the nature of glass and resin. Volatile. From the Latin, volo, I fly, capable of assuming the state of vapour and flying off. Volatilize, to become volatile. Volcanic, relating to a volcano. Voltsia, a genus of fossil conifers. Voluta, Latin, a whorl, a genus of gastropods. Vosgean, belonging or relating to the Vosges. Vulgarius, Latin, common. Walchia, a genus of fossil conifers. Weald, name of a part of Kent and Surrey in England. Whinstone, a Scotch name for greenstone and other trap rocks. Zamia, from the Greek zemia, loss or damage, a genus of the order of Cycadae plants. Zechstein, German, a magnesian limestone lying under the red sandstone. Zoophyte, from the Greek zoon, an animal, phuton, a plant animal which seemingly partakes of the properties of both plants and animals. End of glossary M through Z.